Hello everyone, welcome to the course. This is Vinod and I will be the instructor for this course. I am super excited that you are going to start your journey to learn data structures and algorithms. And I promise you made the right choice by joining me in this adventure. Because today data structures and algorithms provides the massive support for the technologies whatever we have right now. I wanted to take a moment as early on this course to talk about what makes this course so special, why it's the only course you will ever need to learn data structures and algorithms. And I feel really strong about that. This course is everything you need from start to end, regardless of your experience. There is something for everyone. I will take you from very beginning up to complex and advanced topic in data structures and algorithms. This is not a course where we request to have a computer science degree. This course is for people from every background. You can think of people who are fresh out of high school and who want to learn a new skill and who want to be a good programmer, and people from all over the world and all different level of education. I have designed this course such a way. I wanted to make a note here. In this course, we are not going to dive into any programming language specific things. But we need some programming language to demonstrate the things we are going to discuss here, right? So for that in this course, I have used Java, but still I mention you that we won't discuss here anything about Java language specific things. Data structures and algorithms are generic skill for all the programmers. You may JavaScript developer, or you may C developer, or you may C++ or Python or Java developer, or you might have interested in any other programming languages. I promise that this course will be suitable for you as well. Without further ado, I want to give you a quick overview of how this course is organized and what exactly you are going to learn in this course. I have designed this course in two parts. The first part contains a ton of information about data structures. Here we will cover all the data structure concepts, and in the second part of this course contains various algorithms. Here we will discuss shortest path algorithm and search and sorting algorithms technique based on the problem we are facing right now in the product implementation. I split these two parts into 10 sections, including where you are right now. Right after this section, we are going to start with basics of data structures and algorithms. Here we are going to spend some worthy time by talking about what is data structures and what is algorithms and why it's so important and how to analyze the algorithms. Along with this, we are going to discuss the concepts like complexity and big O notations and much more. After that, we are going to take a look at basic data structures like an array and linked list and its various types. Along with this, we will focus on hashing and various hashing techniques. And starting from this section, we are going to get our hands dirty with programs. In this course, data structures or algorithms, whatever it is, once we discussed about this specific topic, we will try it out the concept or implementation approach for the concept in programming. Since I am not strict into any programming language in this course, we will discuss only about the logic to implement particular data structures or algorithms. And then we move to stack and queue data structures. Here we will discuss about stack and queue data structures and its real-time applications and its various types. Right after that, we are going to take a look at advanced data structures. In this section, we will start with tree theory, and here we will discuss about the tree data structures and when to use tree data structure and how we can search over the tree and various traversal algorithm to travel over the tree data structures. After that, we will see graph theory. Here we will discuss about graph data structures, when should we go for graph data structures and graph traversal technique and much more about the graph data structures. And then we will move to algorithms to find the shortest path in graph data structures. Since graph is one of the most useful and complex data structure in all the time, here we will discuss about different algorithms to travel over the graph. And then we will move to search algorithms. Here we will discuss about the best searching algorithms for the search problems. Right after that, we will see sorting algorithms. Here we will discuss about some of the best algorithms to sort our data structures. And finally wind up on conclusion of this course. In all of the videos, I will explain each and every single details about the data structures and algorithms of the technique I am using. But sometimes you may still have a question about one of the topic you are learning in particular video, or maybe you just run into a problem with your code and need helps to fix it. Well, either way you can always get help here in Udemy Q&A section. So at the bottom of the video that you are watching, you always find a Q&A section for that specific video. So whenever you have a question, you can check if another student has already asked the same question before, and if not, well, you can post your own, and then you will get friendly and fast support from me. So that will help you to back writing code as fast as possible. And also, you can Google it your own to get the solution for your problem, and you can check in Q&A forums like Stack Overflow or any other technology forums. But I would suggest that before asking help from me or Google or others, ask yourself first. I mean, to spend some time to find the solution for your own. It will increase your problem solving skill and it will increase your debugging ability. So I hope you are going to have a ton of fun within this course, that you become a good programmer, and that you will take your career to next level. That's really all I wanted to achieve within this course. And with that being said, let's finally get started. So why you should learn data structures? Give the best possible idea to some fool and give your notepad to a good developer. Then you will see the difference between the two. You need to understand algorithms and data structures, because I have seen code written by the people who did not understand data structures and algorithms. And trust me, you don't want to be that guy. Data structures and algorithms skill will improve your problem solving skills, which is essential if you want to become a good developer. Even if you know 100 different programming languages, without knowing the simple graph or hash map, it would be impossible to make a simplest search engine. Say for example, suppose you want to learn riding a bike. Will you ask the question that why you should learn about gears and brakes? Definitely no, because those are not different from each others, and gears and brakes are the basics of riding a bike in much better way. Similar in case of data structures and algorithms. Those are not different from programming, rather concepts of building a program in efficient way. Similar to riding a bike, that applying of gears and brakes will be the route to show the skills. Data structures and algorithms are the route to show the programming skills. Without knowing the data structures, the knowledge of programming language worthless. And programming languages are just a tool that we use to express our mind to code. It's like choosing the right tool for a task. If you need to building a crib for your son, would you use steel? That's expensive, and compared to wood, it's slow on manufacturing, right? And it overkills. It's a crib, not a bunker. So choosing a right thing for your right problem is a skill. I will end up with motivating quotes for all you programmers. A good programmer looks both ways before crossing a one-way street. Hello guys. Here we will start with what is data structures. Data structure is a way of organizing the data in a computer. First of all, why should we organize the data? What will happen if we haven't organized the data properly? Let's imagine you went to one big library. Just think you want to read some particular book. Imagine the situation that the library hasn't organized the book in any order. Means the library hasn't organized the books based on any category. In reality, there might be a chance the library might have 10 or 15 lakhs of books, right? From this huge number of collection, how you will find the book which you want to read if it is not organized properly? It's impossible, right? This is the reason library books are arranged in some order. So for example, fiction books are all in one place and non-fiction books are all in some other place, something like that. Even inside the fiction and non-fiction category, books should be arranged based on alphabetical order. In such a case, it will be more easy to find the books. It does not matter the library having huge number of books if the library books are arranged in some order. If it's in like this way, it's not a big deal, even if the library having 10 crores of books. Am I right? This is the importance of organizing things. The same technique is followed in Bookshop as well. You can see that in Bookshop, there will be a separate section for bestseller books and a separate section for highest rated books or famous authors section, something like that. If it's in like this way, it will be easy for the customers to pick the right book which they are interested in, right? Dictionary is the another perfect example for the data structure. Let's imagine you want to search some word from the dictionary. Let's take the word apple. Means you want to know meaning of the apple. If you see the dictionary, there are lakhs of words within it, right? So how you will search the word apple from the huge number of word collection in the dictionary? It's quite simple. You can directly go to the location the words starts with letter A and then you have to go to next letter P. Something like that. Means A and then P. Correct? Assume that in the dictionary words are in random order. Then how you will find the word called apple? from more than lakhs of the words? It's impossible, right? So words must be organized some way in the dictionary to find the word in a short time. Not only in library or dictionary, organizing the things is quite normal in your day-to-day activities. So for example, in your home, dresses and all you will keep it in your dressing room, and groceries and all you will keep it in your kitchen, right? Just for instance, imagine you kept your watch in somewhere and you don't know where it is. Now where you will search your watch? Will you search it in kitchen? No, right? You will search it in your dressing room, not in kitchen, because normally these kind of things you will keep it in your dressing table or your property cupboard, somewhere like that. So organizing things is more important so that we can manage the things quickly. Like this way, data structure also same concept. It's a concept of organizing the data in a computer so that data can be used efficiently. And the most important thing you should understand is data structure is not a technique, it's a skill, or we can say like it's a knowledge. Do you know what I mean? It's not about only storing or organizing the data, it's also about choosing the right data structure in right place. It's not a technique, it's a knowledge. Both are completely different. Storing the data into some data structure, it may be a technique, but choosing the right data structure for your situation is a skill. It will come from experience. Choosing wrong data structure is somewhat similar to choosing a white marker to write it in whiteboard. Hope you understand. So the key point is, data structure is important to store the data, but the way of storing the data is more than important than storing the data. Algorithms. It's a more controversial word in mathematics and computer science world. Okay, fine. Here I just picked up some random numbers. Just have a look at these numbers. Take your own time and find the biggest number from this list. So you might identify that 9 is the bigger one from this list of numbers, correct? Okay, now go back and just think slowly what you did to find the biggest number from this list. You started looking at this first number and then you have moved to second number. And you might compare the second number with the first one, and your mind stores that 4 is the biggest number for now. And then again your eyes has moved to next number and compare this with the number which you already memorized as the bigger one, that is 4. Since next number is less than 4, your mind keeps 4 as the biggest number. Again for the next number, you know still 4 is the biggest number, and again next number, it's 9. So your mind automatically registers that 9 is the bigger number now by comparing with 4, and you would move to next number. It's not greater than 9, so you kept 9 as the bigger one. And then last number, again no, so you declared 9 as the bigger number from this list. This is how you identify 9 as the bigger number from this list, right? You know what you did now? You have just used some procedure to identify the bigger number, right? This is what algorithm is. Algorithm means well-defined procedure to implement something. There may be a lot of ways to implement the specific problem, but algorithm is the efficient way to do that. Or simply we can say that an algorithm takes a value or set of value as input and produce the value or set of value as the output. So algorithm is thus a sequence of steps that transform input into the output. To understand this and more clear, we will take an example. Let us consider the problem of preparing an omelette. To prepare an omelette, we have to follow some steps. First, we have to get the frying pan. And then the second step is we have to get the oil. Here we have to check whether do we have oil or not. If we have oil, we have to put it in a frying pan. If no, there we have to decide do we need to buy oil or not. If yes, then we have to go on buy. If no, we have to terminate the process. Once we have the frying pan and we have oil, then we have to turn on the stove and do the cooking. That's it, right? Here what we are doing, we are providing a step-by-step procedure to make an omelette. It's algorithm for preparing an omelette. So algorithm is step-by-step instructions working quietly behind the scene. We can also view an algorithm as a tool for solving a well-specified problem. Again, I am highlighting that algorithm means well-defined procedure for the implementation. In real time, for the specific problem, we might have lot of options to choose from the algorithms. It's very important to analyze the algorithm and choose the right one for our problem statement. For example, if you want to go from city A to city B, there can be many ways to go. For example, by flight, by bus, by train, and also by bicycle. Depends on the availability and convenience. We have to choose the one which is suitable for us. Similarly, in computer science, multiple algorithms are available for solving the same problem. Say for example, a sorting problem has many algorithms like insertion sort, selection sort, quick sort and many more. It's our responsibility to choose the right one. Analysis the algorithm helps us to determine which algorithm is most efficient in terms of time and space consumed. Hello guys, welcome back. When we talk about the best algorithms, best practice or performance of the program is everything based on the execution time of the program. An ultimate aim for every programmer is reduce the execution time of the program. Am I right? So when we will say that this is the best algorithm for this process, it's simple. The algorithm which gives the result in short time in all the cases. That is the suitable algorithm for that process. So the next question is how to visualize the execution time of the program. Let's take this simple code. Here I'm just printing the numbers from 1 to 10,000. That's it. If you are not understanding this code, don't worry. As of now, you just understand the logic we have written here. If I execute this code, this will print the numbers from 1 to 10,000. That's it. Now we want to understand that the execution time of this code. This line of code will give us the total execution time for this method. If you see here, I just captured the time when this method starts to execute. And similarly, I'm just capturing the time when this program finishes its execution. Finally, by subtracting execution end time with the start time, we will get the total time of the program execution. System.currentTime_millis is the predefined method in Java to get the system time. Like this, in JavaScript, we can use performance.now. Similarly, your favorite language also will have some method or function to get the system time. You can use that to find the execution time of the program. Okay, now we will take one problem statement and we will try to figure out best algorithm for that problem. Let's take, we wanted to find out the number from some collection of numbers. So for example, we have numbers from 1 to 10 million. From this number collection, we have to find out 9,999,996. We knew that surely this number will be present between 1 to 10 million, but we just wanted to check by using our program. Here my idea is I'm going to check the numbers one by one from this collection. If I found this value, I'm just printing the message saying that we found it on after this many tries. I'm just using one int variable to keep track on number of tries we made to find this number. This idea is nothing but it's my algorithm to do this process. Again, I'm telling that don't worry about the code. Just take an idea to implement the logic. Okay, now let's run this program and see how many tries we are taking to find this number. And also we will see how long we are taking to execute this program. Let's run this. See here, this algorithm finds the value after this many tries. Means 9,999,997th try. And the total time taken for this process is 10 milliseconds. But algorithm execution time will not always same for every time. If we run this code for next time, we may end up with different execution time. Even we are not changing anything in the code. We are running same code and same machine, but still we are getting the different execution time. It's quite common. But if you see the number of try, it will be same for all the time. So for now, we can take this algorithm approximately taking 7 or 8 milliseconds to find this number. Okay, now I'm just thinking, is there any better way to do this job? There are two kinds of numbers. One is odd number, another one is even number. So for example, if it's even number, why should I check odd numbers? If I skip checking odd numbers, I can save half of the tries, right? Let's change my algorithm. Now this iteration starts from 0. I'm just increasing I value by 2. So I will check the number which is we are looking for is 0 or not. If no, I will move to 2 instead of 1. After 2, I will move to 4 without checking 3. Like this, I will skip all the odd numbers. And if the number we are looking for is odd number, then I will start the iteration from 1. So for the next iteration, it will be 3 and then 5 and then 7 like that. Okay, let's run this code. See here, this algorithm finds the value after this many tries. Means 4,999,999th try. Seems like the number of tries reduced by half of the time. And the total time execution for this process is 4 milliseconds. Now I'm pretty much happy with this, but still I can think, is there any better way to do this? Okay, after I spend some time, I come up with another algorithm. Now my idea is, I'm splitting the collection of numbers into two off by identifying some mid element. It's simple, total number of elements divided by 2. It's the mid element. If the value I'm looking for is lesser than the mid, then there is no use if I travel over the second off, right? Similarly, if the number we are looking for is greater than the mid, then there is no use if I travel over this first off. Okay, now if we find the mid number from this number of collection between 1 to 10 million, mid will be 5 million. So I'm checking the value we are looking for is greater than 5 million or less than 5 million. If it's less than 5 million, then we have to go over the first off or else second off. In this case, the value we are looking for is greater than 5 million, right? So we have to go over the second off. Again, I'm finding the mid element from this collection of numbers, and again I'm doing the same process until I found the number. I feel it's a great idea or algorithm to find the elements from the large number of collection. This is the implementation for this algorithm. See here, first I find the mid element. Then based on the mid element, I am deciding whether I am going to travel for first off or second off to find the element. In this case, the number we are looking for is greater than the mid element. So obviously we have to go for the second off. So to travel the second off, again I am calling the same method recursively by changing the starting number. So now the new collection is the complete second off of the original collection. Again I am dividing this collection into two off and doing the same process. At some point I will get the number. Let's run this program and see the result. See here, this algorithm finds the value after 20-second try. And the total time taken for this process is not even 1 milliseconds. Now I am pretty much happy with this performance. Still, we may get a better algorithm than this. When we talk about the algorithm for some process, we can't say that this is the best algorithm for this process. Maybe today this is the best approach, but tomorrow someone may discover the better algorithm than this algorithm for this same process. It's like an endless process. So put your effort to find the best algorithm for the process. See you guys on the next video. Hello guys, welcome back. Why algorithms are so much important? Imagine that you have two Rubik's Cube in front of you. One of them you are allowed to use existing algorithms, like how many times or which direction to turn your face, something like that. On the other hand, you have to find your own way to arrange the Rubik's Cube in proper order. Now tell me, which way will be faster? Almost certainly the first way. There are already hundreds of well-established algorithms to solve a Rubik's Cube, and trying to invent your own method to solve will take much longer than utilizing the current ones. Worse than that, it's most likely that the method you choose will be less efficient and slower than the method that already exists. And even worse than that, the method you invent probably only works for your specific configuration of Rubik's Cube. And considering there are 43 quintillion different configurations, your method isn't quite going to do the job if something changes. Let us take a real-time example. I'm going to Google search engine. Here I will search for something, like what is data structures. When I hit enter for this search, I will get this as result. Okay, think about what Google server will do when I type something in the search bar and hit enter. It will find the words what and is and data structures. These three words in the server. It will find lakhs of web pages contains this keyword, right? From that list of web pages, Google will give the rank for that based on the Google ranking algorithm. So that we are getting the top result in the first page like this. More than 90% we will get the expected result from Google search, right? Just see here the total time taken for this full process. It's just less than a second. So Google processed more than lakhs of web pages and sorted within a short span of time. That's the power of algorithms. Do you think it's possible to get the same performance without an efficient algorithm? Absolutely not. I hope you understand the importance of algorithms. See you guys on the next video. Hello guys. In this video, we are going to discuss about complexity of algorithms. As I said earlier, in real time, we might have a lot of options while choosing an algorithms. Which means for a single problem, we will have a lot of algorithms to solve. Analysis of algorithm helps you to choose the right one. We will analyze the algorithms based on the complexity of the programs. So it's very important to know how to calculate the complexity of the program. So how to calculate the complexity of the program? In every program, arithmetic operations like addition, subtraction, multiplication and division and assigning some value to one variable and all will take one step to execute. So these lines complexity and all constant time. If you take this program, it's a simple search. Here I am searching the value x within this array. If I found the value x, I will print we found h. If the value is not available means I will just print value not found. If I calculate the complexity for this program, this line will take one step to execute. Means this line will execute for only one time because just we are assigning some text to this string variable. So this line complexity will be constant time. To represent this constant time, we will use alphabet C. So I mention it as C0. This if block complexity is also constant time. And this assigning operation also will execute for only one time. So I will represent this as constant time, that is C1 and C2. But these lines of code is present inside of a for loop. Means how many times this for loop is executing, that many times these lines of code will also execute. If this for loop execute for n times, then these lines also will execute for n times. Okay, I will calculate the complexity of this program. It's constant time, that is C0 plus this if block is C1 plus this assigning operation is also constant time, so C2. This C1 and C2 is inside of for loop. So many times these lines will execute. In this case, if I am posing 10 elements within this array, these two lines of code will execute for 10 times. If it's 1000 elements, then it will execute for 1000 times. So I am referring this as n times for C1 and C2. Plus this return statement. This is also constant time. So I am referring this as C3. So finally, this is the expression we got for this program. While calculating the complexity, we will take the highest power of n as the complexity of the program. So for this program, complexity is n. Just consider we have this for loop is inside of another for loop. If so, we will write the expression as C0 plus n times of C1 plus C2. This complete section is inside of another for loop, right? So n times of n into C1 plus C2 plus C3, which is equal to C0 plus n square of C1 plus C2 plus C3. Here maximum power is 2. For this case, complexity is n square. This is how we have to calculate the complexity for the algorithms. If you are not understand the array and the search logic means, don't worry. We have separate section for array and search logic and all later in this course. In this video, our aim is to understand how to calculate the complexity. Hello guys, welcome back. Here we are going to discuss analysis of algorithms. Assume that we have two algorithms for a task. We have to find out which one is better. In general way to do this, implement both the algorithms and run the two programs on your computer for different inputs and see which one takes less time. Assume that first algorithm takes 5 seconds to execute and second algorithm takes 7 seconds to execute. Now tell me which one is better one. Do you think first algorithm is better than second one? We could not say like that at this stage because there are many problems with this approach for analysis of algorithms. It might be possible that for some input, first algorithm performs better than second, and for some input, second performs better. It might be also possible that for some inputs, the first algorithm performs better on one machine, and second algorithm works better on another machine for some other inputs. Asymptotic analysis is the great idea that handles this kind of issues while analyzing an algorithm. In asymptotic analysis, we evaluate the performance of the algorithm in terms of input size, which means we don't measure the actual running time. We calculate how does the time or space taken by algorithm increases of input size. For example, let's consider the search problem in a sorted array. Means we have an array which is having an element in sorted order. We can do a linear search or binary search. We will talk about the linear search and binary search in more detail later on this course. But to understand this example, as of now, you just know that linear search complexity is n and binary search complexity is log n. In the last example I used for calculating the complexity is linear search. Okay, fine. To understand how asymptotic analysis solve the problem while analyzing the algorithms, let's consider we run the linear search on a faster computer and binary search on a slower computer. For small value of input array size n, the faster computer may take less time. But after certain value of input array size, that is if it increases to 1000 or 10,000 elements, the binary search will definitely start taking less time compared to the linear search, even though the binary search is being run on slower machine. The reason is the order of growth of binary search with respect to input size logarithmic, means log n, while the order of growth of linear search is linear. Hello guys, welcome back. When we calculate the code complexity, we have to consider three scenarios. First one is big O, second one is omega, third one is theta. Big O is the worst case scenario and omega is the best case scenario. We will represent this with omega symbol. And theta is the average case scenario. We will represent this with theta symbol. For example, you are bringing $100 into a casino to gamble. The best case is that you walk out owning $500 or $1000. It's possible, but so unlikely that you should not even think about it. The worst case, that you may lose all the dollars. And next, the average case, that the typical better losses or win, like you lost or win $1 or $2. Here, your huge loss is worst case scenario, which is big O. Big O means bad scenario. By your luck, if you win more dollars, it's a best case scenario. And $1 or $2 losses or win are average case. I will explain this with graph. Let's take x-axis and y-axis. In y-axis, I am taking the code time complexity. And the x-axis, I will take some function. This function has three executions. One is here, here, and here. Suppose if we are looking for the execution time for some input, let's take here. Consider that here the execution time is 1 second. It's the best case scenario, which is omega. And for the same input, average case is 3 seconds. This we can represent as theta. And let's take this. This is 7 seconds. This is worst case scenario, which is big O. If you see the difference here, big O is the bad case. In this whole course, our aim is to concentrate on the worst case scenario because we don't need to worry about the best case. As a programmer, we have to take the worst case and work with that in the best way to improve the performance of the code. Let's take this list of values: 5, 9, 6, 1, 4, 8, 2 and 7. I'm going to find number 7 from this list of values. If we go over linear way to find this 7 from this list of values, we have to start from first element. So first I will check whether this first element is 7 or not. No, right? So I'm moving to the next element. Is this 7? No. Then next. Is this 7? No. Like this, I will check all the elements one by one till I found the number 7 from this list of numbers. So finally, I found the value 7 at the 8th position. If I count the number of tries I made for this search, 1, 2, 3, 4, 5, 6, 7 and 8. So I got the number which I was looking for at the 8th try. If you see the total array size, it's 8. I found the expected value at 8th try. This is the worst case scenario. Whatever number I am searching for and it's present in the last element of the array, then that will be the worst case scenario for this situation. If 7 is there in the first position of this list, it will be best case scenario. If it is present in the middle, then we can consider that as a average case. Hello guys, welcome back. When we talk about code complexity, for some algorithms, we may got the complexity of log n. So what is meant by log or logarithms? If we add 8 with 2, the result will be 10. It's a simple addition operation, right? For this addition function, we have reverse function, that is subtraction. I can rewrite this like 10 minus 2, which is equal to 8. Like this, what will be the result if we multiply 5 with 2? It's 10. For this multiplication, reverse function is division. So we can rewrite this like 10 divided by 2, which is equal to 5. Now tell me, what is the value if we raise 10 to the power of 2? It's 100, right? For this kind of function, we have reverse functions, that is logarithms, which means log base 10 of 100, which is equal to 2. We can call the log base 10 as log. In general, scientists and engineers and all will do the logarithmic calculation with base 10 only. That is the reason scientific calculator and all have only log. Means base 10 will not be mentioned in the calculators. So log means it's basically log base 10. Okay, now we will look more examples of logarithms. Just take 2 to the power of 4. It means we have to multiply the 2 with 2 for 4 times. That is 2 into 2 into 2 into 2, which is equals to 16. I am just rewriting this into 2 to the power of x, which is equal to 16. For this reason, logarithms comes into picture. How many times we have to raise the 2's power to get 16? It's 4. If I write this in log base 2 of 16, which is equals to 4. For 3 to the power of x is equal to 81. Now tell me how many times we have to raise 3's power to get 81. 3 into 3, 9, into 3, 27, into 3, which is 81. So 4 times we have to raise the 3's power to get 81. Here x will be 4. If we represent this in log, it will be log base 3 of 81, which is equal to 4. In this video, we are going to discuss different levels of complexities in terms of Big O. When we talk about code complexity, we will have different level of complexity for the algorithms. Here I will plot the graph for the complexity level from low to high. The first level is O of 1. When we talk about Big O, we will represent the notation as O. In this graph, I am referring all the levels of complexity in terms of Big O, because we are not going to concentrate on the best case and average case scenarios. Our ultimate aim is take the worst case scenarios and work with that in best way. Sounds good, right? And next level is O of log n, and the next level is O of n, and next higher level is O of n log n, and next is O of n square, and next one is O of 2 power n. I will give example for these levels of complexities so that you will get clear idea about these complexities. So the complexity of O of 1 means it's one step to execute. For example, a equals to b plus c, or c equal to 1 plus h, something like this. And next level of complexity is O of log n. O of log n is basically time goes up linearly while the n goes up exponentially. So if program takes 1 second to compute 10 elements, it will take 2 seconds to compute 100 elements. Like that, it will take 3 seconds to compute 1000 elements, and so on. That is 10 power 1 is equal to 10, and 10 square equal to 100, and 10 cube equal to 1000. Take this example. This block of code will act based on log base 2. The for loop multiplies the current value of I by 2. So it goes from 1 to 2, 2 to 4, 4 to 8, 8 to 16, and 16 to 32, like that. Because every time we are multiplying the I value with 2. In this block of code, just think we are passing n value as h. Initially, I value will be 1, and the next iteration, it's 1 into 2, which is equal to 2. For the next iteration, 2 into 2, which is equal to 4. And for the next iteration, I will be h. So this hello prints for 4 times. If I increment the I value by 1, this loop will execute for 8 times. But it's not a case here. Here we are doubling the I value on each iteration. So this block of code complexity is log n. I will do this for log base 3. Then the code will be like this. Here I value goes from 1 to 3, 3 to 9, and 9 to 27, like that. So hello prints for 2 times. Because after this loop execute for second time, I value will be 9. So it will be exit from the loop because we have given n value as 8. And the next complexity is O of n. If you see this block of code, I value is increasing by 1. If we pass n as 8 here, this loop will execute for 8 times. If n is 100, then it will be 100 times. So this code complexity is O of n. And the next complexity is O of n log n. See this piece of code. This for loop is inside of the another for loop. So the first for loop will execute for n times, and inside that the another for loop will execute for log n times, because we are incrementing the I value with log base 2. So its complexity is log n, and this first loop complexity is n times. So its complexity is n times of log n, which is equals to O of n log n. And the next level of complexity is O of n square, which is for loop is inside of another for loop. See this example. This for loop is inside of another for loop. This second for loop complexity is n, and it's present inside of this for loop. This loop complexity is also n, because we are incrementing the I value by 1. So n times of n, that is n into n, which is equal to n square complexity. And finally O of 2 power n. This Fibonacci method will call for 2 times, and recursively it will call for multiple times. So the complexity is 2 power n. Let's take that you are going to sort some numbers from given array. Already we have predefined algorithms for sorting problems. That is bubble sort, insertion sort, selection sort, merge sort, and heap sort. Don't worry about this. We have separate unit for these sorting algorithms. In that unit, we will go deep into the sorting algorithms. If you use bubble sort, your code complexity will be n square. And if you use merge sort algorithm to sort your array, the complexity will be n log n, which is lesser complexity than bubble sort. It's your responsibility to choose the right algorithm for your problem statement based on the complexity of the algorithms.
Hey guys, congratulations for completing the first unit of this course. This video is quick wrap up which you learned in this unit. First, we have seen about the data structures. A data structure is a way of organizing data in a computer so that it can be used efficiently. Storing the data is not unique for all the scenarios. It will vary based on the situations. Based on the problem statement, we have to choose the right data structures. And data structure is important to store the data. Way of storing the data is more important than storing the data. And we have seen about the algorithms. Algorithm means well-defined procedure for the implementations. And we are using the asymptotic analysis to analyze the various algorithms for a single task. In this method of analysis, we are analyzing the algorithm based on the complexity of algorithms, not based on the running time of algorithms. And finally, we have talked about Big O and levels of complexities for the Big O. Big O is the worst case scenario. Our aim is take the worst case scenarios and work with that in best way, because we are not interested in best case scenarios. See you guys on the next unit.
Hello guys, welcome to section 2. In this video, I am going to clarify the things about programming language, which is we are going to use throughout this course. This course is purely designed to focus on data structures and algorithms. I strongly believe that data structures and algorithms are not a technology. Using correct data structures and writing efficient algorithm is a skill. So I am going to focus on to teach you how to apply this skill in real applications, which means how to apply this knowledge while choosing data structure in real application. This skill is mandatory for the developer or architect who is working on or who is going to work on the technology like web application or machine learning or artificial intelligence or big data or whatever it is. It's a must-have skill. However, as an instructor, I should make you comfortable to understand the concept, which is we are going to discuss throughout this course. So I need some programming language to explain the concepts. So in this course, I have chosen Java to explain some examples. Since we are going to focus on only logic, I believe that if you are familiar with any programming language, you can understand the logic which is I'm going to write in Java. So you can just correlate the logics with the programming language which is you are already familiar with. Okay guys, we are ready to move on. See you in next video. Hey guys, welcome back. Whenever we want to work with large number of data values, we need to use much number of different variables. As the number of variables are increasing, the complexity of the program also increases, and programmer get confused with the variable names. There may be a situation in which we need to work with large number of similar data values. To make this work more easy, programming language provide a concept called array. That is what we are going to discuss in this lecture. An array is a variable which can store multiple values of same data type at a time, and it shares common name. In addition, this is most efficient data structure for storing and accessing a sequence of objects. Array occupies contiguous memory locations. Moreover, array size is fixed and cannot be altered dynamically. To understand the concept of array, I will give simple example. I am just declaring three int variable called a, b and c. If compiler executes this line, it allocates 4 bytes of memory with name a, and compiler will allocate another 4 bytes of memory with name b and more 4 bytes with name c. These three memory locations are may be in sequence or may not be in sequence. Here these individual variables can store only one value at a time. Imagine that compiler memory looks like this. Here assume that each box is 4 bytes of memory. If we assign a equal to 5 and b equal to 10 and c equal to 20, these values will be inserted in memory locations like this. Now consider array declaration. Int marks of 6. Here compiler allocates total 6 into 4 byte each integer, which is 24 byte of continuous memory location with the same name called as marks, but allows to store 6 different integer values at a time. Okay, I will represent this memory location in diagram. It will allocate 6 continuous memory locations in computed memory, and mark will be pointed to first memory location of the array. This can hold integer type of data because we declare this as int type of array. So it will hold only int type of data, and here we will store only 6 int values. Let's take 90, 92, 86, 91, 85, 88. While the complete set of values is referred to as an array, the individual values are called elements. But how can we refer or access the individual element is a big question, right? Compiler not only allocate memory but also assign a numerical value to each individual elements of an array. This numerical value is called as index. Typically, we need to use index to access the array elements. Note that index always starts with 0, not 1. So this is the index of 0, this is index 1, this is 2, 3, 4 and 5. So if you want to access fifth element from this array, you have to use index this. So mark of 4, which means it refers this element from the array. So it will return 85. And one more thing, if you try to hold another type of data, it will throw compile time error, because an array is a group of similar data type items. And another thing, the size of an int is really compiler dependent. Back in days, when processor were 16-bit, an int value was 2 bytes. Nowadays, it's most often 4 bytes on 32-bit as well as 64-bit systems. Okay, now imagine that if 90 is stored at the memory address 5500, then 92 will be stored at 5504 and 3 will be stored at 5508 and so on, because every int variable occupies 4 bytes of memory. This is the way array will work in any programming language. The thumb rule while we choosing data structure is always we have to consider about big O. I am not talking about only array. I mean all the data structure like linked list, stack and queue also. In general, what and all we will do with collection of data? We will access the element from the collection, we will add the element, we will delete some elements from the collection, and we will find the elements from the collection of data, right? So we have to calculate the complexity for these operations for all the data structures. By this way, we can identify which data structure is suitable for a given requirement. Let's calculate the complexity for these operations for array. So for this array, what is the complexity to access the element? If you want to access first element, you can directly use the index of an array, that is mark of 0. If you want to access fourth element, you can access it by mark of 3. Right, so its complexity is 1, that is O of 1. And the next operation is addition. While we add the element in array, if we add new element as last element of an array, it will take one time. But if you want to add the element middle of an array, what you will do? Just take that, you are going to add the element here. Then you have to shift these elements to next location. Then you need to add this element here. So this shift cost is n times, because you don't know how many elements will be there after write this. So you have to shift it for n times. That means complexity for the addition is O of n. And the next operation is deletion. It's similar to addition. If you want to delete the element at last, complexity will be 1. But if it is middle, then you have to delete the element first, then you have to shift it for n times. So the complexity of the deletion is O of n. And the last one is finding the element from an array. If you want to find 88 from this array, then you have to travel one by one and finally you will get the value. So you have to travel for n times. So the complexity for the search operation for an array is O of n.
Hello guys, welcome back. In this video, we are going to discuss about implementation approach for array. Here we are going to implement array operations like accessing element from the array and adding new element to the array and deleting the element from array and search particular element from the array. Let's start with accessing the element from array. This is main method of the program. Program execution will start from here. Here we have declared one array with 6 elements. And if you see here, this array type is int, means we are going to store integer values into this array, which is 1, 5, 2, 8, 7 and 3. We can access the elements from the array using index positions. Always remember that array index starts from 0. In this case, element 1 will be in index position 0 and 5 will be in index position 1 and 2 will be in index position 2. Similarly, 8 will be in index 3 and 7 and 3 will be in index position 4 and 5. So to access the element, we have to use these index positions of the elements. Say for example, to access this 8 from this array, we have to access it like array of 3. Like this, if we want to access this 5, we have to access it by using its index position 1. So we have to access it like array of 1. So this is how we have to access the element from the array. Let's go to the add operation. If we like to add new element at the last position of the array, we can directly add it in the last position. It's best case. But this is not the case for all the time, right? We might need to add new element in middle of the array. Let's take this same array we have used in this program. I will write index positions for these elements as well. 0, 1, 2, 3, 4 and 5. Okay, so for example, we would like to add a new element 15 in this position, means index position 4. But if you see here, in index position 4 already we have this element 7. So now we have to take right after this index position 4. We have to take all the elements and shift all the elements to one position right. Ensure that we are going to shift the elements right after this index position 4. Index position 0 to 3 will be remain same. In this case, we have to shift these two elements to one position right. Once we move these two elements to one position right, we will not have any values in index position 4, right? Now it's free space. Now we can insert this 15 into this index position 4. This is how we should implement add logic to the array. Let's go back to the code. I have created add elements method to add new element to the array. I just created object for this class and calling the add element method by using this class object.
It's just Java language feature to call a method in one class. So don't confuse with this. Anyway, this is not in our course scope as well. For now, you just understand that we have to create object for the class to call any method within that class. So we are just creating the class and calling the add element method. If you see here, this add element method will accept 3 parameters. First parameter is our array, because in this array only we are going to insert new elements. And second parameter is position. This is the index position where we are going to insert our new element. And the third parameter is actual element, which is we wanted to insert into this array and in this position. Okay, now I'm going to inside this method. The very first thing is we have to create new array with existing array size plus 1. Because if you see here, when we declare this array, we are not assigning any size to this array. While array creation time itself, we are storing the values within this array. So array will be created based on the values we have given to this array. If you want to add new element to this array, we have to extend the size of array. This is called dynamic array. When all space is consumed and an additional element is to be added to the array, the underlying fixed size array needs to be increased in size. But remember that typically the resizing is expensive, because you have to allocate a bigger array and copy over all of the elements from the array you have overgrown before we can finally append our new item. But here we are not doubling the size. Instead, we are just creating the array with extra one space. Okay, fine. Now we are ready with new array, and the next thing is we have to copy all the elements from the old array to new array, including this new value. Let's do that. Here our target position is index 4 and value is 15, which is we wanted to insert into this index position 4. So we are calling this add element method by passing our array and position to insert the elements and actual element value. Since index position is 4, we can keep index 0 to 3 remain same. So copy the elements from index 0 to 3 from old array to new array without changing anything. In this for loop, we are starting the iteration from index 0 to less than position, means index 3. So this loop will iterate from index position 0 to 3. Each and every iteration, we are copying the values from old array to new array. So after completing this for loop, our new array will contain these 4 values from the index position 0 to index position 3. And next element is our actual value. So the next step is directly assign this value into this index position 4. Now we are done with index position 0 to index 4. And finally, copy remaining things right after this position. That's it. So this for loop, we have to start the iteration from position plus 1. Why? Because we are already done with from position 0 to position 4. So we are starting this loop iteration from position 4 plus 1, which is 5 to new array size, which is index 6. Let's take first iteration. For the first iteration, I value will be 5. So the index position 5 is equal to array of I minus 1, which is old array 5th position minus 1, means array of 4. In the old array of 4 will be 7. Similarly, in the next iteration, index 6 of our new array will be array of 5, which is 3. That's it. We have completed our add operation. In the main method, I just created one array with values, and next I am calling the add method to insert these values into this array and in this position. After adding the elements, I just print the array elements. Here we are adding our new element 15 into index position 4. So our expected result will be 1, 5, 2, 8, after that 15, then 7 and 3. Let's run this program. See here, this is what we expected, right? 1, 5, 2, 8, 15, 7 and 3. Okay, let's move on next operation. Before we move into the delete operation, I wanted to complete search operation, because during the delete operation, before we delete the element, we have to check whether the element we are looking for to delete, which is there or not in the array. For this, we need search operation. So now we will see search. Here I am just calling the search method by passing array and the element we are looking for. Here we have to pass the element
we wanted to search within this array. I'm navigating to this search method. First, we are declaring the variable called location. Initially, this value will be -1, and here we are iterating our array from index 0 to till end of the array. If somewhere we found the element which is we are looking for, we just assign that index position for that element to location variable and exit from the loop. Finally, we are returning location of the element. Basically, this search method returns index position for the value which is we are looking for. If value is not found, we are just returning -1. -1 means no data found with that value in this array. See here, we are passing the actual array and value 8 to this search method, means we wanted to search element 8 from this array. Finally, we just print the returned value from this method, means index position of this element. Let's run this program. See here, we got 3. So this 8 will be present in index position 3. If we pass value which is not available in this array, we will get -1. Let's change this value to 100. Let's run this code now. It's -1. Clear? Okay. Now we will move to next operation, which is delete. Delete is also similar to add operation. If you want to delete last element from the array, it's simple. We can directly delete it, but it's best case. Then what about worst case? Delete the element from middle of the array. Let's take the same array which is we have used earlier. Let us take this 7. We will delete this 7 from this array. Means basically we have to shift this next index position to this position. Means one position left if we pass 7 to this delete method. Okay, let's do that. So going back to the code, we are calling this delete method by passing our array and the element which is we wanted to delete from array. The first thing is we have to find the index position of the element. So for that, we are just calling the search method we have implemented earlier. As we discussed earlier, this method will return index position of the element which is we are looking for. If the element not found, it will return -1. Let's take that. We are calling this delete method by passing this array and value 7. This search method will return index of this value 7 in this array. So it will return index 5 because 7 available in index position 5, right? So next we have to take these elements, means right after this element, and shift one position left. This for loop will do the shifting by one position left. If you see here, iteration starts from location plus 1 till end of the array. Inside this loop, for the every iteration, we are assigning next position to current position. This means one position left. And finally, I am copying this array into new array and returning that array. So whatever the array it's returning, that will not have this element 7. If you see here, after deleting, I'm just printing all the elements in this array. Let's run this program. See here, this 7 will be deleted from this array. So this is how we have to implement array operations. See you guys on the next video. Hey guys, welcome back. All the popular languages like C, C++, Java or Perl are starting the array index from 0, while last index is array length -1. While this is usual to most developers, it's not same fact for all the programming languages. For example, in Fortran, when you declare an array with integer a of 10, an int array having 10 elements, the index starts from 1 and ends at 10. However, you can override this behavior using a statement like integer a of 0 to 9 by declaring an array with indices from 0 to 9. But why should we start an index of an array from 0, not 1? First of all, it has strong relation to language design. For example, in C, the name of an array is essentially a pointer, a reference to a memory location. And so, the expression array of n refers to a memory location n minus elements away from the starting element. This means that the index is used as an offset. Take an array int array of 5. If compiler executes this line, it will allocate 5 memory location for the variable array. Imagine the memory location will be looks like this. And this array will point to the first memory location of this array. Let's assume starting address of this array is 5000. We can access the array with array of I, right? Since array is a reference to memory address, we can access the data by accessing the memory addresses. We can write array of I, which is equal to a reference of array plus I. If I equal to 0 means we wanted to access first element. Then array of I equal to reference of 5000 plus 0, which is 5000. So it will give this location value. As we discussed, we can access the array by using index, like array of index. Imagine that if index or start from 1, while extract this line, what we will get? A reference of 5000 plus 1, which is 5001. If this is the case, compiler would need to generate a reference of array plus index minus 1. This minus 1 would hurt the performance. To understand this more better, I will give one real-time scenario. When it's Wednesday and somebody asks you how many days till Wednesday, you will say 0 rather than 1, right? And when it's Wednesday and somebody asks you how many days until Thursday, you will say 1 rather than 2, right? Like this, the first element of the array is exactly contained in the memory location that array refers, which means 0 elements away. So it should be denoted as array of 0. Most programming languages have been designed this way. So index from 0 is pretty much inherent to the language. See you guys on the next video. Hey guys, welcome back. In this video, we are going to discuss about two-dimensional array. When we talk about two-dimensional array, all the features from the one-dimensional array applicable for two-dimensional array as well. The difference is, this is having 2 dimensions. To understand this, it's better to think of two-dimensional array as a matrix. A matrix can be thought of as a grid of numbers arranged in rows and columns, kind of like a bingo board. So we can access two-dimensional array by using row and column indexes. Let's take this array. This is one-dimensional array, right? Here, how you can access the element? Suppose you want to access 3. How you can access it? Array of index, which is 2. Since it's a single dimensional array, we can access the array like this. Then what about for two-dimensional array? First, I will represent two-dimensional array in diagram. So two-dimensional array will looks like this. These are the rows and these are the columns. Let's write the indexes for rows and columns. 0, 1, 2 and 0, 1 and 2. I hope you remember that array index always starts from 0. So here we can access each and every cell with corresponding row and column indexes. So this one is 0 of 0, means row 0 and column 0. This one is 0, 1, means row 0 and column 1. Like this. This is 0, 2 and this is 1, 0, means row 1 and column 0. And like this, other cells are okay. Now I will declare two-dimensional array in programmatic way. Int two-dimensional array a equal to this line of code is programmatic representation of this. Here
If you want to access 0, you can access through the row and column indexes, that is A of 0, 1. Like this, if you want to access 9 from this array, 9 will be presented in third row, third column, right? So we have to access it like A of 2, 2. For this two-dimensional array, what is the complexity to access the element? If you want to access the element, you can directly use the index of row and columns, that is A of 0, 0. If you want to access this element, you can access it by A of 2, 1, right? So its complexity is 1, that is O of 1. But this is not the case for adding the element in array. We have to travel from one position to another position to add the element in an array. So complexity for the add operation is similar to one-dimensional array, that is O of n. Deletion also like the same. We can't able to directly delete the element from this array. We have to travel again to find the element. So the deletion complexity is also O of n. Search operation is also like one-dimensional array. We have to travel one by one. So complexity will be O of n. Okay guys, see you on the next video. Hey guys, welcome back. In this video, we are going to discuss about linked list. Like array, linked list is the another way to store the data. So before we move to the linked list in detail, we first understand why linked list and what is the problem with array data structure. Alright. Okay, let's take this int I equal to 8. If you are defining a variable like this, compiler will assign 4 byte space in computer memory. Let's take an integer array. For example, if you are declaring an array like this, A of 4 equal to 1, 3, 8 and 12. This array contains 4 integer values. As we know that system allocate 4 into 4, which is 16 byte for this array. Let's take 1 will be stored here and 3 will be stored here and sequentially 8 and 12 stored in this location. If you want to add another integer value within this array, it is not possible, right? Because when you are defining array, system allocates memory for your array based on the size which is you have defined. In this case, system allocate 16 bytes. If we really want to add some more elements in this array, system should allocate corresponding memory for this integer array and shift the existing values to the new locations. Note that this shifting process is costly while we consider about complexity. This is what we did in array implementation video for inserting element in array. Here, the another problem is if we want to remove one element from array, we could not clean up the space for value, which is we wanted to delete the value since system allocated this much space for our integer array in memory while creating the array. And another thing is, assume that we are declaring array with size of 10. And we have added only 2 elements. See here, still we have some extra spaces. We define the array with 10 elements, but we have added only 2 elements in this array. In this case, 10 into 4, which is 40 bytes already allocated for this array. So system will not use this memory for other operations because it's reserved for this array. So how we can solve this problem? That's the reason we came for linked list. Now we will take this same list of integer values and store it in memory by using linked list. Assume that this is computer memory. Let's take this first element 1. If we try to add 1, it will store somewhere here. And for the second element 3, system will assign some other space in memory but not sequentially, somewhere here. Okay, similarly system assigns some location for 8 and 12 like this. So like arrays, linked list is a linear data structure. Unlike arrays, linked list elements are not stored at continuous location. The elements are linked using pointers. That means linked list uses some additional information while storing the actual data. That is called a reference or pointer, which means while storing the element, along with the element it stores address of the next element. We can call it as reference in Java and pointers in C language. So this one pointing to this and this one pointing to this element. Linked list uses node to store the data. Node is nothing but just type. So single element of list object or type contain two content within it. One is actual data and another one is node, which is pointing to the next element. Let me explain this in diagram. If we add first element in this list, in our case I am storing the value 1 here, and this second part of the node is initially pointing to null because at this stage we don't have next node to point to it. If we add second element in this list, that will be stored to this node and first node references pointing to second node, like this. Like this way, if we add third element, second element references pointing to third element. So like this way, third one pointing to fourth one. In linked list, there is only one head node. So when we declare linked list, we won't define which size. By this way, we can avoid the problem we are facing with an array. There are three types of linked lists are available: single linked list, double linked list, and circular linked list. We will discuss about this in few minutes. Hey guys, welcome back. Whatever we have discussed in last video, it's singly linked list, which means every node holding value and another node, which means reference of next node. So this is the node. This will hold the value and pointer or reference to the next node. Let's take, we are going to add 5 elements in singly linked list. Let's take 5, 8, 3, 1 and 2. Each and every elements stored in individual node and every node having the address of next node. So how we can represent this node type in programming? Let's take class node. As I said earlier, each and every node having two parts within it. One is actual data or value. Here we are going to store integer value. So int value. This is one of my attribute inside the node class. And second part is pointer or reference to the next node. Means basically it's node type. So node of next. Note that if we don't have any next element, node references pointing to null. Okay, let's add these elements in linked list. This is first node. It will hold value 5 and reference of next node. Anyways, initially it's pointing to null. And this is the second node and we are going to store h onto this node. Once we added second element, first node references pointing to this second node. Like this way, second node points to third node, which is holding the value 3, and third node pointing to fourth node, and fourth one will pointing to fifth one. So we can store 1 and 2 here, and this is last node references pointing to null. In this linked list, first node always be the head node. Always remember that first node always be the head node. If we want to search this element from the linked list, we have to travel from head node. In singly linked list, we can travel in forward direction only, not backward direction. If we are in third element, where you can travel next, obviously you have to travel to the next node, that is fourth node, right? In this node having the references of next node. So from here we don't know where we came from, which means we don't have address of the previous node. Okay, now we will see complexities for basic operations like access, inserting new element in linked list, and deleting the elements and search the elements from the linked list. If it tries to search the element in the linked list, we have to travel from the head node. For example, if we search element 3 in the list, first we have to check this is 3 or not. No, right? Then we have to move to the next node by helping of this reference. Is this 3? No. Again we have to move to the next element. Is this 3? Yes, we got it. So what is the complexity of search operation? It's O of n. So every time we wanted to search something from this list, we have to travel from the head node till we find the elements which is we are looking for. Assume that the elements we are looking for present in the first node. What will be the complexity for that? It's O of 1. But this is best case scenario. Whenever we talk about complexities, we have to go for worst case scenario. We have to consider worst case scenario only, right? So for the worst case scenario, search operation complexity will be O of n. So what about insertion? If we add new element as the first element of the linked list, we can directly add the element here and we can point the reference to this next node and we can make this node as the head node. That's it, right? So this complexity is O of 1. But this is not the case for all the time, right? We have to consider worst case scenario while finding the complexity. Let's assume that the element should be added in middle of the linked list. How to do that? Let's take this is new node. We are going to insert here. It have value and pointer. Pointer means it's referencing to next node. First we have to remove this reference and we have to point this reference to new node. And we have to point this new node reference to the next node. So we have to travel from head node and we have to move this location and new node should be added here. As part of insertion operation, we have to point the previous node references to this new node and this new node references should be point to next node. So complexity of insertion is O of n. Let's go for deletion. If we delete first element from the list, we can directly delete that and make this node as head node. That's it. But if you want to delete the element from the middle of the linked list, it's not simple as delete the first element from the linked list, right? Let's take, we want to delete third element from the linked list. We have to travel to this node from the head node and we should delete this node and remap these references from this node to this. So what about the complexity? Obviously O of n, because we have to travel from head node to delete the node from the linked list. And complexity for access operation is also O of n, because we have to travel from the head node to find the elements from the linked list, right? See you guys in the next video. Hey guys, welcome back. In this video we are going to discuss about doubly linked list. A singly linked list contains two parts within it, right? One is holding actual data and another part contains reference of next node. But a doubly linked list contains an extra pointer. Typically we can call it as previous pointer. Let's take this node. In singly linked list, we will store two informations, that is actual data and pointer to next node. So we can only travel to forward directions because we do have address of only next node. If we want to travel backward, we can't do that in singly linked list. That's the reason we come up with doubly linked list. In doubly linked list, every node will have three informations within it. One is actual data and previous node, which is reference or pointer to previous node, and next node, which is reference to next node. So let's take this. This is the first node of doubly linked list, which is having previous node. Since this is the first element, we don't have any previous node, right? So it will be null. And this is the value part. And this is the reference to next node. Initially, this also will be referencing to null. If we add second element in doubly linked list, this first node next references pointing to this new node, and this new node previous references will point to previous node, like this. If we add third element, second node next reference will pointing to third node and third node previous references pointing to second node. So how we can represent this node type in programming? Let's take class node. As I said, every node having three parts within it. One is actual data. Here we are going to store values. Let's assume we are going to store integer values here. It may be character or string, whatever. And second part is pointer or reference to previous node. So node of previous. And third part is pointer or reference to next node. So node next. If we consider complexities for basic operations like access, insert new element in linked list, or deleting elements in the linked list, and search the element from the doubly linked list, it's similar to singly linked list, which is complexity will be O of n for all the operations, because the way we used to implement the basic operations like add, delete, search or access, whatever it is, in singly linked list, the same way we should use in doubly linked list also. Still, to access or find the element in doubly linked list, we have to travel from first node till the element which is we are looking for. And for adding new element or deleting new element also same as singly linked list. We have to travel to the destination node and remap the references based on the operation whatever we are going to perform, like add or delete, whatever it is. So like singly linked list, all the operations complexity will be O of n for the doubly linked list. Only difference is doubly linked list contains some extra pointer to hold the previous node information. That's it. Okay guys, see you in the next video. Hey guys, welcome back. Let's take this doubly linked list. Now I'm going to store some elements in doubly linked list. Let's take the values 2, 5 and 3. Let's add this element in list. It's first node and it has three parts: exact value and two nodes to store next and previous node informations. Assume that this address is 100. Here I'm going to store our first element, it's 2. Fine. Here previous reference will be null, right? Because we don't have any previous node here. It's our first node in this list, and the next node will hold the address of next node. So what will be the address? Let's assume that this integer value requires 4 bytes and the next and previous node also requires 4 bytes each. So totally we need 12 bytes for one node, right? This node address is 100. Then the next node address will be 100 plus 12. So this node holds the address of next node, which is 12. And this is second node. It holds the value 5. And the previous node reference will be 100. And next node reference will be current node plus 12, which is 112 plus 12. So next node reference will be 124. Similarly, this third node will hold the elements 3 and previous reference will be 112. And this third node next reference will be pointing to null, because this is our last node in our doubly linked list, right? In ordinary doubly linked list requires space for 2 address fields to store addresses of previous node and next node. A memory efficient version of doubly linked list can be created using only one space for the address fields with every node. This memory efficient doubly linked list is called as XOR linked list, or memory efficient as the list uses bitwise XOR operations to save space for one address. In the XOR linked list, instead of storing actual memory addresses, every node stores the XOR of addresses of previous and next nodes. In this doubly linked list, we allocated separate memory to store the previous and next node. But the idea of XOR linked list is avoid using the separate memory for the previous node. So XOR linked list uses only one node to hold the previous and next node informations. So XOR linked list node having two parts within it. One is actual value and second part is XOR value of previous and next node. To understand this more clear, I will explain this with diagram. Let's take these are the nodes in XOR linked list. Take this 3 nodes. So here we are going to store 3 elements. Assume that the first node address is 100. In XOR linked list, every node will have 2 sections only. Here node size will be 4 plus 4, that is 8 bytes. So second node address will be 108 and third node address will be 116. Let's take, we are going to store these values 2, 5 and 3 in this list. Now the question is how this first node will hold the address of previous node and next node references, right? Actually, it will hold XOR value of previous node and next node references. For this first node, we don't have previous node. So this node will have bitwise XOR of 0 and next node address, that is 108, like this. And this second node will have the pointer as previous node address, that is 100 XOR, and next node address, that is 116. Similarly, this last node will have 108 XOR of 0 because we don't have next node here. So this is how we can implement memory efficient doubly linked list. See you guys on the next video. Hey guys, welcome back. Circular linked list is a list where all the nodes are connected to form a circle, which means there is no null at the end. Let's see this linked list. If you see the singly linked list and doubly linked list, last node reference will point to null, right? But in circular linked list, last node reference will point to first node, so that it will form a circle. Here you can start your iteration from anywhere you want, but in singly linked list or doubly linked list, you can start the iteration from the head node only, which means first node. We can form a circular linked list by using singly linked list as well as doubly linked list. If you want to travel clockwise from the linked list, you can use singly linked list. If you want to travel clockwise and anti-clockwise as well, you can use doubly linked list. It's up to your requirement. If you consider the complexities for the basic operations like access, insert new element in the linked list, or deleting the element, or search the element from circular linked list, it's similar to singly linked list and doubly linked list, which is complexity will be O of n for all the operations. Hey guys, welcome back. In this video, we are going to discuss about implementation approach for linked list. As we have already discussed, we are using node type to store the element in the linked list, right? Each and every node will have two parts within it. One is actual data and another part is reference or pointer to the next node. Actual data means whatever data we are going to store in the linked list, that specific type. Here I have created one node type which is having two attributes within it. One is actual data, which is int type. I'm going to store int values to this linked list. So I'm just using int type and reference. This will be another node. That's it. And it's having one constructor. So whenever I create object for this node class, it will expect one integer value. If I pass that integer value, it will be assigned to this variable, and next value will be null by default. Let's go for linked list class. Here I just created one method for insert element in the linked list, and I have created another method to delete the element from the linked list, and I have created this method to display what all elements we have it in the linked list. And this is my main method of this class. Whenever I execute this program execution will start from this method. Alright, when I execute this program, first this line will execute. Here I am just declaring one linked list. That's it. In the second line, I am just inserting one element to this linked list, which is 4. And next I am adding element 1, and I am adding 3, and I am adding 8. So totally I have added 4 elements to this linked list, and just printing that. So it will print 4, 1, 3 and 8. And next I am going to delete element 1 from this linked list, which is this element. After I am removing this element, I'm just printing this. Means it will print 4, 3 and 8. This is what we expected, right? Let's run this program and see what is happening. After inserting everything, I'm just printing all the elements, which is 4, 1, 3 and 8. This is what we expected. And next is deleting element 1 from this linked list. Deleting 1 from the linked list. 1, it's found, so it's deleted. After deleting this 1, right, we will have only 4, 3 and 8 from this linked list. Alright, let's run this program in debug mode so that we can understand what is happening in step by step. I'll just put some breakpoints here from the starting and what is happening in the insert method, right? To that I'll just put one breakpoint in insert method. Same thing we have to do it for delete method. That's it, right? Okay, let's run this program in debug mode. Whenever I execute this line, it will create one object for linked list class. It will not have any element by default within it, right? This is just having 0 elements. I'm going for next line. In this line, we are going to insert element 4 to this linked list. Here in this insert method, we are just passing empty list, which is we have created earlier, and I'm passing 4. Basically, we wanted to add this element 4 to this linked list. If I click next line, it will go to insert method. Here we are just sending empty list and data will be 4. Here I'm just creating one node with the type of data, which is 4. Actually here the expectation is I'll just draw that in nodes. Whenever program executes this line, what will happen, right? It will create one node with value of 4, right? This is what will happen in this line. Here we are just assigning null to the next. This will be pointing to null, right? Now we know that every linked list will have only one head node, which is first node will be the head node, right? So since this is the first element in our linked list, we should represent this node as the head node, right? For that I'm just checking this list already having any head node. If it is null, which means it doesn't have any head node, I'm just adding this node as the head node, right? When I'm executing this line, this head will be null, so it will go inside this if block. So whatever new node we are creating, this node, basically this node going to be treated as a head node. That's it. Just we are returning this node as the first element. So after executing this line, this first node will be the head node. That's it. We have added the first line, right? We are going for the second line now. So now we have this data in our linked list. Now we are going to insert element 1 to this linked list. Basically what we have to do, right? We have to create one node. It should have 1. Now another thing we have to do is we have to point our previous node reference to this current node. This is what we have to do, right? Let's see what is happening in program. In this list already we have one element, that is head node, which is having data 4, and next reference will be pointing to null, and this is what our data we are sending 1. Okay, now we have created one more node, which is this node, which is having data of 1 and next will be null. Okay, now here this condition will be false because in this linked list already we have the head element, right? So this will not be a null. In this head we will have some information, right? So this is not null, so this will not be true anymore. So it will skip this if block. It will go to else part of this if. Here if head node is there, we are just assigning this head node to this new variable called node. So this last node will have the head node information. This head node having any next value, which means this head node having any next. In this situation we don't have any next, right? Means we haven't point any node to this node, so this will be false. It will skip and it will go to here. Our new node will be assigned to this next, which means this new node will be assigned to this next. Got it? Now we have two elements. First element is our head element, which is holding 4, and the first node next will be pointing to this second node, which is holding value 1, and this second node reference of next will be pointing to null. Clear? Right. We have added two elements in the linked list, so this is what we have. I'll just clear it. Now we are going to add third element to this linked list, which is 3. So already we have two elements. This is head node. This head node reference will point to this one. Now this one will be pointing to null as of now. After adding this 3, this one node next reference will point to this third node. Let's see that. Here we have created the node with 3 and head node is not null, so it will go else block. Again head node we are assigning to one node which is having data 4 and next node pointing to another node which is having data 1. For this node having next reference as null. This is what we can say here, right? Now head dot next, which is head node dot next. Is it not null? Yes, it's not null, so it will go inside. Now our last node, it's basically head node dot next, which means it refer this node. So now this last node will be our second element, right? Again this while loop will execute. Now this second element will have next no, this will be false, so it will skip, and this last node dot next means this second node dot next, which is equal to new node, which is 3. Clear? We inserted 3 elements to this linked list. Like the same way we added 8. This is having 8 and next reference will be null. We have head node, so it will skip here, so head node will be assigned here. Now head node having next, so it will go inside here. Next node next reference will be second element, that will be assigned to last node. Again last node will have next reference, which is third element, so again this will be true, it will go inside. Now so this third element next reference will be assigned to last node. So basically whatever element we have added lastly, that is having null reference, right? So this node dot next will be null for this next iteration. We'll see that this is null, so it will false, it will go here, and this new node will be added here as a next, so this will be added here as the next. We have added all the 4 elements. I'm just printing that element. If you see here, it will print all the 4 values 413h 413h. Now we'll delete element 1, this element, from this list. So basically what we have to do, right, if we want to remove this element, we'll just point this reference to third node. This is what basically we have to do, right? Let's do that in program. I'm just calling this delete by key method. I'm just pausing whatever list we have and pausing 1, means which element I wanted to delete, that element I am sending as the second parameter to this method. See here, we need to maintain current node and previous node. You know why we need to maintain previous node? Suppose if you wanted to delete this node, right, previous node reference should point to next node, right? So if I am here, this node dot next means it will refer this one, but we want previous node to point new node, right? So that we need to maintain previous node as well. So I'm just declaring 2 variables, current node and previous node. I'm just reverting this. So we are maintaining current node and previous node. But here, right, we are going to delete this element 1, right? First we need to find this element, then only we can able to delete it, right? First we have to find. For the search operation, from where we have to start our finding? From the head node, right? Because that is our first node. From the head node we have to travel to into this linked list, then we have to find the element and we have to delete it. So I'm just assigning head node to the current node, previous node will be null. I'm just checking whether our first node is whatever we are looking for, means current node dot data is equal to key. If current node is 1, then we can directly delete this node and make second node as the head node. This is what I'm doing here. Current node dot data, which is 4, is equal to 1, no. So basically we don't want to delete head node here. Suppose here we are passing 4, then we wanted to delete first node, right? So here it will go inside list.head equal to current node.next, means whatever node we have as a second, that we are making as a head node, that's it. But here this is not the case, right? So this will not execute. I'm just going here, current node dot data is not equal to key, which means in the head node value is not 1, right? Then it will go inside whatever current node we have, that I will assign it to previous node, and here I'm just assigning next node as the current node, that's it. So again I'm checking whether this current node key is not equal to key. Actually it's false, right? Because whatever node we have currently is, that is 1. Our key is also 1. 1 is not equal to 1 is false, so it will skip. So it will go this if block. Now our current node is 1. Current node dot next means it's referring 3. Our previous node will be head node, means first node. So here what we have to do, right? From the previous node dot next, we have to refer next node, which is current node dot next node. So current node dot next means it will refer this one, and previous dot next means previous dot next means this reference will be pointed to third one. Means logically we are deleting this element from this linked list. That's it. So here just we are remapping the reference. So logically it will be a delete the element 1. I'm just printing key 1 found and deleted. That's it. So basically it's deleted from this linked list. So this is the case to check whatever element I'm trying to delete which is not available in the linked list, which means I have to display whatever key I'm looking for, it's not found to delete, right? If current node is null, means the last node reference will be null. In this case we already look for all the data, right? So whenever this will occur, right, which means basically we can't able to find the record whatever we are looking for. In that case we have to display not found. So anyway, this is not the case for this scenario. I'll just skip this. That's it. So finally I'm just printing all the elements. It should print 4, 3 and each. That's it. Okay guys, see you on the next lecture. Hey guys, welcome back. Whatever we have discussed in linked list implementation, it's singly linked list, right? Because our node type will have only next reference. Basically it will have only next node information. Now I would suggest you to implement doubly linked list and circular linked list by your own. So in singly linked list, whatever we have implemented, it's basic idea to implement linked list. But for the doubly linked list and circular linked list, you can apply the same logic with slight modification into that. I will give you the idea to implement doubly linked list and circular linked list so that you can implement the same by your own. If you do it yourself, you can get much more confident on programming logic while creating your own algorithms. Okay, let's start with doubly linked list. If we take this node type for singly linked list, it's having data part and node type to point next node, right? But for the doubly linked list, we should have previous node reference as well. So this is the first thing you should do. So create another variable to hold previous node information. In doubly linked list, whenever we add second node, we will point first node reference to next node, like singly linked list. And at the same time, we have to create a reference from second node to first node as well. I mean, we need to point second node previous reference to first node. Similarly, if we add third node in linked list, while assigning second node next reference to third node, we have to assign third node previous into second node, means previous node. If you see here, new node dot previous equal to last node, so that you can assign new node previous reference pointing to last node, which is previous node. That's it. Let's try this. And next is circular linked list. It's very simple to implement. If you see singly linked list or doubly linked list, last node next reference will point into null, right? But in circular linked list, we will point last node next reference to head node. That's it. To create this circular linked list, you can use singly linked list or doubly linked list. It's your wish. Let's try this. Hope you will get it completed. If you have any issues or doubts while implementing, feel free, leave your comments in QA section. I'm here to help you. All the best guys. See you on the next video. Hey guys, welcome back. Till now we have discussed about array and linked list and various form of array and linked list. But when we should prefer linked list over array and when we should prefer array over linked list, let's discuss this in this video. Linked lists are preferable over the array when you need constant time insertion or deletion from the list, such as in real-time computing where time predictability is absolutely critical and you don't know how many items will be there in the list. In array, you may need to reallocate and copy memory if the array size grows too big and you don't need random access to any element and you want to insert the item in middle of the list. These are the places we can prefer linked list over arrays. Arrays are preferable when you need indexed or random access to elements. You know the number of elements in the array ahead of time so that you can allocate the correct amount of memory for the array. You need speed when iterating through all the elements in sequence. You can use pointer math on the array to access each element, whereas you need to look up the node based on the pointer for each element in the linked list, which may result in page faults, which may result in performance hit. In this case, array is a good choice. Memory in concern. Filled array take up less memory than linked list. Each element in the array is just a data, right? But in linked list, each node having some additional information, right? So comparatively, linked list need more memory than array. So if you are concerned with memory, you should go for array. Hey guys, welcome back. Here we are going to discuss about a new data structure called hash table, also known pretty commonly as a hash map. It's probably most used and important data structure in all of the computer science. Hash table is a data structure that allows us to fast retrieval no matter how much data it is. Hash table is used to store key value pair. If we store the value in the array, it will store based on the index, right? We don't have any meaning for that index. It's just a numeric values. Let's take an array. This array having countries. So for example, it's United States, and it's United Kingdom, India, China, Italy, and Sweden. If you want to access Italy from this array, we have to go over one by one within this array, right? If the array size is too large, it will take a long time to find the element. Am I right? Think about, you know the index of the element which is you wanted to access. Means you know in which index Italy is stored. In such a case, it's very easy to access it, right? Regardless of the size of the array or its index position of the elements. But how do you know which index of the array contains the value you are looking for? So the idea is, if the index is calculated based on the value itself, then we know the index position of the value which is we are looking for, right? Means the index number somewhere related to the data. This is the idea of a hash table. Let's repopulate this array. Let's take the United States. And we will send this string to hash function and get a unique hash code for that United States and convert the hash code into index and store it into the corresponding position. So for example, hash function returns 4 for United States. So we can store the United States in index position 4. We will talk more about the hash function in the next video. For now, you just understand that the hash function is a function will accept a string as an input and it will produce the hash code for that particular string as an output. This string may be an object or number or whatever it is. Okay, let's take United Kingdom. If we send this into hash function, it's returning 2. So store the United Kingdom in index position 2 of this array. Like that, for India it's returning 3. Means it will be stored index position 3. Later, if you want to access India, we can send India to the same hash function and get the index value and look the value at that index position. This is how hash table will work. Here, rather than storing individual value, the hash table is often used to store key value pairs. For example, here country name would be the key, which will be used to calculate the index. The corresponding value for the country is country code. For this reason, the hash table comes up with key value pairs. In fact, if an object-oriented approach was taken, each country would be an instance of the class and the key would be any one of the attributes. It would be nice, instead of using the indices to access the country, we would use more user-readable keys in hash table. If we call this array is countries, countries of India is better than countries of 3. On top of that, the keys in the hash table are not ordered. So in array, of course, the index or indices starts from 0 and they go up to some numbers. And another thing is, the hash table is really faster than array while adding new elements or finding some elements. Most of the languages have some sort of hash table structures. For example, Java will have hash map, hash table, concurrent hash map. Like that, in C# we have hash table, dictionary, string dictionary. Like that same way in Python it's dict. In Ruby it's hash. In the next video we will see the details about hash functions. See you guys on the next video. Hey guys, welcome back. Here we will discuss more about hashing algorithms, or basically we can call it as hash functions. In the last example, we are sending the key to the hash function. In that case, we send United States, and this function processes the string and return back the index. Based on the index, we are storing the value for that country in the array. So hash function is a calculation applied on the key, which may very large number or very long string, to transform it, which is a relatively small index number that corresponds to a position in the hash table. So what is happening inside this hash function? First, it will find the hash code for that particular number or string, which is we are passing to the hash function, and then based on the hash code, it's construct the index position based on the array size. Finally, it will return the index as the output. This process is called as hashing. I am repeating it again. First, it will find the hash code for that particular number or string, and then based on the hash code, it's construct the index position based on the array size, and finally it will return the index as the output. So in order to implement key, we need a way to convert keys to valid array indices. A function that performs this task is a hash function or hashing algorithm. Okay, let's implement our own hash function. First of all, we have to define the return type. We are expecting index position, right? So we will return int type value from this method, and I can call this method name as hash, and I am accepting string value as input, but in real time it may be any type. Let's take the country Italy. To find the index position for Italy, we send Italy to this hash function. The first thing is we have to find the hash code value for Italy. In order to do that, I am just converting each and every character of the string into its ASCII code values and adding all the characters ASCII code values together to get hash code for that string. If you see the ASCII code table, the ASCII value for capital I is 73, plus ASCII value for T is 116, plus ASCII value for A is 97, plus ASCII value for L 108, plus ASCII value for Y is 121. So the total is 515. This is the hash code for Italy. So the first step is over. We found the hash code for Italy, but we need an index position to store Italy, right? So from this hash code, we have to construct an index position. So my formula to do that is hash code modulo size of the array. Here the total element of the array is 6. So the hash code for Italy is 515 modulo 6, which is equal to 5. We are just returning this 5 as the output from this hash function. So this key Italy will be stored its code in index position 5. This is an algorithm to find the hash code. and it's not necessarily have the same logic to find the hash code for the key. There are lots of hash algorithms are available to choose from, some more appropriate than others depending on the nature of your data, or you can implement on your own way. But when you implement a hash function on your own, you have to follow some rules. The first rule is your hash function should be fast. This is an example for how you should not write your hash function. If you see here, there is more loop going on, right? Which is unnecessary. Your hash function should be simple enough to find the hash code. And the second rule is your hash function should always return the same value for the particular key. So for example, for Italy, it's returning 515, right? If again we call this hash function to find the hash code for Italy, it should return the same hash code. So this is how you should not write your hash function. If you see here, this function randomly generates a number between 1 to 100. Each time it will give the different result for the same key, right? So your hash function should not be like this. See you guys on the next video. Hey guys, welcome back. So far we have seen how to load up hash table with data that very conveniently without causing any problems. Sometimes if we apply hash function to two different keys, it generates the same index number for both the keys, but both the elements can't go to the same place. This is known as collisions. When we have hash function and when we have a lot of data, it's very common that we will have some collision. Even we work with large array and great hash function, we will still have some collisions. So how to handle collisions? There are many ways to handle this, but I'm going to talk about two ways to handle this collision. One is separate chaining. It's also known as direct chaining. And the second one is open addressing. Okay, let's start with separate chaining. With the separate chaining, at each index in our array, we will store the value using a more sophisticated data structure, something like another array or linked list. Let's take this array and load up some data. Let's add string AB, both are caps. If we call as function by passing AB, we will get index 1. So it will be stored in index position 1. Let's add another string into the as table. Let's add BB. So if we send this string into as function, we will get index 4. So it will be stored here. Let's add another string into the as table. Let's add PR. If we send this string to the hash function, we will get index 2. So it will be stored here. Let's add CA. If we call as function with this key, we will get index 4. If you see here, already we have some data in index position 4. So no rooms available for CA. So in this case, instead of directly adding the elements into the index position, we can have another data structure in each index position. We can use another array data structure inside every index position on original array, or we can use linked list data structure. Okay, we will use linked list to store our data inside our original array. So in index position 4, we will store one linked list object. We already know that every linked list node contains two parts within it, that is actual data and reference to the next node. So this BB added as the first element of the linked list, and initially this reference pointing to null. When we insert another value with the same key, means in this case CA, we can add it as the next element of the linked list. By this way, we can add CA as well in index position 4. Let's add another element into the hash table. Say for example PQ. So for this, hash function produce index as 1. Here index 1 already occupied, right? We already have AB in this position. So AB will be the first element of the linked list, and the first node next reference pointing to another node which is holding PQ. Hope you are clear. This technique to handle the collision is separate chaining. Let's move on to the another way to handle the collision. It's open addressing. Open addressing means when we don't have any space to store the element, we can store it in the next available position. Means every address is open for every item. Let's clear everything. Let's add same elements again, but this time when collision occurs, we will use open addressing technique to handle the collision. Let's add AB. So hash function returns index position 1, so it will be stored in index position 1. Let's add second element, BB. The hash function will produce 4 as the index, so it will be stored here. And the third element is PR. Let's add this. Hash function returns 2 as the index, so it will be added here. And the next element is CA. For this element, hash function will produce 4 as the index. So here collision happens, right? In this case, this CA will be stored in the next available space. It will check next available free space in linear way. Here it's index 4. So it will check next index, which is 5. If index 5 is free, then it will be stored in index position 5. If index 5 is not free, then it will check for next index position, which is 6, something like that. But in this case, our array size is 5. So total index is up to index 4, right? So it will start looking the free space from beginning of the array. So it will check the index position 0. Here index 0 position is free, right? So it will be stored here. So CA will be stored here. And the next element is PQ. For this PQ, hash function will return index position 1. Here in index position 1, we have already data. So it will check next available free position. So it will check next position, which is index 2. Index 2 also having some data. So it will move on to the next position, which is index 3. Here index position 3 will be free, right? So this PQ will be stored in index position 3. Resolving the collision by placing an item somewhere other than its calculated location or address is called as open addressing, because every location is open for any item. Open addressing can use a variety of techniques to decide where to place an item that does not go where it should. This particular open address technique is called as linear probing. If calculated address is occupied, then the linear search is used to find the next available space. If linear probing gets end of the array and it still can't find the free space, it might start looking from beginning of the array. That's what we did in this example. See you guys on the next video.
Hey guys, congratulations. You have completed second unit of this course. This video is quick wrap up which you learned in this unit. First, we have covered array and linked list data structure. Both array and linked list comes with different flavors. We have seen two dimensions of array. One is one-dimensional array and another one is two-dimensional array. So in one-dimensional array, we can store sequence of data and it will have row level dimension. So in this one-dimensional array, we are having some data. If we represent this array as A, we can access the element by using index. For example, if you want to access first element from this array, we can access it like A of 0. Remember that array index always starts with 0. So if you want to access third element from this array, we can access it like A of 2. For one-dimensional array, complexity of accessing data is O of 1 and insertion and deletion complexity will be O of n. And to find the element from the array, complexity will be again O of n, because we have to travel from first element till the element we are looking for. And next we have discussed about two-dimensional array. When we talk about two-dimensional array, all the features from the one-dimensional array applicable for two-dimensional array as well. The difference is this array having two dimensions. We can access two-dimensional array using row and column index. Let's see this two-dimensional array. If you see here, these are the rows and these are the columns of the array. If we represent this two-dimensional array as A, we can access this specific element by using row and column index, that is A of row index and column index. If you want to access element 6 from this array, we can access like A of 0 and 0, means 0th row and 0th column. And if we need 5, we can access it like A of 2 and 2. And complexity for the operations like access, adding the element and deleting the element are like same as one-dimensional array, means access complexity will be O of 1
and addition and deletion complexity will be O of n. And next we have seen linked list and its different flavor. Like array, linked list is the another way to store the data. Whenever we declare array in our program, we have to define the size as well. So based on the size of the array, system will allocate memory for that. Whether we are using it or not, but system will allocate the memory for that array based on the size we have defined. So this might be a problem, right? To avoid this problem, we came for linked list. While implementing linked list, we won't define size, but remember that access wise still array is the good option, because to access the element in the array, complexity will be O of 1, but in linked list it's O of n. And linked list comes with 3 different flavors, that is singly linked list, doubly linked list and circular linked list. We will represent the linked list with the type node. In singly linked list, node type will have only next reference. Basically, it will have only next node information. But in doubly linked list, node type will have next and previous references. So in doubly linked list, we can travel forward and backward direction, while singly linked list travel only forward direction. And next we have discussed about circular linked list. In singly linked list or doubly linked list, last node next reference will point into null, right? But in the circular linked list, we will point last node next reference to point head node. That's it. To create circular linked list, we can use singly linked list or doubly linked list.
And next we have seen hash table. Hash table is a data structure used to store a key value pair. In a hash table, data is stored in an array format where each data value is its own unique index value. Access of data becomes very fast if we know the index of the data. That is the idea of hash table. Hash table allows us to fast retrieval no matter how much data it is. Hash table uses an array as a storage medium and uses hashing technique to generate an index where an element to be inserted. Hashing is a technique used in hash table to convert the range of key values into range of indexes of an array that is used to uniquely identify a specific object from a group of similar objects. We are going to use modulo operator to get a range of key values. And finally we have seen collisions. Sometimes if you apply a hash function to 2 different keys, it may generate the same index number for both the keys, but both the elements can't go into the same place, right? That is known as collision. And we have seen 2 different ways to handle the collision. One is separate chaining and another one is open addressing. That's all about we have discussed in this unit. Hope you are clear on the topic which we have covered in this unit. If you have any questions, feel free leave a comment in Q&A section. I will get it clarified that. See you guys on the next unit. Hey guys, welcome to the new unit of this course. In this unit, we are going to talk about stack and queue data structure in detail. Let's start with stack data structure. Stack is a simple data structure and it's another option to store the data, and stack is somewhat similar to linked list. In a stack, the order in which data arrives is important. Let's say for example, how we are handling the plates in cafeteria. It's a good example for the stack. The plates are added to the stack as they are cleaned and they are placed on the top, right? When a plate is required, it is taken from the top of the stack, which means first plate placed on the stack is the last one to be used. Am I right? Think about you're working in a team and your boss or your lead assigns some task to you. So you have started working on that. While you are doing that task, he called you again and says that, hey, can you take up this task and complete this as soon as possible because it's very high priority. Now what you will do? You will push the current working task to pending tray and start working on new high priority task, right? Okay, now while you are doing this new task, you are getting some call on your mobile, meaning that this is higher priority than your current task, right? So again you have to push that new task to the pending tray and attend the phone call. Once you are done with the phone call, you will pop up the priority task and you will work on that, right? This is the way stack will work. So coming to technical point of view, stack is a data structure to store the data like linked list and array. In the stack, the elements which is placed last is accessed first. Okay, let's take some elements and we will add those elements into the stack. Imagine the stack looks like this. Let's push value 5 to the stack. So it will be stored here, meaning adding 5 into the stack. It will be added here. Now this is the top element of this stack.
and let's add 2 into the stack. It will be added here. Now this is the top element of the stack. Now add 7. It will be added here. Now this 7 will be top element of this stack. Always remember that stack operations always affects only top of the stack, which means adding new element or removing element from the stack will perform on top of the stack. If you want to add another element into this stack, it will be added to top of the stack. If you want to remove the element from the stack, it will be removed from this top element only. That's why stack is always called as limited access data structure. Let's add 2 more elements to this stack. At 9, it will be added here, and this element will be the top element now. And add 1. It will be added here, and now top element is 1. Okay, now we will try to remove the elements from stack. If we try to remove the element from the stack, always top elements will be removed. In this case, 1 will be removed from the stack, and now top element will be 9. If again we remove the element from the stack, this 9 will be removed because 9 is the top element now. Think about if you want to remove this element 2. If so, you have to remove this element first. Now this will be the top element. Then only we can able to remove this element 2. This feature makes it last in first out or first in last out data structure, which means the element which is coming in last, that will be going out first, or the element which is coming in first, that will be going out last. So here the element which is inserted last is accessed first. In the stack terminology, adding operation is called as push operation and removal operation is called as pop operation. Okay guys, see you on the next video. Hey guys, welcome back. When we use stack data structure to store the element, we can do the basic operations like inserting element into the stack and remove the element from the stack. It's basically push and pop. These are the main operations in the stack. As discussed in last video, stack follows first in last out or last in first out structure, and it will perform these main operations on the elements which is present in the top of the stack. Try to pop out an empty stack is called as underflow, and trying to push an element in the full stack is called as overflow. Generally, we treat them as exceptions. For example, let's take this stack. Here we don't have any element in this stack, right? Here we can push the element in the stack, but it's not possible to pop out the element from the empty stack. If we tries to pop out element from the empty stack, it will give exception, and this is called underflow. Exception means attempting the execution of an operation sometimes cause an error condition. That's called exception. Like the same way, we can't able to push the element in the stack when stack is full. This is called overflow. For instance, this stack size is 5. I'm going to pushing elements into it. I'm pushing A, and then B, then C, then D, and finally E. Here he will be the top element of the stack. If you try to push the element F, it will give an exception because stack is already full, right? Other than this main operation, we have some additional supporting operations. For example, just take top. Top operation returns the last inserted element from the stack. In this case, it will return element E. And next is size operation. Size operation returns the number of elements which is stored in this stack. If I apply size operation onto this stack, it will return 5 because here we have totally 5 elements. And next operation is empty stack. This operation indicates that whether any elements are stored in this stack or not. So if I apply empty stack operation onto this stack, it will return false because this stack is not empty, right? And next operation is full stack operation. It indicates whether the stack is full or not. If I apply full stack operation onto this stack, it will return true because in this stack we can able to push 5 elements and we have already did that. Now this stack will be full, so it will return true. So what is the complexity of the stack operations? In any collection, we have considered 2 complexities for the operations like insert, delete, accessing the element and searching the element. As we discussed earlier, when we pushing the element into the stack, it will add the element only in top of the stack. So complexity for push will be 1, that is O of 1. Similarly, if you want to pop the element from the stack, always it will be top element from the stack. So complexity for the pop also will be 1, that is O of 1. Next operation is search. When we search the element from the stack, we have to travel from the first element. In the stack, if you want to search element C, we have to travel from first element. So complexity will be n times, that is O of n. And finally, access the element. To access the element, we have to travel from first element. So complexity will be n times, that is O of n. See you guys on the next video. Hey guys, welcome back. Now we are going to see some real world application for stack data structure. Consider I am just typing some content in text editor. While I am doing that, I just deleted some text by mistake and then I realized. So I revert back the changes what I did. To revert the changes, I just press undo input key so that we can see lost deleted content. So how it's happening? Just imagine whatever changes we are doing in the text editor, that will be pushed to stack. So if we do undo, it will pop up the lost changes. Let's consider another example. I am searching some topic in Google, and once I click the enter, it will show the search result. Then I will click some other link in it to go further. Basically it's a new URL and it will keep going on. At some point I want to go back to the link which is I have visited earlier. I will click back button here. So that I just click back button to go back. When I click go button, it will show the page which I visited lastly. Similarly, if I keep on pressing back button, it will show the last visited page from the current page. Just imagine whatever URL we are navigating, it's stored in the stack. So the last page which is I have visited will be on the top, and if I click go back button, the last page on the stack will be removed and it will be show the one before the last. Like this, where and all you need to fetch the data which is added lastly, there and all we have to use stack data structures to store your data. You just take basic idea behind this example. That's all for this video. See you guys on the next video. Hey guys, welcome back. In this video, we are going to implement stack. We can implement the stack by using linked list as well as array. In this video, we are going to start with stack implementation by using linked list. Before I move to stack implementation, I just recall how we have implemented linked list. So whenever we add any new element into the linked list, that will be added as a node type. Say for example, this is my first node. Here I am storing element 2. Whenever we add first element, this element will be the head node, right? And this head node next reference will point to null. Since here we don't have any node, this will point to null as of now. I'm just adding one more element into this linked list. Say for example, it's 3. Now my first node next reference will point to my second node, and second node next reference will point to null because here I don't have any next node to point to that. And I'm adding one more element which is 4, and my second node next reference will point to my third node, and third node next reference will point to null. That's it. If you see here, whatever element we have added newly, that will be the last element of the linked list. So I just added 2 as a first element, that will be head node. Inside the head node next reference will have another node which is having 3, and inside this second node next reference will have another node that is holding value 4. If I want to delete the element which is I have added lastly, I have to travel from my head node. From here, by using next reference, I have to travel to second node. From here I have next reference, by using that I have to travel to third node, then I have to delete this node. Hope you remember that stack is first in last out, or we can say like last in first out, which means whatever element added lastly, that has to be come out first. Means whenever we delete the element from the stack, by default whatever element we have added lastly, that has to be deleted. So think about, if we implement the stack by using the same way, what will happen, right? This is the element we added lastly, right? So every time whenever we pop the element from the stack, we have to travel from head node
till the last node. Then we have to delete this. So instead of that, what we can do, right, whenever we add new element into the linked list, we can add that new element as a head node. For example, see, this is my first node. Here I am adding element which is 2. It will be pointing to null. If I had second element 3, instead of adding this as a next element, I'll just add that as a head node 3, and this will point to this one. Now this will be the head node. Now I'm going to add one more element, that is 4. I'm just pointing my next to head, and I'm changing my head to this node. This is the element we added lastly. If I want to delete the element from this tag, I can directly delete this head node. That's it, right? Here we have other elements. Again, if I want to pop the element from this tag, this will be deleted. So this is what the basic idea of implementation of this stack by using linked list. So this is what I have implemented stack implementation by using linked list. First, I will run this program and I'll show you that what is happening in my program. See, these are the elements I have added, 1, 6 and 4. After that, I just removed one element from the stack, which is 1. After I remove that, these are the elements are there in my linked list. If you see my class, here I just have one first node, which is head node. By default it's null, and I have 3 methods. One is for pushing the data into stack, delete the data from the stack, which is pop method. This is my utility method to print to see what all elements I have it in my stack. And this is my main method. Whenever I execute the program execution will start from my main method. Here I am just pushing element 4 and then element 6 and then element 1. After I print this, I am just removing element from the stack. Obviously whatever elements we added lastly, that has to be deleted, right? Here we have added element 1 as the last element, so it will be deleted. After deleting this, I am just printing the element from the stack. I can expect 6 and 4 should have my stack. That's it. Now I am going to run this program in debug mode so that you can understand what is happening in step by step. I'll just put one breakpoint in my main method and in my push method and in my pop method. So before I debug this, I just draw this object structure so that you can easily understand. Now this is one object I have declared in my stack linked list class, which is initially referring to null. Just imagine that this is my first object. Okay, fine. Now I'm going to run my program in debug mode. See, here I'm just pushing element 4 into stack. Here we are going to create one node with data of 4. So I'm just draw it here. This is the node we are creating in this line, which is holding value 4. If you see here, this is the node, this is having data 4 and next node will be null. Now after executing this line, our node looks like this and next reference will be null. Here we are assigning first into next reference. By default we have first as null, right? So it will be null now. So after executing this second line, our node will looks like this. And the third line, we are just assigning whatever node we have created, that node into first, which is this node. So now what we'll have in our first object, it's having one node with the data of 4 and it's pointing to null, right? Now we have added one element into the stack, and this is my second element. In this line we are going to add one more element into the stack, which is 6. So again it's going here. Here we are just creating one node with the data of 6. I'll just draw it here. Which is 6. In the next line we have assigned our first node into new node next. This is our new node. New node next will be first node, which is this one, that is this node. So I'm just pointing that into here. Got it? And lastly, we are updating our first node with new node. New node means here 6. Here I am just updating our first node with new node, which is 6. That's it. We have added second element in our stack. And finally I am going to push one more element into the stack, which is 1. When I am doing that, this is the new node we are creating, which is holding the value 1. I'll just draw it here. 1, and new node next reference will be first node. Here we have this as the first node, right? So it will be pointing to this. And finally we are making this new node as first node. So it will have 1 now. So this is our first node now. That's it. In this line I'm just printing all the elements which is we have it in the stack. We can expect 1, 6 and 4. Alright, now we are going to pop the element from the stack. Whenever we execute pop, whatever element we have added lastly, that has to be deleted. Here we added element 1 as the last element, so it has to be deleted. Okay, now I'm going to next line. It's going for pop method. I'm just assigning whatever value we have it in the first into temp, which is node which is having 1. This is the first element now. This is the first node now. It will be assigned to temp node. And the next line, first dot next, which is first dot next is equal to first, means this node. We are making this node as first node. That's it. If we print that, it will start from first node, right? So obviously 6 and then 4. That's it. This is how we can implement this stack by using linked list. Hey guys, welcome back. In this video we are going to discuss about stack implementation by using array. This is what I have implemented stack by using array. In this class I have one push method, I have pop method, and just one utility method to display whatever elements we have it in the stack, and this is the main method. Whenever we execute the program, flow will start from here. If you see here, I just declared one variable called top to track the top element of the stack, and I have declared one array A, and it should have maximum 100 element, and initially I'll declare top value as -1. If you see this push method, before I push any element into the stack, I just check whether the stack is already full or not. Top is greater than or equal to max -1, which is 99, which means we already have 100 elements into the stack. We can't able to push any new element, right? So we have to show message like stack overflow. It's basically overflow exception. Like that same way, during the pop, if we don't have any element, which is top equal to -1, if we don't have any element in the stack, we can't able to pop, right? So in that case we have to display underflow exception. Okay, let's run this program and see what is happening. I just pushed one element 1, and second element 2, and third element 3. Finally I am printing all the elements, which is 1, 2 and 3, and I try to remove one element from the stack. Obviously here we have added 3 as the last element, so 3 will be removed from the stack. After removing this element from the stack, we are just printing existing element from the stack. So here we have 1 and 2. So after removing 3, we have only 1 and 2 from the stack. Now we will go through this program line by line. I just created one object for the class to access my push and pop methods, and just push element 1 into the array. If you go here, we are just checking whether our stack is full or not. If it is not full, we can able to add it, right? Obviously this will be false for the first time because top will be -1. So -1 is greater than or equal to 99, which is false, right? So it will go else block. Here a of plus top value is initially -1, plus top means it's 0, so a of 0 equal to element. So whatever element we are sending here, which is 1, will be stored into a of 0, means first element of the array, and we are just printing that element, and we are trying to push second element into the stack, which is 2. If I send it here, top will be 0, 0 is greater than or equal to 99, again it's false, it will come else block. Here a of top will be 0, plus 0 means 1, a of 1 equal to second element. So after executing this, first element of the array will be 1 and second element of the array will be 2, and we are pushing third element. Again this will be false, it will come to else block. Here a of plus plus 1, which is true. A of 2 equal to element, that is 3. So after executing this, first element will be 1, second element will be 2, third element will be 3 in the stack. That's it. I'm just printing all the elements what are all available in the stack. It will print 1, 2 and 3. After that, I just call pop method from the stack. Whenever we execute this pop method, we expect last element should be removed, right? So here we added element 3 as the last element, so it has to be removed. When I call this pop method, we are just checking whether this stack is empty or not. Since here we have some elements, this will not be -1, so this will be false. It will go to else block. Here a of top minus minus, currently top will be 2, so a of 2 will be element 3, so it will return value 3. It will be stored in X and we are returning that value. Just we are printing whatever element we have deleted. So after executing this line, top will be 2 minus minus, which is 1. So after executing this line, top will be 1. So when we print the whatever elements we have it in the stack, right, it will print from 0, 1, that is 1 and 2 only. So finally we will get 1 and 2. This is what we can implement stack by using array data structure. See you guys in the next video. Hey guys, welcome back. Queue is the another data structure to store the data, and it's similar to linked list and queue. In a queue, the order is which data arrives is important. Let's say for example, a queue is a line of people or things waiting to be served in sequential order, starting at the beginning of the line or sequence. Queue is a linear structure which follows a particular order in which the operations are performed. The order is first in, first out. Think about you are standing in a queue to get a train ticket. Imagine that you are the first person entered in the queue. Obviously, you will get ticket first. You are the first person will come out from the queue, right? Similar way, queue also will work. Element which is added first will come out first, or I can say in different way, last element comes last from the queue. It's called first in, first out, or last in, last out. Okay, let's take some elements and we will add those elements into the queue. Imagine the queue looks like this. For insertion and deletion, we have special name in stack, right? That is push and pop. Pushing the element means inserting the element into the stack. Pop the element means delete the element from the stack. Similarly, in queue, we have special name for inserting element and deleting the element from the queue. That is enqueue and dequeue. Enqueue the element means insert the element into the queue. Dequeue the element means delete the element from queue. Let's enqueue value 5 into the queue. So it will be stored here. Now this is the front and rear element of this queue, because now we have only one element in the queue. So first and last element will be the same now. And let's add 2 into the queue. It will be added here. So this is the rear element of the queue now. And front element remains same, meaning still 5 is the front element of this queue because it's first element entered into the queue, right? Now we will add element 7. It will be added here. Now it will be the rear element. Always remember that unlike stack, queue operations like insertion and deletion will happen in different end, but in stack, insertion and deletion will happen in same end, which means adding new element or removing element from the stack will be performed on top element of the stack. Okay, coming to queue, if you want to add new element into the queue, it will be added to rear of the queue. If you want to remove the element from the queue, it will be removed from front of the queue, that is first element of the queue. Let's add 2 more elements into this queue. Add 9, it will be added here, and this element will be the rear now. And add 1, it will be added here. Now this element will be the rear. Okay, now we can try to remove some elements from the queue. If we try to remove the element from the queue, always front element will be removed. In this case, 5 will be removed from the queue, and now front element will be 2, right? Again we remove the element from the queue. This 2 will be removed because 2 is the front element now. Think about if I want to remove this element 9. If so, you have to remove this element first. because this will be the front element now. We can't able to remove middle of the element from the queue. So first we have to remove the front element, which is this element. Then only we can able to remove this 9. This feature makes it first in first out or last in last out data structure. Here the elements which is inserted first is accessed first. Remember that in queue terminology, adding operation is called as enqueue operation and removal operation is called as dequeue operation. See you guys on the next video. Hey guys, welcome back. When we use queue data structure to store the data, we can do the basic operations like inserting element into the queue and remove the element from the queue. It's basically enqueue and dequeue. These are the main operations in queue. As we discussed in last video, queue follows first in first out or last in last out structure. And we will perform enqueue operation on the element which is present in the rear of the queue. And we will perform dequeue operation on the element which is present in the front of the queue. And trying to dequeue an empty queue is called as underflow. And trying to enqueue an element in a full queue is called overflow. Generally, we treat them as exceptions. For example, let's take this queue. Here we don't have any element in this queue, right? Now we can enqueue the element in the queue, but it's not possible to dequeue the element from the empty queue. If we try to dequeue the element from the empty queue, it will give exception. And this is called underflow. Like the same way, we can't able to enqueue the element in the queue when queue is full. If it tries to do that, it's called overflow. For instance, this queue size is 5 and I'm enqueue the element into it. I'm enqueuing A and then B and then C, then D and finally E. Here E will be the rear element of the queue and A will be the front element. If we try to enqueue the element F, it will give exception because queue is already full. Other than these main operations, we have some additional supporting operations like front, queue size and is empty queue. Let's see one by one. First one is front operation. Front operation returns the first inserted element from the queue. From this queue, it will return element A because this is the element which we have inserted first. And next is queue size operation. It will return the number of elements stored in the queue. If we apply this operation on top of this queue, it will return 5 because here we have totally 5 elements. And next is empty queue operation. It indicates whether any elements are stored in the queue or not. If we apply this operation in this queue, it will return false because we have some elements in the queue, right? So it will return false. Okay, fine. Now we can discuss about complexity. So what is the complexity of the queue operations? In any collection, we have to consider the complexity for the operations like insert, delete, accessing element and search the element. As we discussed earlier, when we enqueue element into the queue, it will be add the element only in the rear of the queue. So complexity to enqueue will be 1, that is O of 1. Similarly, if you would like to dequeue an element from the queue, always it will be front element from the queue. So complexity for dequeue is also will be 1, that is O of 1. The next operation is search. When we search element from the queue, we have to travel from first element. Say for example, in this queue, if you want to search element C, we have to travel from the first element. So complexity will be n times, that is O of n. And finally access the element. To access the element, we have to travel from first element. So again complexity will be n times, that is O of n. See you guys on the next video. Now we are going to see some real world application for queue data structure. Think about, you're going to develop one application which accepts input from the user and it should respond back to the user. And you have to serve the response first in first served basis, which means your application should process the first request first. So how you will do that? If you thought about process the request based on timestamp, but there is better way to do that. Instead of that, you can enqueue this request in queue and dequeue back while processing the request. It will give first request first automatically. So knowledge of data structure is choosing right data structure for right place. We can take printer as another application for queue. It will queue the document which is you sent for printing and it will process based on first come first served basis. And scheduling job in CPU is another application for queue. In multitasking environment, for example operating system,
In such environment, CPU cannot run all the jobs at once. So job must be batched up and then scheduled according to some policy. Again, queue might be the suitable option for this case. Other than this, we can say millions of applications running based on queue. These are just an idea of using queue data structure in real world. See you guys on the next video. Hey guys, welcome back. In this video, we are going to implement queue data structure. We have implemented stack data structure by using linked list as well as array. Like the same way, we can implement the queue data structure by using linked list as well as array. In this video, we are going to implement the queue data structure with linked list. Okay, let's take one linked list. We will add some element onto that. When we add first element, it will be a node type. Just say for example, I'm going to add value 1. And if I am add second element into the linked list, it will be next node of that. Say for example 2, and this first node next reference will point to next element. Similarly, if we add third element, it will be added here, and second node next reference will point to third element. If we don't have any element to point, it will be null. Right? If you see here, whatever element we added newly, that will be last element of the linked list. Whatever element we added first, that will be the head element in linked list. Fine, this is normal linked list. But when we implement stack by using linked list, instead of adding the new node as a next node, we will keep new node as the head node. Say for example, if I add one new node here in the stack, it will be added here. Say for example, it's 1, and this next reference will point to null. If we add second element, the element will be the head node, like this, and this head node will point to previous node. Now this will be the head node, right? Similarly, if we add third element, whatever element we are adding lastly, that will be head node. This head node will point to previous head node, and now this is not head. New element will be the head node. Why we did like this? In stack, whatever element we are adding newly, which means lastly, that has to be deleted, will pop the element from the stack. So if you are keeping like this, we can easily delete the head node from the stack. Suppose if I want to pop the element from the stack, we can directly remove this element and we will make this head.next, which is this node, as head node. So if we are doing like this, it will be easy to delete the element from the stack. That is why we have implemented stack in this way. But in queue, whatever element we added first, that element has to be deleted last element of the queue. Meaning that whatever element we have added lastly in the queue, that element deleted lastly. For that, again we are going to use the same method which is we used for linked list. For example, in the queue we are just adding one element. Say for example it's 1. So now this will be the front element as well as its rear element. Because here we have only one element, so this element will be front as well as rear. If we add second record, it will be added here. Say for example it's 2, and this front element next reference will be pointing to next node. Otherwise we can say like rear element next node will point to next node. After pointing this, we are making this new node as rear node, and we will keep front node remain same. Like that, if we add third node, it will be added here, and rear.next will point to next element, and we are making this rear to new node. That's it. This will point to null. So this is the basic idea to implement queue by using linked list. So this is what I have implemented queue data structure by using linked list. If you see here, I have one method to enqueue the element to the queue, and I have another method to dequeue the element from the queue. This is the utility method to display whatever elements we have it in the queue. And this is the main method. From here our program execution will start. So whenever I create this class, I have created two variables. One is front and another one is rear to keep track on front and rear of the queue. And initially these two will be null. Fine, let's execute this program and we'll see what is happening. So in this queue, I'll just enqueue 1 and then enqueue 2 and then enqueue 3.
means first this element will be added, then this element will be added, finally this element will be added. I'm just printing all the elements, so it's just printing what other elements we have it in the queue. 1, 2 and 3. So after that I'm just dequeue the element from the queue, and I have just printed what the element has got deleted. If you see here in the queue, this is the element we added first, right? So this element should be deleted first. Whenever we delete the element, dequeue item will be element 1. So after that I am printing remaining elements from the queue. Once we deleted the 1, we have only 2 and 3 in our queue. So 2 and 3, that's it. So we'll run this program in debug mode so that you can understand what is happening in step by step. Before that I just put debug point in my main method and enqueue method and dequeue method. Let's debug this. Here I just create an object for my class to access enqueue and dequeue methods. In this line we are just enqueuing element 1. It will go to enqueue method. Here we are just creating one node with whatever value we are passing. Here we are passing 1, right? So after executing this line, we are creating one node with data of 1. Initially we don't have rear, right? So it will be null initially. So we are making this node, whatever node we have created, that node as rear as well as front. So I'm making this element as front as well as rear, right? Okay, now I'm going to execute this line. So after executing this line, element 2 will be enqueued into queue. So again it's going to enqueue method. We are creating node with data of 2. So it will be created somewhere here, and this value will be 2. So now we have some rear value, which is our first node. So this if block will fail, it will go to this line. Here our idea is rear element next should be point to our new node. So this is our rear node. This rear node next reference should point to new node. So this is our new node. This is our rear element next node. We're just assigning rear dot next into new node. That is what we are doing here. So what next? This new node we have to make it as rear, right? That is what we are doing here, right? We added second element into the queue. Now we are adding third element into the queue. If you come here, this is a node which is having data 3 that we are going to create here. So we have rear node. So currently we have the second node as rear node. So we have some rear node. So it will skip here. Rear dot next, which is this, pointing to new node. New node means this node. It will point here. Our next step is we have to make this new node as rear node. That's it. So we enqueued 3 elements into the queue. These elements are 1, 2 and 3. If you print this line, we expect 1, 2 and 3. See here we can see 1, 2 and 3 element from the queue. After that we are just dequeue the element from the queue. What element we have dequeued, that element will be printed here. If we execute dequeue method from this queue, which element will be dequeued? Whatever element we added first, that element has to be removed. So in this case front node should be removed. So what we can do, just we are making this second node as front node. That's it. So how to do that? Front dot next means this node, right? We are making this node as front node. So whenever we dequeue, just we are assigning front equal to whatever we have front dot next. Front dot next means this node. Currently we have this node as front node. So front dot next means this node. We are making this node as a front node. That is what we are doing here, right? So after we execute this line, this node will be the front node. This is how we can implement queue data structure by using linked list. In the next video, we will discuss how to implement queue data structure by using array. See you guys on the next video. Hey guys, welcome back. In the last video, we have implemented queue data structure by using linked list.
In this video, we are going to implement the queue data structure by using arrays. In this class, I just declared one array variable to hold the queue elements, and I declared one variable called rear to track the rear information for the queue. By default, it will be 0. Here I have created enqueue method to enqueue the data into the queue, and I have created another method for dequeue. This method will dequeue the element from the queue. This is the utility method to print what all element we have it in the queue. And this is the main method. Our program execution will start from here. In this main method, I just created one object for this class to access what all methods we have it in this class, like enqueue, dequeue and all. If you see here, I just enqueue one element, value 1, and I am enqueuing element 2, and I am enqueue third element, which is 3. So after adding this, our queue will have 1, 2 and 3. If I dequeue, 1 will be removed because this is the value we added first, right? After that, I am adding 5, then I am adding 6. So finally our queue will have 2, 3, 5 and 6, right? Let's run this and see what is happening. Here I just print what element I have deleted. Finally I print what all elements we have it in the queue, which is we expected 2, 3, 5 and 6. Now we'll go through line by line what is happening in the program. See, this is the object creation for this class. By using that object, I am invoking this enqueue method by passing value 1. In this enqueue method, we are just passing whatever element we wanted to add into the queue. This is checking for queue is already full or not. If our queue is already full, we have to show the message like queue is full, dequeue some objects. Now, initially rear will be 0, right? So for the first element, data of 0 equal to element means in the array, first element will be this data, which is 1. Then we are incrementing rear. After executing this, rear will be 1, right? For the second element, again we are checking this queue is full or not. Here we can store maximum of 5 elements into the queue. We already have only one element, right? So this will be false. If we come here, data of, in the last call, we have increased this rear value into 1, right? So data of 1, which is second element of the array, equal to this element, which is 2, right? So after executing this line, our queue will have 2 elements within it. One is 1 and second element is 2. Again I am incrementing the rear element to 1, which is 1 plus plus, that is 2. If I am adding third element into the queue, it will come here. Again this queue will not be full, it will be false. Data of 2 equal to 3. So after executing this line, our array will have 3 elements within it. Basically our queue will have 3 elements within it. First element is 1, second element is 2 and third element is 3. In the next line, we are just dequeuing the element. I am just printing what all element we have dequeued from the queue. If I call this dequeue method, it's basically we are shifting our array into one position to left. See, in our array currently we have 1, 2 and 3, right? This is the element we had at first, right? We want to delete this element first and we should have only 2 and 3. So what we can do, array into one position left, which means 2 to here, this 3 to here. Basically we are going to remove this. Now first element will be 2, second element will be 3. This is what we are doing here. So how to do that? I'm just iterating all the elements from the array. In first iteration I will be 0, so data of 0 equal to data of I plus 1, which is 1. So data of 1, we are just assigning second element into first element to the array, and in the second iteration third element will be moved to second element, and next iteration fourth element will be moved to third element, and fifth element will be moved to fourth element, something like that. So basically we are shifting our array to the left by one position and we are reducing rear count by 1. So after dequeuing this, 1 will be removed from our queue. Again I am enqueuing value 5 and 6. So it will be added into this queue. So finally we will have only 2, 3, 5 and 6 in our queue. That is what we are printing here. If I run this application, we can get 2, 3, 5 and 6 because we have deleted 1 from this queue. Okay guys, see you on the next video. Hey guys, welcome back. In this video, we are going to talk about priority queue. Priority queue is similar to queue, and only difference is While adding the element into the priority queue, data will be added in sorted order. That's it. That is the only difference between normal queue and priority queue. Other than that, everything is similar, like enqueue, dequeue operations, and basic features of the queue like first in, first out, last in, last out, everything is same. Let's take some set of elements and try to store it in priority queue, and we will see how it's sorting. Let's take the element 5, 2, 3, 6 and 4. I'll just create one empty queue. Okay, now if we enqueue this element 5, it will be added to first element of the queue. And as of now, this is the front as well as rear of the queue. Now enqueue second element. It's 2. It will be added here. Here, priority queue will make the difference with normal queue. If we add like this in queue, it will be stored here. But in priority queue, it will be sorted with ascending order. So here 2 is less than 5, right? So 2 will be swapped with 5. And this is what queue will looks like now. Now 2 will be the first element and 5 will be the second element. And 2 is the front of the queue now, and 5 will be the rear of the queue. And let's add third element. It's 3. This is lesser than 5. So again it will be swapped with 5 and it will be stored as a second element in the queue. And 5 will be third element. And add next element 6. While comparing 6 with 5, it's greater than 5. So it will be added here and it will be the rear of the queue now. And finally, I'm going to add last element 4 into the queue. It's compared with last element of the queue. Rear is 6 and 4 is less than 6. It will be moved here. Here we have 5 and 5 is also greater than 4. So again 4 will be swapped with 5. So 4 will be third element now, and 5 will be fourth element, 6 will be last element of the queue. So finally result will be 2, 3, 4, 5 and 6 in the queue. So how will be the removal process in the priority queue? It's same as normal queue. If we do the dequeue, 2 will be removed first, and next dequeue 3 will be removed, and for the next dequeue 4 will be removed, and next 5 and finally 6. See you guys on the next video. Hey guys, welcome back. This is quick wrap up for whatever we have covered in this unit. In this unit, we have seen stack and queue data structure. So what is stack? Stack is a simple data structure and it's another option to store the data. And stack is somewhat similar to linked list. In a stack, the order in which data arrives is important. So in a stack, whatever an element we have pushed first, that has to come out last. Or we can say like whatever an element we have pushed last in that stack, that has to come out first. This feature makes it last in first out or first in last out data structure. In stack terminology, adding operation is called as push operation and removal operation is called as pop operation. And we have discussed about exception in stack while performing operation on the stack. While stack is empty, we can't able to delete the element from the stack, right? Means we can't able to pop the element from the stack when it's empty. If we try to do that, it will be an exception. That is called underflow. Similarly, if stack is full, we can't able to push the element into it. If we do that, it will be overflow exception. And we have seen queue data structures. Queue is another data structure used to store the data and it's similar to linked list and stack. In a queue, whatever an element we have enqueued first, that has to come out first. Or we can say like whatever an element we have enqueued last in the queue, that has to come out last. This feature makes it first in first out or last in last out data structure. In queue terminology, adding operation is called as enqueue operation and removal operation is called as dequeue operation. And in queue also we have discussed about exception while performing operation on the queue. While queue is empty, we can't able to delete the element from the queue, right? Means we can't able to dequeue the element from the queue when it's empty. If we try to do that, it will be an exception. This is called underflow. Similarly, if queue is full, we can't able to enqueue the element into it. If we do that, it will be overflow exception. And we have seen about priority queue. Priority queue is similar to queue, and only difference is while adding the element into the priority queue, data will be added in sorted order. That's it. That's all we have discussed in this unit. Hey guys, welcome back. In this video, we are going to discuss about tree data structure. Tree is another type of data structure like linked list, stack and queue. But tree is somewhat different from these data structures. Means tree is the non-linear data structure while linked list, stack and queue are linear data structure. Which means in linked list, stack and queue, node are simply pointing to next node. Means one node will point to another node. But in tree, nodes are pointing to many number of nodes. These nodes are leaf of the tree. Let's imagine tree data structure will be looks like this. There are some properties are there for the tree structure. For example, every tree should have one root node. A root node means the node which is not having parent node. So in this tree, A is the root node. Here B is having parent which is A, but A haven't any parent. So A is the parent node of this tree. And next thing is edges. Each node in the tree connected with edges. Here this line is called as edge. Basically, each parent are connected with child or leaf node by edges. Here A is parent node for B, C and D nodes, and B is the parent for E and F nodes. These parent and child nodes are connected with help of edges. And another thing is children of same parent are called as siblings. Here B, C and D are siblings of A, and E and F are the siblings of B. Depth and height of the tree is the another thing we have to discuss when we talk about tree. The depth of the node is length of the path from the root node to the node. Here depth of J is 3, that is A to B and B to F and F to J. So totally we have 3 edges, right? So depth of the J is 3. And next thing is height of the node. The height of the node is number of edges on the longest downward path between that node and a leaf. It is the longest path from the node to a leaf. So node A height is the number of edges of the path to J, not E or F node, and its height is 1, 2, 3. So height is 3. Height of the tree is the maximum height among all the nodes in the tree, and depth of the tree is maximum depth among all the nodes in the tree. For this tree, depth and height return the same value, but for the individual nodes we may get different result. See you guys on the next video. In the last video, we have discussed about tree data structure, its basics of tree. Further, we will discuss about binary tree, which is derived from tree. We can say like if tree met certain condition which is applicable for binary tree, that is called binary tree. So the things we were discussed about root node, children, height and depth are applicable for binary tree also. So what condition should have met tree to become binary tree? The condition is each node should have up to 2 children nodes, creating the branch of the tree. The 2 children are usually called as left and right node. Parent nodes are nodes with children, while child node may include reference to their parents. Note that should not be more than 2 nodes. So binary tree must have only 2 nodes at max. See, this is binary tree. See, this is binary tree. If you see here, this node having 2 children, and again this node having 1 children. But we should not have more than 2 children for a node. Suppose if this node have one more node like this, it's not a binary tree. There are different type of binary trees are available. That is strict binary tree, full binary tree, and completed binary tree. Strict binary tree means each node should have exactly 2 children or no children. Strict binary tree will be looks like this. If you see here, nodes are exactly having 2 children. And full binary tree means each node has exactly 2 children and all leaf nodes are at the same level. Full binary tree will be looks like this. If you see here, each node has exactly 2 children and all leaf nodes are at the same level. And next is complete binary tree. Complete binary tree is the binary tree in which every level, except possibly the last, is completely filled and all nodes are as far as left possible. See, this is complete binary tree. These are the basic things we should consider for the binary tree. So while implementing binary tree, how we can define the node? As we have discussed in linked list video, for the linked list node structure will have 2 parts within it. One is actual data and another one is node which is holding a reference of next node. So class node, it should have 2 content within it. One is data, so int data, and next is node type. Node should point to next reference, so next node. Here this data will hold the element value and this one should point to next node. So this node structure will have another node inside it to hold the next node information. Like this, every tree node should have up to 2 children. These children are also be a node. So for this tree, how will be the node structure? It will be looks like this. This part will have exact data and this left side is holding reference for left node and this right section will hold right node. Let's take this binary tree. It's a logical representation of binary tree. Think about how you will represent this while implementing. So we can define binary tree node like this. Class binary tree node and it should have 3 content within it. One is actual data, so I will represent that with int data, which is holding actual data. And the next attribute is binary tree node, which is same type. Left child node, which is holding reference to left child of the node. And third attribute is binary tree node of right child node, which is holding reference to right child of the node. For the leaf nodes, left child node and right child node will point to null. Leaf node means the node which is not having any children. This is root node. It has 3 things, that is original data and reference to left child and reference to right child. So this left section will have address of this node and this section of the root node will have address of this node. Similarly, all the child node have the data as well as child node references and leaf node references pointing to null. Let's see you guys on the next video. Hey guys, welcome back. In this video, we are going to discuss about binary search tree. Binary search tree is the another variant of binary tree. In the binary tree, we haven't any restrictions for the node data. So if you want to search any node data from the binary tree, you have to search both left subtree and right subtree. Means we have to visit each and every node of the tree. So complexity will be O of n in worst case. That's why we came for binary search tree. The main use of binary search tree is search. It has the restriction for the node data while storing it into the binary search tree. So it will simplify the complexity of the search operation in the tree. As a result, it reduces the worst case complexity to O of log n. So what is that restrictions? In binary search tree, all the left subtree element should be less than root element and all the right subtree element should be greater than root element. This restriction is not only for root element, it will be applicable for each and every node present in the binary search tree. Let's take this binary search tree. and let's take this root element as 10. So here this left section of the tree node data should be less than 10 and this right subtree node data value should be greater than 10. If you want to add value to this node, it should be greater than 10. Let's say for example 15. Like that. If you want to add element onto this node, it should be less than 10. Let's say for example 7. Let's take this right subtree of this node 7. If we want to add the data to this node, it should be greater than 7, but we should make sure that it should be less than 10 because this complete section comes under left subtree of the root. So this left section of the subtree should have less value than 10. While we add element into the binary search tree, we should consider this restriction. Okay, now we add the element for this node, let's say for example 9. And left side of this node 7 would be something like less than 7, for example 5. And similarly, this left side of this node 15 would be less than 15 and it should greater than root node 10, for example 12. And this right side of the node 15 should be greater than 15, for example 16. Okay, now in this binary search tree, we would like to search element 5. Here, we no need to search all the element in the tree like binary tree. First, we have to check root node value. Based on that, we can decide which way we have to travel to search element 5. In our case, root element is 10. The value we are looking for 5, which is less than 10. So, we have to travel left section of the tree because we already arranged data like this in binary search tree. So, we have to check the element we are looking for only one half of the tree. That's why the complexity for the search operation in binary search tree is O log n. So how we can delete the node from the binary search tree? Let's take node 16. This node does not have any child node, so we can directly delete this. After deleting this node, tree will be like this. We have deleted the node directly if it's not having any child. But what about when we want to delete the node which is having some child on it? Let's say for example, we want to delete 15 from this tree. It's having node 12, right? We can't delete it directly. So what we have to do is, we have to swap the element first. So here, we have to swap this element like this. 12 will be moved to higher level and 15 moved to leaf node. Now we can delete this node 15, right? So deleting is not always easy in binary search tree. Think about the element which is have 2 nodes or more subtree nodes in it. So basic idea is we have to shift it and then we have to delete it. Okay guys, see you on the next video. Hey guys, welcome back. In this video, we are going to discuss about implementation approach for search operation in binary search tree. Before we move to binary search tree search logic, we'll just understand how node structure will be in binary search tree. Let's take this node. As we have already discussed, in every tree node will have 3 parts within it. One is actual data. Here I will represent that actual data as key, and another one is left node, which is pointing left node reference, and right node, which is holding right node reference of the node. Say for example, take this tree. In this tree, take this node H. Suppose if we represent this node as node structure, this key will be H and left node will be pointing to this node 4 and right will be pointing to this node 12. Clear? So this is how we will use node structure in tree. Okay, coming to search logic, I have just created one binary search tree here by calling insert method. We will discuss about this insertion logic and deletion logic and all in upcoming videos, but in this video we are going to concentrate only on search logic. So imagine this is what we have already created. So this is the tree structure we have currently. From this tree, I wanted to search element 1. I just call this search method by passing root node, which is H, and I'm sending one more parameter 1. That is, this is the value I wanted to look from this binary search tree. Clear? Let's start with search logic execution. So this is our binary search tree. We are just calling our search method by passing root node, which is H, and key is 1,
this is what we wanted to search from this binary search tree, right? So here our core idea is, first we have to check whatever value we wanted to find, that value is already there in our current root node, means that is the node we are looking for, right? So I'm just checking. So I'm just checking this root node holding the value 1. If so, we found that, right? So we can directly return that node, that's it. But in this case, key is 1, which is not root node. So what next? And in binary search tree, we know that what null value we have left side of this node, that should be less than 8. From this root node, left subtree node values less than 8 and right subtree node values will be greater than 8. Now we have to decide which way we have to travel. Whatever value we are looking for, it's less than 8, we have to go for left side of this node, or else we have to go for right side of this node. So whatever value we are looking for, it's 1, so it's less than 8, so we have to go left side of this node, right? Again, from here we have to do the same thing. This is the current root node now. From this root, whatever value we are looking for is there or not. If it is there, then this is what we are looking for, so we can return this node directly. Or else again we have to decide, we have to travel left side of this node or right side of this node. So whatever value we are looking for is 1, it's less than 4, so again we have to travel left, so in this node. Now take this as a current root node. Now again we have to check this root node having 1 or not. Yes, we found it, so we can return this. That's it. This is what we are going to do in this search method. Let's go through this method line by line. So whenever I call this search method, I just pass root node, which is 8, and value, which is key, whatever we are looking for is 1, right? If I send here, our first work is, we have to check whether this root node having value 1 or not. If this root node having 1, that is the node we are looking for, right? So I'm just checking root.key, means 8 equal to key 1, no, right? So this will be false, it will go here. Now we know that whatever value we're looking for, it's not root node. So what next? We have to find which way we have to travel, left side or right side. So we have to compare this value 1 with root node. Based on that we can decide which way we can go, right? So if key is less than root node key, then we have to travel left, right? Here key is 1 and root node is 8, so 1 is less than 8, so we have to look only for this left side, or else we have to go for right side, right? So in this case this will be true because key is less than 8. Again we are calling the same search method by passing root.left, which is this node. We are passing this node as a root node to search method again. Again we are passing the value which is we wanted to search, right? For this second search call, root node will be 4, key will be 1. Here we are checking whatever value we are looking for, it's there in root or not. Again 1 is not there in root, so it will be false. So again it's coming here. So here k is 1, which is less than 4, right? So again we have to travel left side. So again we are calling search method by passing root.left, which is this node, as a root node for this search method and key value, right? Now for this next call, root node will be 1 and key will be 1. Here we are checking root.key, 1 equal to 1, yes. So this is what we are looking for. We can directly return this node, that's it. So whenever I call this search method by passing root node and key, and I will get node back if that element is found. So that node.key means it will return the key, which is 1. So this line will print data you are looking for 1. So this is how search logic will work in binary search tree. So here, what is the complexity for this search operation in binary search tree? Let's say here we have totally 7 nodes. To find the node 1, here we are not looking for each and every node, right? First we check age. From here we'll decide that we have to go for left side or right side, right? From here we decided that we have to go for left side, so we no need to check this right side 3 nodes, right? So here we have reduced our half of work, right? So from here also, right, we are not going for all the child nodes of this 4. From here again we are deciding which way we have to travel. So based on that value, whether we will go for left side or right side. So from here also we reduced half of the work. So what is the complexity? It's log n, right? But this is the best case scenario.
Why means if you see this tree, it's completely balanced, right? Means for this root node, left hand side we have 3 nodes, right hand side we have 3 nodes. But think about this tree. This is also binary search tree, right? Let's take this node 4 and this 7 is greater than 4. So it will be right side. I don't have any left node for this 4. Again for this 7, right? I don't have left side, only right side node, which is 16. Again 20. Again 37, 38, 43. So this is also proper binary search tree. If I want to search node 43 from this node, apply the same logic whatever we have did earlier. We have to search all the nodes from this binary search tree. We don't have other options, right? So now tell me, what is the complexity? It's O of n, right? Because we have to travel for all the nodes to find number 43. So in the worst case, binary search tree complexity will be O of n, and in the best case, O of log n. See you guys on the next video. Hey guys, welcome back. In this video, we are going to discuss about implementation approach for insert operation in binary search tree. So we are going to construct this binary search tree here. Let's take this is root node H. This is having left subtree which is 3 node and right subtree which is having another 3 nodes. This is what we are going to construct here. So how we can do that? So if we take tree.root means it's this node, right? So whatever value we are passing here, that has to be placed here. So tree.root means this one, H. Tree.root.left, which means this position. I'm passing 4. It will be placed here. Tree.root.right. Root.right means 12. Root.left.left. Root.left.left. This position, it's 1. Root.left.right means root.left.right. This position is 7. Again the same thing. Root.right.left 9. Root.right.right, which is 14. This is the way we can construct the binary search tree. If you see here, this node structures and all hard-coded thing, right? If you see, this root node is H. Whenever I create root.left, I should make sure that it should be less than H, right? Whatever value I'm passing here, it will directly placed here. This line of code will not check whatever value we are going to assign this root.left is less than 8 or not. So it will directly assign the value whatever I'm passing here to that position, right? Say for example, if I'm sending 14 here, so it will be stored here. It will not check anything like it's proper binary search tree or not. So this is not the right way to create binary search tree. I just given this for some basic idea, means how we can represent this position and this position and all, right? So I'll make it 4. So whatever logic we are writing for the insert element into the binary search tree, it should automatically handle the position, meaning that if I send 8, I don't have any node in this tree, right? So this will be the root node. If I send 4, our program should automatically identify that this 4 is less than 8, so it should go for left side of this 8. If I send 1, it will check this 1 is less than 8, so it should go for left side. In the left side already we have data. Again we have to check from here, it should go right or left. So 1 is less than 4, so again it will left side of this 4. Like the same way, if I insert 7, it's less than 8, so it will go left side of this. Again we have one data 4. From again we will compare whether it should go for left side or right side. 7 is greater than 4, so it will go to the right side. So this is the way our program should work. Let's see how we can implement this insertion logic in binary search tree. Let's take this method. For this method, I'm just passing value H, means I wanted to insert this node into my binary search tree. Alright, so this is the method. I'm just passing key H and I'm calling on a helper method to make our code cleaner. Here I'm just passing the root node. Root node initially null because currently we don't have any node in our binary search tree, right? So by default it will be null, and this is the key which is we sent H. So as of now we don't have any data. We wanted to construct the binary search tree in this structure. As of now I just make these elements as X. Okay, now we called this method by passing H. From here we are calling on a helper method by passing the root node and key value H. Since we don't have any element or node in our binary search tree, whatever node we are creating first in binary search tree, that node will be the root node. That is what I am doing here. If root is null,
based on that value I'm constructing new node. I'm just returning that node. That's it. We are making that node as root node of this binary search tree. So in this case 8 is the first node, right? So whenever we call this method by passing value h and root is null, it will return the node. We are making that node as root node. So as of now 8 will be placed here. Clear? So after h we are calling the insert method by passing 4. Means basically we wanted to add second element into this binary search tree. So we are calling this insert method by passing value 4. We are sending 4 here. Now we have root node here, right? So from here we have to decide whether this 4 has to go left side or right side. 4 is less than 8, right? So it has to go to left side. In the left side I don't have any node, so it will be placed here. This is what we have to do for this insert call. Alright. So we are calling this method by passing 4. Here we are calling insert helper method by passing root node, which is h, and key value is 4. So it will come here. Root is h, key is 4. So here our root is not null, right? So this will be false. Now we are checking whether this new node has to go left side or right side. So here key is 4 is less than root node h. So this will be true, because whatever element we sent now, that is lesser than 8. So this will be true now. So our plan is we have to place our new node into root.left position. Root.left position means this position. So root.left equal to, again we are calling same method. This method should return one node. If it's returning the node with value 4, it will be assigned to root.left, which is this place, right? So here what we are sending in this root helper, it should accept two parameters. One is root node and key. Key is 4, we know that. And what is the root node we are sending now? Root.left. Currently root node is h. We are sending this root.left, which is null. We have not assigned any value yet, right? So it's null now. So root.left means it's null now. So we are passing root.left and key to this method again. Root will be null and key will be 4. If root is null, we are creating the node with value of 4 and we are returning that. So this will return the node with value 4. That will be assigned to root.left, which is this position. So 4. Clear? Fine. And our next element, we wanted to insert 1 into this binary search tree. By passing the 1, I am calling this method. Again we are calling helper method by sending the root. Root will be h, key will be 1. We are calling this method. Root is not null, so it will be skipped from here. We have to check whether we have to go left side or right side. So 1 is less than h, so it will go here. From here again we have to assign root.left. As of now this is the root. Root.left means this position. This position equal to, I am calling this method by passing new root node, like means root.left. Root.left means this one. We are sending 4 here and value is 1. So this method again called with root node 4 and key value 1. Again here root is not null, right? Here we have root value 4. So this is not null. So this will be fail again. So again we are checking 1 has to go left side of this 4 or right side of this 4. Since 1 is less than 4, we have to place this in left side of this 4. So root.left. Currently this is the root. Root.left means this position. We have to assign root.left equal to something, means some node. That will be placed here. So we are calling insert helper method by passing root.left, which is null, and 1. If you are passing this, this will be null and this will be 1. Root is null now, so it will create the node with value of 1 and it's simply returning, right? So here we will get node with value 1. That will be assigned to root.left. So here it will be 1. And next element is 7. For the 7, we are just calling this method again by passing the 7, and again we are calling helper method by passing the root node h and key is 7. Now root node is not null, so it will be skipped, and again we have to check whether this 7 has to go left hand side or right hand side of this root node h. 7 is less than 8, so again it has to come this. So again it has to come left side of this node. This root.left means this one, and we are calling insert helper method by passing the root.left, which is 4 and key 7. While coming this, again root node is not null, so it will come here, key is 7 and less than root.key. Root is 4 now, so this is false, so it will come here. If key is greater than root.key, yes, this is true, right? Because 7 is greater than 4. Now root.right equal to root.right equal to whatever node it's returning, that has to be placed here, because root.right. Again we are calling this method by passing root.right, which is this. As of now it's null, so it's come here, it's null, k equal to 7. If root is null, we have to create the node with value 7 and we are returning that has to be assigned to root.right, which is this position. So I make this as 7. And next node is 12. We are calling this same method by passing 12. This is the root node h. It will come here. Root node is not null, so it will come again. So it will check whether this key is less than root node or greater than root node. It's greater than root node, right? So it will go here. So root.right equal to root.right equal to root.right, we are passing, and key, which is 12. So here root.right is null, so again it will call this method by passing null and 12. Root node is null, it will return the node with value of 12, that will be assigned to root.right, which is this position, 12. And next value is 9. So we are calling this method by passing 9. It will call this insert helper method by passing root node and value 9. Root node is not null, this will be false, this will be true now because key value is greater than h, so this will be true. And root.right means 12. Insert helper by passing root.right, which is 12 and key is 9. So it will be 12 here and this will be 9. Root is not null, so it will come here. This will be true because root.key is 12 and key is 9, which is less than 12, right? So it will come here, root.left, which is this position, equal to, we are calling this method by passing root.left. Root.left is null, we are passing this, it will return the node with value of 9, that will be assigned to root.left. Currently root is 12, root.left means this position, it's 9. Like the same way we are calling the insert method by passing value 14. So we are calling this insert method by calling 14. Root node will be h, this will be 14. Again we are calling this insert method by passing the root node h and key value 12. Root is not null, it will come here. Key is less than root key, no, key is greater than root key, so root.right, which is 12, equal to, we are calling this insert method by passing root.right, which is 12 and key is 14. So it will come here, again this will be 12, this will be 14. Root is not null, it will come here, this will be false. Key is greater than root.key, key is 14 here, 14 is greater than 12, so this will be true. Now root.right, which is this, equal to, we are calling this method by passing root.right, which is null and key is 14, so this will be called as null 14. So root is null, it creates the node with value of 14 and it's returning whatever value is returning, that value has to be assigned to root.right. Current root is 12, root.right means this value 14. So that's it, we have constructed the binary search tree with proper structure. If you see here, from this root node, what all nodes we have left subtree of this root node h, it's lesser than h, and what all nodes we have it in right subtree of this root node h, it's greater than h. So this is how we have to implement insertion operation in binary search tree. See you guys in the next video. Hey guys, welcome back. In this video we are going to implement deletion logic for binary search tree. In the last video we have discussed about implementation approach for the binary search tree. So this is what we have created in the last video. So by calling insertion method, we have inserted the nodes into binary search tree, right? So this is the search logic. This is also we have already discussed. Whenever we call the search method by passing the root node and by passing the key value, it will find whether this binary search tree having this key or not. If it is there, it's printing like data you are looking for is 1. This is also we have already seen. In this video we are going to delete some node from binary search tree. Let's take this 14. If we try to delete this node 14, if you see here, this node does not have any leaf nodes, so we can delete this directly. There is no restrictions, there is no difficult things to handle that, right? Because it's not have any child node.
like this. Same case for node 9, node 7 and node 1. For this leaf and all, right, we can directly delete it. But if I want to delete 8, 12 or 4, we can't able to directly delete it, right? Say for example, if you want to delete node 12, first we have to swap this 14 into this position, then only we can able to delete this 12. Let's see how we can implement that. I'm just calling delete method by passing 12. Here I'm calling helper method by passing root node and key to make our code cleaner. So while calling this method, this root node will be 8 and key will be 12. And here I'm just checking from which side I have to travel. So whatever node I wanted to delete, if that node will be less than 8, I have to travel to left side, or else I have to travel to right side, right? So in this case, key will be 12. So this is not less than root node 8. So this will be fail. And this if block, key is greater than root.key. Yes, this is true because here our key is 12 and root.key is 8. So we have to make this root.right, which is this element, equal to, again we are calling this delete node by passing root.right, this node, and key is 12. So again we are calling this method by passing root node and key. Now root node is 12, key is also 12, so this case will be fail, and again this case also will be fail because this 12 is not less than 12 and not greater than 12 as well. So it's 12, right? So it will go to else block. Here I'm just checking this node does not have left as well as right, means I can directly delete it, and I'll make this root.right equal to null. That's it. But this is not the case here, right? I am checking whether it's having any one of the node, like left or right. In this case, if left is null, means it's having right node, right? If it is having right node, I'm just returning the right. If it is not having right node, means it's having left, right? So I can return the root.left. But in this case, both are false because here we have left as well as right. So it will come this block. From here, in the right side of this root node, which one is the less value, means minimum value, that value we wanted to make it as this node. So if I call this minimum method, it will return 14 because for the 14 we don't have any leaf node, right? So we don't have other option, we have to return this 14 only, so it has to be placed here. So this minimum value will be 40 and root.key is equal to 14. Now root is this one, root.key means this value replaced by 14. So after executing this line, this 12 will be replaced with 14. So next thing is we have to delete this node. For this root.right, which is this node, equal to, again we are calling this delete node method by passing root.right, which is this node, and passing minimum value, which is 14. So this method again called with root node 14 and key is 14. So this will be false, and again this will be false. So it will come here. Here we don't have left node as well as right node, so it will come here, it will return null. So it will return null. Root.right will be null. Root.right will be null, means it's deleted. When I run this program, this is what we have in the binary search tree. After deleting the 12 will be removed from this binary search tree. So we have only 1, 4, 7, 8, 9 and 14 in this binary search tree. This is how delete logic will work in binary search tree. See you guys in the next video. Hey guys, welcome back. In this video, we are going to discuss about tree traversals. Think about in front of you, some people are standing on the queue, maybe around 20 peoples. Now, someone asks you to find the person who is wearing blue shirt. How you will find? Your eyes will start looking from the person who is standing first in the queue and travel from the till end. Or will start looking from the person who is standing last in the queue and travel from the till start, right? The way you are looking is sequential order. Suppose in middle, somewhere you found the person who is wearing blue shirt, then immediately you will start looking further, right? Because you found the person. So there is no use to look the remaining people in the queue once you found the person already. In the same approach, we will follow the search the element from the array or linked list. Array or linked list data structure store the data sequentially. If we want to find some element, we have to travel sequentially. It's straightforward approach. Once you found the element which is you are looking for, then you can stop looking further. Let's take this list. 10, 28, 3,
11, 5 and 8. If you want to search 5, you can start from first element, which is 10. Just check, is this 5? No. So move to the next element. Is this 5? No. So again for third element. Is this 5? No. Again move to the next element. Is this 5? No. Then is this 5? Yes, we got it. Like this, you want to search element 3. In this list, you will start from first element and travel sequentially to find 3. It's pretty much straightforward to travel through the linear data structure like array and linked list, tag or queue. But it's not easy to travel through non-linear data structure like tree. Let's take this tree. If you want to travel in this tree to search some element, we have lots of options to travel through this tree. Let's say for example starts from 1, 2, 4, 5, then again 2, 1, 3, 6 and 7. Or we can travel like 4, 5, 2, 1, 3, 6, 7, something like this. Or 1, 2, 3, 4, 5, 6 and finally 7, like this. So while traveling through the tree, we have lots of options to travel. So tree traversal is a process of visiting each node in a tree exactly once in some order. Visiting a node means reading or processing the node. Based on the order on which node is visited, tree traversal algorithms are classified into two categories. One is breadth first search and another one is depth first search. We can call breadth first search as BFS and we can call depth first search as DFS. Breadth first search and depth first search are general technique to travel or search for particular element in the tree structure. Let's talk about breadth first search and depth first search in detail in upcoming videos. See you guys on the next video. Hey guys, welcome back. In the last video, I mentioned two approaches to search or travel through the tree. The first one is breadth first search and second one is depth first search. Here we will start with breadth first search. In the name itself, it says that we have to visit the node based on the breadth of the tree, or simply we can say like search horizontally. And in breadth first search, we have to prioritize the node by visiting all the node on the same level before we move to the child node. Let's take this binary tree. If we travel by using breadth first algorithm, we have to travel horizontally, or we can say level wise. That is, we have to prioritize the visiting all the node on the same level before we move down to the child node. In this tree, this node 1 is level 0 and this 2 and 3 nodes are level 1 and 4, 5, 6, 7 nodes are level 2. So what we will do in breadth first search is, we will visit the node that are present in the level 0 first, and then we will visit the node that are present in level 1, and finally we will visit the nodes which is present in the level 2. So here we have to travel from level 0. I will write it here. It's 1 and then level 1, that is 2 and 3, and next level is 3. So next node will be 4 and then 5 and then 6 and 7. This kind of traversal is also called as level order traversal. So we have to travel 1, 2, 3, 4, 5, 6 and 7, and we will keep going on if we have more levels on this tree. Here more important thing that you have to notice is it's traveling horizontally. See you guys on the next video. Hey guys, welcome back. In this video we are going to implement breadth first search algorithm. To demonstrate that, I have just created one binary tree. So this is how I have created binary tree. Tree.root 1, root.left 2, root.right 3, root.left.left, root.left.left 4, like that, root.left left dot right is 5. Okay, now we have tree, right? In this tree, this is level 0, which is having only one root node, that is 1, and level 1, which is having two nodes, 2 and 3, and level 2, which is having again only two nodes, node 4 and node 5. Alright, if we travel through breadth first search, or it basically called as level order search, right? So each and every level we have to visit, so we have to search the element in level by level. So in this case, level 0 first, then level 1, then level 2. Means level 0, first we have to visit 1, then level 1, which is 2 and 3, and level 2, which is 4 and 5. So what we can expect, 1, 2, 3, 4 and 5. Right? This is what this method will do. I just created one method, print level order, which is basically breadth first search. If I run this program, we can see like 1, 2, 3, 4 and 5, which is we expected, right? Okay, now we'll go through this method line by line. So this is our tree. In this method, I'm just getting total levels of this tree. In this tree, we have totally 3 levels, right? This method will return 3. That one I have assigned to variable h. I mean its height. Now we'll go to this method. This method accepts one parameter, which is root node 1. From here, we will go through full left side and full right side of this tree. Which one is higher value? That value this method will return. That is what we are doing here. Math.max means it will accept two parameters, 1, 2, and it will compare both the values and it will return which one is maximum. In this case, we are just run through left side and right side, and it will compare both the things, which one is higher value, that it will return. So totally here in the left side we have totally 3 levels, right? So it will return 3. So here we can expect h equal to 3. Now we have 3 levels, right? So each and every level we have to iterate and we have to print that values. That is what we are doing in print given level method. Let's put debug point here and I'll run this program. So here h will be 3, means level 0, level 1 and level 2. So for the first iteration, we have to process the level 0. So I equal to 0, so level will be 0 and a root node will be 1. This one. If we go here, I'll put some breakpoint here also. If root node equal to null, we have to terminate the program, but in this case root node is not null, so it will skip. If level equal to 0 means basically we will have only one node in level 0, right? So we can directly print that element. In this case level will be 0, so it will print root.key, which is 1. If you see here, it should print it here 1. Fine, right? Now next iteration is level 1. So here we are passing I equal to 1, root will be again same 1. If you see here, root is not equal to null, then it will skip, level will be 1. So this is also will be false now. Now in this level 1, we have two nodes, right? Means basically left node and right node for this root node. First we have to process this, then we have to process this right node. For that we are calling the same method by passing root.left, which is this element, and next we are passing root.right, which is this element, for the same method, and we are passing the level as well. So as of now level will be 1. Whenever we make root.left, we are coming from here to here, right? So we have to reduce level by 1, so level minus 1, which is 1 minus 1, 0. So again we are calling this same method by sending root.left, means this node as the root node, and level will be 0. Alright, now level 0, so it's printing this root node now, so we can expect 2. Right, now we have completed this node, right? What next? We have to print right side of this root node. We have to complete right side now. So next this one, root.right, which is this node. We are calling this method by sending this root.right, which is this node, as the root node to this method, and sending the level by reducing 1, because we came from here to one level down, right? So we have to level minus 1, which is 0. Root node will be 3 now, so level will be 0. It will print root node, which is 3. So we have finished level 0 and level 1. Now level 2, right? In the third iteration, it's level 2. I equal to 2. We are sending I equal to 2 and root node equal to 1. If we come here, level is not 0, so it will go to else block. Level is greater than or equal to 0. So here we are calling the same method by sending root dot left, which is this, and level is 2 minus 1 because we reduced one level, right? So level minus 1, that is 1. So again we are calling this method by sending this as root, and level is 1. Again this will be false and this will be false. It will go here. Level is greater than 0, which is level 1, right? So it's greater than 0. Again it will go here. From here, this is the root, right? From here, root dot left, which is this node, and we are sending level minus 1. Currently level is 1. 1 minus 1 means 0, because if you come from here, it's 1 level down, then 1 level down. From here 2 to 1, from here 1 to 0, so it's 0. Now level is 0. Our root node is 4 now. It will print 4. Right? What next? Right. Root dot right. This is our root node, and root dot right means this 5, and level is 1 minus 1, which is 0. So it will print 5 here. Right? And we have visited each and every node in all the levels. So final result will be 1, 2, 3, 4 and 5. So basically first level, second level and third level. After removing the breakpoints, I am just running this program again so that it will give clear picture about it. 1, 2 and 3, then 4 and 5. Right? This is how breadth first search will work. See you guys in the next video. Hey guys, welcome back. In breadth first search approach, for any node, we visit all its children before visiting of any its grandchildren. Let's take this tree. In this tree, first we will visit 10, and then we will visit 7, and we won't go for 5 or 9. Instead that we will complete the same level first, then only we will move to the down. But in the depth first approach, if we would like to go child of any node, we have to complete full left subtree of that node before we move to right child node. In this tree, 10 is the root node. If we are going left, we have to complete this full left subtree of the node 10. We should complete this left subtree in full depth, or in other words, we should complete all the grandchildren of 10 along this path before we going to right child of 10, that is 15. And then we have to move right child of 10, and once again we have to visit all the grandchildren of right subtree of 10. So basically we have to complete right subtree. In depth first search approach, the relative order of visiting the left subtree, the right subtree and the root node can be different. Again, in the same tree, we can visit left subtree first, then root node, then right subtree of the root node, or root node first, then left subtree and then right subtree. So the order may be different, but the core idea in the depth first search is visiting a child means visiting the complete subtree in the path. Based on this order of visiting the node in depth first search, there are 3 popular depth first search strategies. One way is first visiting the root node, then the left subtree and then right subtree. This traversal is called as pre-order traversal. The another strategy is first visit the left subtree and then root node and then right subtree. This traversal is called as in-order traversal. And if root is visited after the left and right subtree, that is called post-order traversal. In order to remember, we can represent this root node as D, that is data, and left node we can refer as L, and finally right node will refer as R. So in the pre-order strategy will be first root node, then left subtree, then right subtree. And for the in-order strategy will be left subtree, then root node, then right subtree. And for the post-order strategy will be left subtree, then right subtree, then root node.
Okay guys, see you on the next video. Hey guys, welcome back. In the last video, we have discussed about depth first search and its strategies to travel over the tree. Here we will discuss about pre-order traversal strategy in detail. Let's take this tree. If we go over pre-order traversal, we have to visit root node first, then left node, then right node. Okay, now we will travel through this tree. At first, root node, that is 1. I will write it here, 1. And also this is the current node now. Now we should go to the left node of this current node before we move to the right of this root node 1. Here left node is 2. We have to complete left subtree of this node 1 before we move to right child of this root node. So now we are in node 2. So as of now this is the current node. So as per pre-order traversal, we have to travel left subtree. So next visiting node will be 4. Now this is the current node. From here we don't have any left node for this node 4, right? And also we don't have any right node 2. So we have to go back to node 2. It's already visited. And then we have to visit right node, which is 5. For this node 5, we have to go left as well as right node. For the 5, we don't have any left node as well as right node. So again we have to go back to node 2 and again go back 1. So now we have finished the traversal for left subtree of 1. Now we have to do the same thing for right subtree. So now we have to visit 3, then left node which is 6, then right node of 3 which is 7. So finally we would have traveled from 1 to 2 and then 4 and then 5, then 3 and 6 and at last 7. Hey guys, welcome back. Here we will discuss about in-order traversal strategy in detail. Let's take this tree which is we have used for pre-order traversal. If we go over in-order traversal, we have to visit left node first, then root node and then right node. Okay, now we will travel through this tree. At first, left node of the root node 1, that is node 2. This node having children, so again we have to travel left, that is node 4. Node 4 does not have any children, so we can stop it here. So this is our first visiting node. I'll just write it here, 4. Now node 4 is the current node. As per in-order traversal, next we have to visit root node of the current node 4, that is 2. So next visiting node will be 2. Then right node of this root node, that is 5. So next visiting node will be 5. Are you clear on this? As per in-order strategy, we have to process the left node first and we have to move to root node and then we have to move to right node. Clear? At this stage, correct node is 2. We came for 2 from the node 1 left subtree. So we have finished left of the node 1, which is root node. So what next? After left, we have to go root node, right? So next visiting node will be 1 and write it here 1. And then we have to travel right of the node 1. From node 1, right subtree is node 3. This node 3 having child. So we have to travel left first, then root and then right. So it will print 6, 3 and finally 7. So finally we would have traveled from 4 to 2 and then 5, then 1, then 6, 3 and at last 7. Hey guys, welcome back. Here we will discuss about post-order traversal strategy in detail. Let's take this tree which is we have used for pre-order and post-order traversal. If we go over post-order traversal, we have to visit left node first and then right node and then root node. Okay, now we will travel through this tree. Here at first we have to visit left subtree. At first left node of the root node 1, that is 2. This node also having children, so again we have to travel left, that is 4. This node 4 does not have any child, right? So we can stop it here. I will write this here 4. Now node 4 is the current node. As per post order traversal, we have to visit right node of this current node 4, that is 5. So next visiting node will be 5. Then root node, that is node 2. So next visiting node will be 2. At this stage current node is 2. We came for 2 from node 1 left subtree. So we have to finish left of the node 1.
So what next? After left, we have to go for right subtree, right? So we have to travel to node 3 and it's having child, so we have to visit left node first, that is 6, and then right, that is 7, and root node, that is 3, and finally we will visit the root node of this right subtree, that is 1. So finally we would have traveled from 4 to 5, and then 2, and then 6, then 7, then 3, and at last 1. Hey guys, welcome back. In this video we are going to implement depth first search traversal algorithm. As we have already discussed, depth first search algorithms comes with 3 forms. One is pre-order, in-order, and post-order. If we travel through pre-order, we have to travel root node first, then left node, then right node. If we travel through in-order, we have to visit left node first, then root node, and finally right node. If we travel through post-order, we have to travel left, then right, and finally root node. Now we are going to apply these 3 traversal algorithms on top of this tree. This is the same tree which is we have used for breadth first search. On top of that, I just applied depth first search. Let's run this program and see how depth first search is working. In the pre-order traversal, we have to travel through root, left, and right. If you take this tree, this is root node. First 1, then 2, then 4, 5, 3, 6, and 7. Like that in order, left, root, and right. It will be 4, 2, 5, 1, 6, 3, and 7. And post order means left, right, and root, which is 4, 5, 2, then 6, 7, 3, and finally 1. Let's run this pre-order line by line. I have just created one helper method to execute pre-order algorithm by passing the root node of this tree, right? Okay, now this is my helper method. Here I'm just passing the root node. If you see here, if root node is not null, I'm just executing these 3 lines of code, which means first we have to visit root node, right? Then we have to visit left node, left, and finally we have to visit right node, right. Let's run through this algorithm. Let's take this root node 1. We are just passing this root node to pre-order helper. If we run here, root node will be 1. Root node is not equal to null. Then it will come and execute this SOP. Means it will print 1. I'll just write it here. It will print 1 in this line, right? Again, we are calling the same method by passing root.left, which is this node. For the next call, pre-order helper node root will be 2. If you are coming here, root not equal to null, so again it will come here, it will print root value. So now this is the root value, right? So it will print 2 now. Clear? Then this is the root dot left means this value. So again we are calling the same method by passing the root dot left, which is this, as a root for this same method. So now we are here, root node is 4. Root node is not equal to null, and it will print root value, which is 4. We have printed root node value, which is 4. And next call will be calling the same method by sending root.left, which is null here, because this is current node now. For this current node, we don't have left as well as right. So if you are passing left root.left, it will be null, so it will be skipped, and then it will execute this line. Root.right, again it's null. This root value will be null, again this will be skipped. So we have completed the full call for this root node 4. So already we have paused our execution for the root node 2 from here. We came for 2 from this line, right? So we have to execute this line for this node. So we are calling the pre-order helper method by passing root.right. So root is 2, root.right means 5. We are sending 5 to this root node. Root not equal to null, so it will come here, it will print root value 5, so it will be 5, right? So we have completed the execution for this root node. For this we are coming from here, right? So this line will execute for this node. We are passing root.right, which is 3, and this root will be 3, and it's not equal to null, then we have to print 3. And now
root dot left, which is 3 dot left 6. We are sending 6 here, that will be root now, so 6 will be printed now. And then for the 6, root dot left is null and root dot right equal to null, so it will be skipped. And again we are coming for root node 3. For the root node 3 we are passed from here. Now we have to execute this line. So pre-order helper root dot right, which is 7. If we are sending 7 here, it will be passed here. 7 is not equal to null and we are just printing root node value, which is 7. And for the 7 we don't have left node and we don't have right node, so it will be skipped from here. So that's it. We are done with pre-order traversal. So final output will be 1, 2, 4, 5, 3, 6, 7. Here we are getting that. This is pre-order, right? If we travel through the in-order, logic will be same, but traversal order will be different. If you see here in pre-order, root node first, then left node, then right node, right? But instead of that, here in pre-order, first left node, then root node, and finally right node. First left node, then root node, then right node. So it will print 4, 2, 5, 1, 6, 3 and 7. Like the same way for the post order, again logic will be same and order will be different. Here order is left, then right, then root. So first left, then right and root. So it will print 4, 5, 2, 6, 7, 3 and 1. So this is how depth first search will work in all the form of traversal algorithm. See you guys on the next video. Hey guys, welcome back. This is quick wrap up for whatever we have discussed in this unit. In this unit, we have discussed about tree data structure. Tree is another type of data structure like linked list, stack and queue. But the difference is linked list, stack and queue and all linear data structure. But tree is non-linear data structure. And we have seen about binary tree. Binary tree is derived from tree. We can say like if tree met certain condition which is applicable for binary tree, that is called binary tree. The condition is each node should have up to 2 child nodes, creating the branch of the tree. The 2 children are usually called as left and right nodes. Note that tree should not have more than 2 children. And next we have seen binary search tree. We don't have any restrictions while adding the node into binary tree. But in binary search tree, we have some restrictions while adding the data into it. That is, when we add child for any node, higher value child node should be in right child of the parent and lower value child node should be in left child of parent node. And finally, we have seen traversal algorithms. We have discussed about 2 traversal algorithms to travel over the tree data structure. One is breadth first search and another one is depth first search. In breadth first search, we have to visit the node based on the breadth of the tree, means horizontally. So in breadth first search, we have to prioritize the node by visiting all the node on the same level before we move down to the child node. In depth first search, if we would like to go to child of any node, we have to complete the full left subtree of that node before we move to the right child node. Means we have to go depth of the left subtree before we move to the right subtree. Hey guys, welcome to the new unit. In this unit, we will discuss about graph data structure and its real-time application, something like where we will use it in real time and how we will use it and how we will represent the graph. Graph is a pair of node and connections. I will just draw some circles. I will call it as A, B and C. These circles are nodes and these nodes are connected with line. And we can call this as connection. It's just a connection between nodes. We will refer these nodes as vertices and we will refer this connection as edges. So this is graph. So basically a graph consists of a finite set of vertices and set of edges which connect a pair of nodes. And a graph is a non-linear data structure like tree. So I will draw some graph here. If you see this graph, it's valid one. These are nodes and these are the connections. And here is the another valid graph. Here the difference is nodes are same, but connection between the nodes are different. And here is the another one. It's different looking than first two graphs, but still it's a valid graph. The same number of nodes and same number of letters, but different connections, different edges. And we have talked about linked list a lot. In a linked list, nodes that are connected in a linear fashion. And we have talked about tree as well. You can feel like same look as graph, but graph and trees are not same. Tree is one type of graph, but in tree data structure, the parent and root node is only one, and we have only two children of each node. But in graph, we don't have parent and child node concept. These are just a nodes. Each node connected with another node in any direction. That's it. If you see this graph, there is no parent, there is no starting point, and there is no any entry point. These are just nodes that are treated equally, and they are connected in different way, and those connections can mean different things. Hey guys, welcome back. So we have talked about nodes and connections between nodes. Now let's talk about type of graph. First of all, we have to discuss about some terminology. In the graph, we have talked about nodes means a circle which is holding some value. But in technically, we can call it as vertex or vertices. We can interchangeably the name vertices or vertex or nodes when we discuss about graph. But there is technical term unlike Wikipedia. You will see it as vertex or vertices. Let's take this graph. See, this is vertex A and this is vertex B and this is vertex C. These lines, those are connecting the vertex is connection. Technically, we can call it as edges. This is an edge from A to B, from B to C, and so on. Let's take this tree. So, for a tree, to be a tree, it's just a bunch of nodes with a bunch of connections. However, there is only one path from given node to another. If you take this tree from node K, you want to go to node A, means there is only one path, K to E and E to B, then B to A. But in graph, we have many paths to reach from one node to another node. Let's take this graph. Here, if you want to go from E to D, there is path from E to A and A to B and B to F and F to D. Or we can go like E to A and A to B and B to D. This is a small graph and this is not a right example for more path to reach one node to another. But the thing is, unlike tree, graph are more ways to reach destination. So coming to type of graph, there are two kinds of graph, that is directed and undirected graph. And weighted and unweighted graph. Till now, what we have discussed and what the example we have used to discuss about the graph is undirected and unweighted graph. Means we haven't used any direction when we represent the edges, and we haven't given any number to the edges to associate with. I mean weight. Let's talk about directed graph. Just take this simple graph. If you take this graph, here we can travel from A to B as well as B to A, because we haven't specified any direction to the edges to travel between nodes. Similarly, we can travel from A to C or C to A. If we given direction to the edges like this, it's basically meaning that we can travel from A to B, but we could not travel from B to A because it's directed from here to here. It's called directed graph. Similarly, we can travel from A to C, but we can't able to travel C to A. Let's take this graph. It's directed graph, means we can travel from B to A, but not A to B. Here there is no way to reach from F to A because there is no direction to go from F to A. This is the basic idea of how Google Maps work. When you search for some place to go, based on the allowed path to travel, it will show the routes to you. So if we have direction on the edges in the graph, it's called directed graph. If we don't have direction on the edges, it's called undirected graph. So what about weighted and unweighted graph? It's simple. Each and every edges are associated with some weight. Basically, it's a number. I will just draw some weighted graph. This is weighted graph. Here, let's take edge from A to E. This one. Here the weight of the edge is 10. Similarly, weight of the node from A to B is 8. If we haven't given any weight on the edges, it's unweighted graph. But this one is weighted graph. In real time, again think about Google Map. You might have seen sometimes in Google Map will suggest you that your route is 30 minutes slower than usual. Are you? And it will also suggest some faster route for you. How it's finding the time delay? It's just help of weight of the path, or we can say edges. Just imagine that these weights are presented on these edges or time delay in Google Maps. It will calculate the total time taken from your source to destination by using weights of the edges, means path. Also it will find other available paths for your source and destination, which is less weight than your current route. And for the all available path, it will calculate the weight. Basically for this use case, it's time. And it will suggest you which one is lesser distance. That's all about type of graph. See you guys on the next video. Hey guys, welcome back. So far we have seen graph and what are the types of graph. Now the question is, when we have to graph data structure, means at what scenario we have to use graph. In this video we are going to see some real-time example for where and all we can use graph. First one is social network. Let's take Facebook. In Facebook we are connected with friends, right? How Facebook handle this connection between you and your friends, and how Facebook finds the mutual friend details to you when you look at some of your friends' profile. Think about what data structure Facebook might have used for this. It's graph. Just imagine all the people who is signed up in Facebook or nodes. For example, let's take this node. It's you in Facebook. Let's take another node. It's my profile in Facebook. So I sent you the friend request and you have accepted my friend request. Now you and me are friends, right? Means logically we are making connection between these two nodes. In this case, only you and me. Let's take another node. We can name this Facebook profile as Dan. And think like he is your friend and also he is my one of friend in Facebook. Now graph will be looks like this. And there is one more profile called Kathy. She is also friend of both of us. Fine. And let's take another two profile, Andrew and Jam. Both are my friends. Now graph will be looks like this, right? If you see here, there is no edges between you and Andrew and Jam because you guys are not friends in Facebook. That's why no connection between these three nodes. Okay, fine. Now you came to my profile and looking at mutual friends, means who is friend of you as well as me. Now you can see Dan and Kathy name are mutual friends because we are all four people connected, right? If I go to Dan profile, I can see your name in mutual friends list. But I will not get your name if I visit Andrew profile because you and Andrew are not friends in Facebook. This is one of the finest example for graph in social network. Another great example is Google Maps. If you search for some location to travel, it will suggest you the best route, right? For example, I just get the direction in Google Map from Chennai to Bangalore. These are cities in India. If I look for the direction in Google Maps, it's suggesting 3 possible routes for me from Chennai to Bangalore, and it will show how long distant it is and how long it will take to reach from Chennai to Bangalore as well. Think about this in graph data structure. These 3 parts are nothing but edges, which is connecting more number of nodes. Here, nodes are places we are connecting to go from Chennai to Bangalore, and Chennai is the source node and Bangalore is the destination node. By default, Google Maps will give me the lowest distance path. How it's doing? Because weights are associated with these edges, basically path. It will count all the weight between the places from Chennai to Bangalore for all the possible path and give us the best path for us, which is basically lower weight. Here, weight factor may be distance or time taken to reach one place to another place. Other than this, lots of places we are using graph, for example, networks, internet routing, and recommendation on e-commerce websites and etc. See you guys on the next video. Hey guys, welcome back. If you want to store the sequential data, we can go for linked list, stack, or queue data structure. If you store your data in linked list, we will have the reference of next or previous data. By using the reference, we can access the data in linked list. Or else think about tree data structure. There we have some uniform structure. I mean, we have node and it might have left and right node on it. Basically, a node might have up to 2 nodes, or it may be a leaf of the tree, means no child nodes, and it will not have more than 2 nodes for any parent node. So in tree, if we need to access the data, we can access like node.left or node.right. Somehow we can access the data like this. But think about graph data structure. How we can store the data in graph form, or how we can represent the data in graph for data access. If we search this in internet, mostly people are talking about the 2 ways to represent the graph data structure. One is adjacency matrix. And another one is adjacency list. It's hard to represent the graph data structure other than these 2 ways. Why? Because we can expect one node may connect with more number of nodes. We will start with adjacency matrix method to represent the graph. Let's take this graph. Here node A connected with B and E, and node B connected with A, C and D, and C connected with B and D. Similarly, D connected with B, C and E, and E connected with A and D. Right? To represent this in matrix, I will write all the nodes as row and columns. Let's take A, B, C, D and E as columns, and A, B, C, D and E are rows. First we will take node A and we will check with all other nodes. Let's take this node A. Is it connected with A? No. If it's like this, A is connected with A. But now A is not connected with A, right? So I will represent this as 0 in matrix. And now let's take B. A is connected with B. Yes, it's connected. So it's 1. I will represent the connected node with 1. Now let's take C. Is A connected with C? No. So it's 0. Node A connected with D? No. So this one also 0. And finally, is A connected with E? Yes. So it's 1. Similarly, we will do the same thing for node B. Is node B connected with A? Yes. so it's 1. B is connected with B? No, it's 0. And is B connected with C? Yes, it's 1. Is B connected with D? Yes, again it's 1. And B connected with E? No, it's 0. Now we will check with C. Here C is connected with only B and D. So I will make those as 1 and others are not connected, right? So I will make it as 0. Now let's take D. D is connected with only B, C and E. So we can make B, C and E as 1 and A and D are 0. Like this, E are connected with A and D. So let's make it for A and D as 1. Others are 0. Are you clear on this? Right. So we are just represent the connected node with 1 and a node which haven't connected, we are represent those as 0. This is for undirected graph. Let's take the same graph and we will give some direction for the edges. Here node A is connected with B, but node B is not connected with A. And B is connected with C and D, and this C and D are not connected with B. For this directed graph, we can redefine the adjacency matrix. Let's take node A. Is A connected with A? No, it remains same. And next one is node B. Is it connected with B? Yes. So it will remain same as 1. And A is connected with C? No, it's still 0. And is A connected with D? No, it's 0. And finally, is A connected with E? Yes, it's 1. Let's go for B. Is B is connected with A? No, it's directed graph. It's direction from A to B, not B to A. So it's 0. So we can change it to 0. Like this. Is B connected with C? Yes, so it's 1. And is B connected with D? Yes, this also 1 remains same, that is 1. Is B connected with E? No, it's remains same. Let's take C. Is C connected with A? No. Is C connected with B? No. This is directed from B to C, not C to B. Let's change it to 0. Is C connected with D? Yes, it's 1. And is C connected with E? No, it's 0. And for the node D, is D connected with A? No. Is D connected with B? Again no. Let's change it to 0. Is D connected with C? No. Let's change it to 0. And is this connected with E? No. Let's change it to 0. If we take node E, it's only connected with D. So we will keep this only as 1 and others are 0. So this is how we can represent the graph in adjacency matrix. Now we can see how we can represent this graph by using adjacency list. Let's take this graph. It's undirected graph. See, there is no direction on the edges. So I'll just write down all the vertices here. A, B, C, D and E. In this graph, A is connected with B and E. So we can represent this like A of B and E. It's like a hash map. This is key value pair. Here A is the key and connected with node B and E, which means A is linked with B and E. We can use linked list to represent this. This is node B and we can define another node E. and this node B will refer node E, and E reference will point to null, right? Let's take node B. It's linked with A, D and C. So we can define it's node A, and it will have the reference of C, and C will point to D, and D will point to null. Basically, these nodes are linked together. Now we will take node C. It's connected with B and D. So this is node B, and it's linked with D, and D reference pointing to null. Now we will take node D. It's connected with B, C and E. So this is node B, and it's just linked with C, and C reference pointing to E, and E will be pointing to null. Let's take node E. It's linked with A and D, right? It's A, it's pointing to node D, and D will point to null. This is the way we can represent the graph by using adjacency matrix. We have seen here two ways to represent the graph data structure. So what is the best representation of the graph data structure? Let's compare that in next video. See you guys on the next video. Hey guys, welcome back. Matrix is the one way to represent the graph data structure. In other hand, list is the another way to do the same job. So which one is better? Here we will compare both the things based on certain factor like accessing node and accessing child node and memory. Let's first take accessing data. I will take left hand side as matrix and right hand side list. So accessing the data in array is simple, right? By using the index, we can directly access the element. Matrix is simply a two-dimensional array, right? So complexity of accessing data in matrix is O of 1. Coming to the list, as we have already discussed in list data structure, complexity of accessing the data in linked list is O of n, because we have to travel from the first element to till the element which is we are looking for. So in this case, matrix is the best for access the data compared with linked list. What about accessing child node? From the linked list, we can get where each and every nodes are connected. So from the linked list, it's very easy to access the children's. Let's take this node B. Its children's are C and D. But in matrix, it's very hard to find the children. Let's see this matrix. And for this element, what is the parent? We can't directly say that, right? This node is parent for these child nodes and all, right? So while accessing child node, list is the better option. While we consider the memory, again list is the good option. Take this matrix. Here we have lots of zeros. These and all waste of memory, right? Here nodes that are not connected, we are referring that as 0. But in linked list, we are creating the node only for the available connections between the nodes. So list is the very good option when we consider memory. If we consider iteration speed, again list is the good option, because we have to iterate the list based on the key, I mean node. So in linked list, we will iterate over the keys, but in the matrix, we have to iterate the connected as well as not connected nodes. So while comparing these two, based on the iteration speed, list will be the good option. See you guys on the next video. Hey guys, welcome back. In this video, we are going to discuss about implementation approach for graph. As we have discussed already, graph will have two things. One is vertex and another one is edges. Vertex is nothing but it's just a circle with hold some value, and edges means connection between these nodes or vertices. Alright, in this video we are going to create one graph and we are going to represent this graph in adjacency list. Alright, let's take this class. Here I am having two variables. One is vertex count
So whenever I create graph, I just pass number of vertices. Say for example, if I pass 3 here, means basically I wanted to create this graph with 3 vertices. If I send 10, we are going to create graph with 10 vertices, right? And this is the next variable, adjacency list array. This array will hold the vertex information. So for example, if I send 3, basically vertex 0, 1, 2, right? So this array will have 3 elements. And this array type will be linked list to hold the connection between the vertices, right? And this is the constructor for this class. So whenever I make object for this graph, we are basically creating the graph vertices. This constructor will accept number of vertices. Say for example, if I send 5, we are going to create 5 vertices with this graph. So how we are doing that? We are just iterating 5 times and we are making 5 element into this array. Means basically 5 vertices, right? And see this constructor will create only vertices. It will not make any connection between the vertices. And next one is add edges method. This is the method will make the connection between the vertices, and this method will accept 2 parameters. One is source and another one is destination. Say for example, let's take vertex 0. I'm setting source as 0, destination will be 1, which means we are going to make connection between vertex 0 to vertex 1 or vertex 1 to vertex 0. So this is what this method will do, and this is the utility method to represent our graph into adjacency list way. And this is our main method. Our program execution will start from here. So in this method, I'm just creating one object for this class by passing total number of vertices, which is 5. If I execute this line in our graph, 5 vertices will be created. If you see here, this for loop will execute for 5 times, which is from 0 to 4. For the first iteration, adjacency list array of 0 will be one linked list object, which is basically vertex 0. Like that we are creating vertex 0, vertex 1, 2, 3 and 4. So after executing this line, we are just creating 5 vertices. I'll just represent this here. This one is vertex 0, this is vertex 1, it's vertex 2, and it's 3, and it's 4. See here, we just created vertex. We are not making any connection between the vertices. Alright? Okay. Now I'll represent the same in array. So this array will hold the value for vertices. It's vertex 0, and it's 1, 2, 3 and 4. So totally 5 vertices. Alright. And here we are just making connection between 2 vertices. Here we are passing 2 vertices information. Source is 0 and destination is 1. So by calling this method, we are making connection between these 2 vertices. In this case, we are passing 0 and 1, right? So vertex 0 to 1, we are making connection. We'll see here. I'm going to this add edge method. Here we are passing 0 as a source and 1 as destination, right? So in the adjacency array, this is our array. Here I'm just getting source, means array of 0, which is vertex 0. In this vertex, we are going to add some destination. Here destination is 1. So from vertex 0 to 1, we are making one connection. If we represent in adjacency list, for the 0, we are just linking with one node of vertex 1. It will be like this. Right? In the next line, we are making connection from 1 to 0. So in this graph, from 1 to 0. If I represent this in array, for the 1, we are making one connection for 0. Alright. Now we are going to make connection between vertex 0 to 4 or 4 to 0. So if I call same method again, source will be 0 and destination will be 4. So array of 0 means vertex 0. In the vertex 0 we have to add destination node 4. Here we are creating another node with value 4, right? Like that. Here we are making connection between 0 to 4, and in this line 4 to 0. Here we are already having connection between 4 to 0. If I represent here in the 4, I am making connection with 0, right? And this third line we are making connection between vertex 1 to 2 and 2 to 1. So here source will be 1, destination will be 2, so array of 1, which is vertex 1, and we are adding that into vertex 2. So basically we are making connection between 1 to 2, this one. So from the 1 we are making connection with 2. So for the 1 we are making connection with 2. Right? And here from the 2 we are making connection with 1. So for the 2 we are making connection with 1. Alright, like the way here we are making connection between 1 and 3. So 1 and 3. And here 3 to 1. So first 1 to 3, and for the 3 1. Like that way 1 to 4, 1 to 4. So we are making connection between 1 to 4, and here for the 1 I don't have space here, so I'll just create it here. It's 4, and 4 to 1, and for the 4 1. Like that way 2 to 3 and 3 to 2, 2 to 3 and 3 to 2. For the 2 here we are making connection for 3, and for the 3 we are making connection with 2. Finally 3 to 4, 3 to 4. Here I am just making connection between 3 to 4 and 4 to 3, 3 to 4 and 4 to 3, right? So this is how our graph will be looks like now. If you see here, this is our graph we have created in this program, and this is what we have represented using adjacency list. If I run this program, if you see here, this will be the text representation of this adjacency list representation. If you see here, vertex 0 will have 1 4, vertex 0 will have 1 4, and vertex 1 will have 0 2 3 and 4, 0 2 3 and 4, and vertex 2 will have 1 and 3, vertex 2 will have 1 and 3, and vertex 3 will have 1 2 4, 3 will have 1 2 4 here, and vertex 4 will have 0 1 3, and vertex 4 will have connection between 0 1 and 3. Alright, see you guys on the next video.
Hey guys, welcome back. In this video we are going to discuss about graph traversals. Let's take two cities. It's city A and it's city B. Let's say for example, in city A we have some places P, Q and R, and in city B we have some places X, Y and Z. If we need to go from city A to city B, for example from place B to place Z in city B, first of all we should have a route to go from P to Z, else we can't able to go, right? Route means this node should have connection from P to Z. Let's say for example P connected with Q and Q connected with R, and place R in city A should be connected with place X in city B, and X should connected with Y and Y should connected with Z. If it's like this, then only we can able to go from P to Z. Am I right? If there is no connection between R and X, then how it is possible to go from this city to and this city? It's not possible, right? Imagine this as graph, and these places are nodes of the graph. If we need to travel from P to Z, nodes should be connected such a way, else we can't able to travel. In this example, we haven't any connection between R and X, right?
So imagine that we have connection from Q to X. Now we can able to travel from P to Q, Q to X, X to Y, and then Y to Z. Suppose if we have connection from the node P to node Y, instead of using the path P, Q, X, Y, Z, we can go by P to Y and then Y to Z. So here we have two possible paths to reach from P to Z, but we have to choose the one which is short one. Alright, so to view the node or to source some node from the graph, we have to travel throughout this graph like tree traversals. We have traversal algorithm for graph 2. Based on the order on which node is visited, graph traversal algorithm are classified into two categories. One is breadth first search. And another one is depth first search. Breadth first search and depth first search are general technique to travel or search for the particular element in the graph structure. Hope you remember that these are the same technique we have used to travel or search in the tree data structure. Let's take this tree. If we are traveling through this tree using breadth first search, first we will prioritize the node by visiting all the node on the same level before we move down to the child node. If we travel by using breadth first search algorithm, we will travel horizontally, means first we will start visiting the tree based on the breadth. It's basically width, or we can say like level by level. It's first level and it's second level, and this one is third level. So we can travel like 10, 7, 15, 5, 9, 12 and 16. But if we use depth first algorithm, we will go to the depth of the tree before we move to the siblings. If we would like to go child of any node, we have to complete the full left subtree of the node before we move to the next child node. In this tree, 10 is the root node. If we are going left, we have to complete this full left subtree of the node 10. We should complete this left subtree in full depth, or in other words, we should complete all the grandchildren of 10 along with this path before we go into right child of 10. And once again, we have to visit all the grandchildren of right subtree of 10. So basically, we have to complete right subtree. Here, node 10 having two children. One is node 7 and another one is 15. If we start with root node 10, we will go with left or we will go with right. But always, we will prefer to start with left. Now, in breadth first search, we will go to node 15 for next because it's same level. But in depth first search, we go to depth of this node and complete it first. Then we will come to node 15. So here for the node 7 having two children. So we have to complete the children. Even if children's having grandchildren, that also we have to complete first. So we have to go in depth of those children. After that, we have to come to this node 15. If we take any node here, let's take root 10. Whatever branches are coming from this node, all are the same level. In this tree, it's two nodes. Obviously, we will have maximum of 2 branches for the tree data structure. But in graph, it's not like that, right? We have more than 2 branches for single node in graph. So the basic idea is, if we travel using breadth first search in graph, we have to visit same level node first. Then we have to go to child. But in depth first search, we have to go depth in the node, like child and grandchild like that. Let's take this graph. First of all, it's director graph, meaning we can able to travel based on the direction provided on the edges. For example, we can go from node 0 to node 1, but we can't able to go from node 1 to node 0 because there is no direction over there. Okay, now let's take this graph and travel using breadth first algorithm. Here we can take node 0 as the source node. So we can start from here. If we take node 0, it has 3 branches, node 1, 2 and 3. These 3 nodes are same level. In breadth first search, we have to complete this level first and then we have to go depth of the node 1, 2 and 3. Okay, now we will start from node 0. First we have to go from node 0 to node 1. Even though we have node 2 and 3 are at the same level, we have to visit node 1 because it's the shortest path
compared with other two nodes. And next traversal is node 0 to node 2 and then node 0 to node 3. Right, now we have completed first level. Then we have to go for second level. We have visited node 1 first, right? So we can go with that child node. For the node 1 there are two children, 3 and 4. Means node 3 and node 4 are the same level. We have to visit these nodes before we move to the child of node 2. Here with these two nodes, node 3 is the shortest one. So our next visit will be node 3. And next we have to visit node 4. Now we have done with node 1, node 1's children's. Now in the same level we have to go for node 2 and node 3. Node 2 and node 3's children's. Let's take node 2. It's having only one child, which is node 4. So we have to visit node 4. And next we have to visit node 3 and its children's. For the node 3 also we have only one child, that is node 4. That's it. So we have visited all the nodes in the graph by using breadth first search. Now we will do the traversal by using depth first algorithm. Let's take this same graph. Again we will take node 0 as the source node. So that we will start from node 0. Here from the node 0 having three children, that is node 1, 2 and 3. These are on the same level. Since node 1 is the shortest than other two nodes, first we will travel from node 0 to 1. And before we visit node 2 and 3, we have to finish node 1 in depth. That's what depth first algorithm says, right? Now we are in node 1 now. Node 1 also having two children, that is node 3 and node 4. So we can visit node 3. And before we move to node 4, we have to complete child of node 3. So now we have to visit node 4 from node 3 and go back to 3, and from 3 go back to 1. Now we can visit second node of node 1. So visit from node 1 to node 4. Now we have finished from node 0 to node 1 and its children. Now we have to take care of other two children of node 0, that is node 2 and node 3. So we can visit node 0 to node 2 and go depth into node 2 before we move to the node 3. So node 2 to node 4 and finally node 0 to node 3. This is how we can travel in the graph data structure by using breadth first search and depth first search algorithm. There is one amazing website to understand the data structure by visualization, visualgo.net. I'll just hit this URL in my browser. It's going to homepage of this website. If you see here, there are almost all the concepts in the data structures are available here for visualization. I will recommend you to take a look on this website and try out some visualization for the data structures and algorithm, which is we are discussing in this course. Let's search for breadth first search in this search box. It will give you the result. From that we can choose graph traversals, and from here I'm choosing breadth first search. So it will give us visual representation of breadth first search algorithm. As well as here you can see the execution of this algorithm as well. When you refresh this page, every time we will get new graph. I will recommend you to spend some time with this. See you guys on the next video. Hey guys, welcome back. In this video, we are going to discuss about graph traversal implementation approach. As we have already discussed, we have two approaches to travel over the graph, right? One is breadth first search and another one is depth first search. In this video, we are going to implement breadth first search. And already we have discussed how to implement graph and how to make the connection between the vertices within the graph. Let's take this class. I have created one class with name of graph traversal. This is basically breadth first search. I just created one graph with 4 vertices. Starts from 0, 1, 2 and 3. And I'm making some connection between these vertices. Just I will draw this here for clear understanding. Right? And whenever we implement graph, we just did the same thing, right? We just created vertices, then we are calling the add edges method to make the connection between the edges, right? But here I make some small difference. If you go for graph implementation, whenever we make the edges from the source to destination, we are making the connection from source to destination as well as destination to source. Here we are making connection from source to destination, and here destination to source. Means if we send source as 0 and destination as 1,
we can able to travel from 0 to 1 as well as 1 to 0, right? It's like a undirected graph. But here I'm just making some direction, means in this add edges method I just creating the connection from source to destination, not destination to source. Means if I send source as 0, destination as 1, we can able to travel from vertex 0 to 1, and we can't able to travel from 1 to 0, right? So here we are making connection from 0 to 1 and 0 to 2 and 1 to 2 and 2 to 0. If you see here, we can able to travel from 0 to 2 as well as 2 to 0 because we have connection such a way, and finally 2 to 3. I'll just represent the same in adjacency list. Here 0 is connected with 1 and 2, and 1 is connected with only 2, and 2 is connected with 0 and 3, and 3 is connected with nothing, right? So we have created the graph and we have created the connection between the vertices inside this graph. Now I'm going to call breadth first search method by passing source vertex. Means we have to start our traversal from source vertex. In this case I'm sending 0, so we have to start traversal from 0. If you take this graph, in the breadth first search, from the source we have to complete all the same level vertices. In this case, for the source 0 we have 1 and 2 in same level. So first we have to complete 1 and 2. So first visiting node will be source node, which is 0, and from the 0 we can travel 1 or 2. Since 1 is shortest path, I'll choose 1. So 1. And next visiting node will be 2. Now we have completed one level, right? So from this one level again go to 1. From the 1 child we have to go. From the 1 we have child as 2. This one is already visited, so I go back to 1 again and again go back to 0. From 0 next node is 2. For this 2, what is child node? 3. So next visiting node will be 3. And from here 3 to we don't have any child node. That's it. We have completed our traversal algorithm, right? So this is the final traversal list, which is 0 to 1, 2 and 3, right? We will run this program in debug mode. So before I run that, I'll just put some breakpoints here. So here idea is I'm just creating one variable to keep track on visited nodes. Means if we visited some vertexes, we should not visit it again, right? So for that I'll just create one variable called visited. Here we are going to track visited node informations, and this is one variable as type of linked list to travel over the vertexes, right? So initially this visited will be false for all the node, means all the vertexes. Why? Means we haven't visited yet any node, right? So this will be false. So our idea is first whatever node we are sending as a source, we have to visit that node first, and we have to add that into the queue, and we have to get the information from the adjacent matrix representation. For example, for this vertex 0 we have connection from 1 and 2, so we have to visit 1 and 2 after the source node. So for that we are iterating one by one based on the connection, which is we have created adjacency list. For example, if source is 0, this adjacency list array will return 1 and 2. So we have to travel based on that, right? I'll just run this program in debug mode. Here we have created graph and we have created connection between the vertices within this graph, and I'm sending 0 as the source vertex for this method. Now all the visited node will be false initially, and I'm making source node as visited, and I'm adding this source node into queue. So in this visited list we have only one node is visited now, which is node 0, and our queue will have only one element, which is source vertex, source node, right? I'm iterating what and all elements we have it in the queue. Based on that, we will iterate one by one. From our queue, I'm just removing the element we have and I just printed that. So initially we had source element, that is 0, we removed from the queue and we have printed that. That is what we can see here. And next we have to get the connection for this source node from the adjacency list representation. So this will return 1 and 2 because this node 0 connected with 1 and 2, right? It will return these two elements. Now this iterator will have two content within it, right? So we have to visit one by one. So our next visiting node will be 1 and after that it's 2, right? So for the first iteration, here will come node 1. We have to make it as visitor. Before visit this, we have to check whether it's already visited or not. If it's already visited, we have to skip this. Since 1 is not visited yet, it's true. Now it will come here. Now we are making this 1 as visited node and we are adding it into this queue. And in the next iteration, next node will be 2. So this n will be true now. We are checking whether this 2 is visited or not. It's not visited yet, so it will go inside and we are making this 2 as visited node and we are adding that 2 into queue. Alright, that's it. Only we have 2 nodes that we have completed. Now in our queue only 2 nodes we have. First element will be 1 and second element will be 2. In the queue, this will be the head element, right? Whenever we poll means basically dequeue. So whenever we dequeue from this queue, head element will be removed, right? So next element will be removed is 1 and we are printing that. This is the removal process and then we are printing that element which is 1. And for the 1, we have only node 2. So this adjacency representation will give 2. We have to iterate this. In this visited list, we already have 2, right? So it will be skipped. Right? Now our next dequeue will be 2. We are removing 2 and we are printing 2. Right? So as of now we have visited first level 0, 1 and 2. 0, 1 and 2. Right? And for the 2, adjacency representation will return 0 and 3. 0 and 3. Right? If we come here, first element will be 0. 0 is already visited, right? So it will be skipped. And next element to visit is 3. It's not yet visited, so it will go inside. So we are making this as visited node and we are adding it into the queue. Now we have only one element in queue, which is 3. So we have to remove that and we have to print that. That's it. We got 3 here. So we have completed our visit. So our final result will be 0, 1, 2 and 3. So this is how breadth first search algorithm will work. So now we will see how depth first search algorithm will work for the same graph. If we travel through the depth first search in the same graph, first source node will be visited, which is 0, and we have 2 nodes for this source. One is 1 and another one is 2. From here we can go 1 because it's the shortest path compared with 2, right? So next visiting node will be 1, and from the 1 we have to go to the child of 1 before we go to the next child of source 0, right? So for this one child node is 2, so our next visiting node will be 2, and we have to still go depth into this node 2. For this 2, child node will be 3, so our next visiting node will be 3. From 3 go back to 2, and from 2 go back to 1, from 1 go back to 0. Now we have completed in depth of node 1. So we have to go visit next child of this source node 0, which is 2. 2 is already visited, so we can skip. From the 2, next visiting node will be 3. So this is also already visited. So that's it. So we have completed depth first search traversal, right? So here I'll just comment it out, breadth first search algorithm. I'm just calling depth first search method by passing source node as 0. Right? This is also somewhat similar to breadth first search algorithm. Let's run this program in debug mode and we'll see what is happening. In the depth first search, I'll just put some breakpoint here as well as this helper method. If you see here, we are just sending vertex 0 as the source node. We are calling one utility method for the depth first search. If we go over there, same thing. Initially we haven't visited any node, right? So all the visited node will be false initially,
whenever we send source node, we are making source node as visited 1. So, and next we are printing that source node. So it will be 0. And from this adjacency list, we have to get the linked nodes information. So for this 0, linked node will be 1 and 2, right? So it will return 1 and 2. For the first iteration, 1 will come here, so n will be 1. And we are checking whether this 1 is visited or not. If it is not visited, it will go inside. Again, recursively, we are calling this DFS util method. So now vertex will be 1. And we are making this as visited, and we are printing that. It will be printed here. Now for this 1, we have node 2 as connected node, right? So it will return 1 node, which is 2. Our next visiting node will be 2. We are checking whether it's visited or not. It's not visited, so it's going inside. So now we are visiting that. So it will be printed 2 here. For this 2, adjacency list will be 0 and 3. 0 we already visited. So our next visiting node will be 3. So it will call DFS util method by passing vertex 3. And we are visiting that and we are printing that. That's it. Now we have completed depth first search traversal. Hey guys, welcome back. This is quick wrap up for whatever we have discussed in this unit. In this unit, we have discussed about graph data structure. Graph is pair of node and connections. In graph, nodes are vertex and connection between the nodes are edges. You can feel that graph and tree are same look, but actually graph and tree are different. Tree is one type of graph, but in tree data structure, the parent or root node is only one, and we have only 2 children for each node. But in graph, we don't have parent-child node concept. There are just 10 nodes, each node connected with another node in any direction. That's it. And we have discussed about different type of graphs, directed and undirected graph, and weighted and unweighted graph. Directed graph means graph edges will have additional information, that is direction. So edges are connection between the vertices, and direction of the edges represents that which way graph will travel. If vertex A and B connected with directed edges from A to B, we can able to travel from vertex A to vertex B, and we can't able to travel from vertex B to A. And undirected graph means edges without any direction, so we can travel from vertex A to B as well as B to A. And weighted graph means graph edges will have some additional information, that is weight. So weight means edges are associated with some number. In real time, it may be a distance or time or whatever it is. And unweighted graph means edges will not have any values, means all the edges are same weight. And finally, we have discussed about traversal algorithm for graph. Like tree, we can use breadth first search and depth first search algorithm to travel over the graph. For these two algorithm concept is same for graph and tree. Breadth first search means we have to complete the same level first before we move to the child node. Depth first search means we have to go depth of the node before we move to the next same level node. Hey guys, welcome to the new unit. In the last unit, we have talked about graph data structure and how we can travel over the graph. In this unit, we are going to talk about what is meant by shortest path and what is the best algorithm to find the shortest path in graph. So what is meant by shortest path? It means shortest distance between two vertices in graph. If we take maps, shortest distance from city A to city B. We might have hundreds of routes to reach from city A to city B, but shortest path means shortest distance route to reach city B from city A. Let's take this simple graph. Here we have 3 nodes, A, B and C. If we want to move from A to B, what are the available options? Whether we can go A to B or A to C and then C to B. Here what is the shortest path? A to B or A to C and then C to B. This edge associated with weight of edge, and A to C is 2 and C to B is 3. Imagine these are the places in some city, and these weights associated with edges, basically its path or distance between the places. Now we are in place A and we need to go to place B. Here distance between place A to B is 8 miles. Like that, from place A to C is 2 miles and C to B is 3 miles. So which way or route we will prefer to go place B Obviously A to C and then to B, right? Because it's only 2 plus 3, which is 5 miles by this route. If you choose this route, it's 8 miles. So here this is the shortest path. While finding the shortest path, we should consider weight between the source and destination. It's not a matter how many nodes we are passing while traveling from one node to another node. In real time, weight factor may be a time, distance or size, whatever it is. While finding the shortest path between two nodes, we have to use weight to identify that. It's very simple graph so that we can easily identify the shortest path. Think about millions or billions of nodes and we might have millions of paths between one node to another node, right? Such a case is very hard to identify the shortest path. So we have to choose the right algorithm to find the shortest path in the graph. Hey guys, welcome back. In this video, we are going to discuss about Dijkstra's algorithm. Dijkstra's algorithm can be used to determine shortest path from one node in the graph to every other node within the same graph. Let's take this weighted and undirected graph. Let's take our target would be A to E, meaning that we are going to find out shortest path to reach from vertex A to E. There are many ways to reach from vertex A to E. We can use this way or we can use this. Since it's a simple graph, we may have 4 or 5 ways to reach source to destination vertex. But think about millions of vertex in the graph. There are billions or trillions of ways to reach from source to destination vertex. Okay, now let's come into Dijkstra's algorithm. Dijkstra's algorithm requires some initial setup. But before we get into that, let's take a quick look at steps and rules to run Dijkstra's algorithm. Rule number 1. Whenever we try to visit new vertex, we have to choose the vertex which is having small distance or weight. Let's say for example, now we are in vertex B. From vertex B, we have 4 options to go, whether we can visit A or C or D or E, right? But we have to choose vertex C as the next visiting vertex because compared with other vertexes, this vertex is small distance, right? And rule number 2 is, once we have moved the vertex that we are going to visit, we will check each of its neighboring vertexes. And rule number 3 is, for each neighboring vertex, we will calculate the distance or weight for the neighboring vertex by summing the cost of the edges, which means we came B to C. And for the C, we have 2 options, that is A and D. For example, we came from B to C, so it's already 1, and now C to D is 2, so 1 plus 2, which is equal to 3. And rule number 4 is, if the distance or weight to a vertex is less than known distance, we will update the shortest distance. These are the rules we should follow till end of the algorithm. I will take table structure to mark the progress of the algorithm on every step. Let's take vertexes in the first column. And shortest distance from A is the second column. Because we are going to travel from A to E, right? That's why we have taken shortest distance from A. And the next column is previous vertex. This column is to track from where we came. Okay, let's write down all the vertexes in this column: A, B, C, D and E. Our initial point is vertex A. Initially, we know the distance or weight only for vertex A, which is 0, means distance between A to A. Other than this, we don't know the distance of other vertexes, right? So let's put as infinity for other vertexes. As I said, these are the initial setup to run Dijkstra's algorithm. And one more thing we need to do before start algorithm. We need to keep on track visited vertexes. Algorithm will complete once we are visited all the vertexes in the graph. So we need to keep track on whatever nodes we are visiting. When we start out, we haven't actually visited any node yet, right? So visited list will be empty as of now. Once we start visiting the vertex, we will keep adding the visited vertexes here. Okay, now we are ready to start. Keep in mind the 4 rules which we have discussed. We are going to follow them in step by step as we work through each vertex in this graph. Okay, now our starting visiting vertex will be A because it's rule number 1. We have to choose the vertex which is having small distance first. In this table, A is the smallest distance. Obviously 0 is lesser than infinity, right? So we have to visit A. We can add it in the visiting list. Next, we will examine its neighboring node. It's rule number 2. And calculate the distance to them from the vertex that we are currently looking at. It's rule number 3. Currently we are in vertex A. Vertex A having 2 neighbors B and C. The distance of the node B is 7 and the distance of node C is 3. It's calculated based on the rule number 3. We came to B from A. A's distance is 0. So 0 plus 7 which is 7. And for the C, 0 plus 3 which is 3. So distance to B is 7 and distance to C is 3 from A. So we can update the table with these values because now we know that shortest path from A for these nodes. Here B value is 7 and it's lesser than infinity, right? So we can update this column for B is 7. And similarly C's distance is 3. It's less than the infinity, so we can update this as well. Since we need to keep track of where we came from to get this path, we will update the previous vertexes of B and C to A. Since that's where we just came from, so what is our next new node to visit? As per rule number 1, we have to choose the node which is having small distance. In this case, our next new node will be C because its weight is less than B. So we can add C in the visiting list. Now we are in node C. We will repeat the same procedure as we did earlier. And now we have to check its neighbors. C's neighbors are A, B and D. We already visited A, so we can ignore that. So we have 2 options now. One is B and another one is D. Now we can calculate the distance to B and D from A through C. So distance of B is 3 plus 1 which is 4. It's rule number 3. And already knowing distance to B is 7 from A, right? As per rule number 4, we have to update the existing distance once a new distance is less value than that. So here our new distance is 4, which is less distance from existing one. So we can update 4 here for this shortest distance. We came from C. So I'm updating this as well in the previous column. Similarly, distance to D is 3 plus 2 which is 5 and this is the less than infinity. So I'm updating this as well in this table. And from where we came to D, it's C. So till now we have completed node A and C. So what is the next node to visit? In this table, what is the next shortest distance from A except A and C, because these 2 nodes we already visited. So what is our next new node to visit? As per rule number 1, we have to choose the node which is having small distance. In this case, our new next node will be B. We can take B as the next visiting node. So I'm adding B into visiting list. So for B, what is the neighbors? C, D and E. We can ignore C because we already visited that. So what's the distance to D from A through B? 4 plus 2. It's 6. Note that we should not consider this value because we already found the shortest distance to B from A. It's 4. So we have to use this shortest distance, not 7. So what's our table value for already known shortest path to D? It's 5. So whatever we found, it's larger than what we have already. So we no need to update the shortest path in this table for D. and previous vertex is also same. It's C. We no need to change. And what about node E? Its shortest distance is 4 plus 6. It's 10. 10 is less than infinity, so I am updating the shortest path for E is 10. And where we came from? It's B. So till now we have visited A, B and C. And what is the next node to visit? Unvisited nodes are D and E. We can pick D because it's shortest distance than E. For D, neighbors are C, B and E. C and B already we visited, so we can ignore that. And the distance to E is distance till D 5 plus 4. It's 9. It's less value than already we found. So I am updating the shortest distance as 9. And previous vertex is D. So till now we have visited A, C, B and D. Only left is node E. For node E, neighbors are B and D. That we are already visited. So we are done. None of the nodes neighbors we need to examine. Since every other vertex has already visited, we can mark E as visited node as well. Now we are actually completely done with running Dijkstra's algorithm on this graph. We have crossed out a lot of information along the way as we updated and changed the values in our table. Let's take a look at nicer, cleaner version of this table with only final result of this algorithm. From looking at this table, it might not be complete, obviously, but we have actually got every single shortest path from our starting node available here. We need to find the shortest path from A to E, but this table will allow us to look up all the shortest path. So we need a shortest path from A to E. Here we have shortest path from one node to another, meaning that let's take this node E. We come from D, that is the shortest path. Even though we have other options to come E, we found that coming through the D is shortest distance. I will add this in the stack and I will retrieve it later. Let's take this stack. Let's push this E into the stack. So it's added here, and previous vertex for the E is D. So let's push D into the stack. And D's previous vertex is C. So push C into the stack. And what is the previous vertex of C? It's A. So push it into the stack. What is the previous vertex for A? Nothing, right? Because it's the source. Now we have added all the vertexes in the stack. If we pop out the element from the stack, we will get the exact result what we are looking for. Stack is last in first out, right? Means the last element which is we have pushed to stack will come out first. If I pop out the stack, A will be come out from the stack, and for the next pop, C will be come out, and for the next, D, and finally E. So the result will be A, C, D, E. So this is the shortest path to reach from A to E, that is A to C, C to D and D to E. See you guys on the next video. Hey guys, welcome back. In this video, we are going to discuss about another alternative for Dijkstra's algorithm to find the shortest path in the graph. A-star algorithm is one of the best and popular technique used in pathfinding in graph. It's really a smart algorithm which separates it from the other conversational algorithms. Or we can say like the A-star algorithm is an extension of Dijkstra's algorithm to find the shortest path between the nodes. And A-star algorithm requires a heuristic. It is defined using heuristic value for the distance. We will get the heuristic value from heuristic function. A heuristic function is a function that calculates an approximate cost or a distance to the problem. For example, the problem might be finding the shortest driving distance to a point. A heuristic cost will be straight line distance to the point. It's simple and quick to calculate. The true distance would likely to be higher as we have straight to road and it's much harder to calculate. Let's take this graph. We have used this same graph for Dijkstra's algorithm also. For clear understanding, I just added some direction to the edges of the graph. Let's take node A is the source and E is the targeted node. Now we are going to find the shortest path to reach from A to E. So before we start the algorithm execution, we need to find heuristic cost or distance for all the nodes. Heuristic cost is just an imaginary distance to the targeted node from current node. As of now, I will just imagine that heuristic cost for A to E is 10 and heuristic value for C to E is 4 and for B to E is 3 and heuristic cost for D is also 3 and for E to E obviously it's 0, so it will be 0 because from E to E is 0, right? It's just imaginary cost from that node to destination node. If I draw this graph in one A4 sheet and I can find the distance from the A to E by using any measurement calculator like scale 2, just you can get some imaginary distance, that's it. Now we are ready to start algorithm execution. We have a graph and its heuristic cost for all the nodes. In A star algorithm, the formula to find the distance from one node to another node is, which is f of n equal to g of n plus h of n. Here f of n means total estimated cost of the path through node n and g of n is cost so far to reach node n, means here g value for C is 3 and g value for B is 7 and h of n means estimated cost from n to destination node. This is heuristic part of the cost function, so it will be like guess. Say for example, f value for B is g plus h, that is this 7 plus h value will be 3 for B. So 7 plus 3, that is 10. Okay, let's take source node A. From A we can go for C or B. Let's take C first. So f of C will be g of C plus h of C, right? So here g of C will be 3, means from A to C is 3 and h of C will be 4. Here you can see h value for all the nodes. So A to C distance is 7 and we have to go for A to B, which means g of B plus h of B. Here g of B is 7 and h of B is 3. So 7 plus 3, which is 10. So A to B distance is 10. We can store this in priority queue. I hope you remember that priority queue will be the same as normal queue, but it stores the value in ascending order. If we store this in priority queue, A to C will be stored first element because it's 7, which is less than A to B, and the next element A to B, which is 10. So now our queue will be look like this. Now we have completed A to C and A to B, and we have to continue our algorithm till we reach the node E in all the available pods. So as of now we are completed till this. Now we will take A to C and from C we can go for B or D. Let's calculate f of D, which is g plus h, that is 3 plus 2 plus h value for D, that is 3. So 5 plus 3, which is 8. And for A to C, C to B is g of B plus h of B. Here g of B is 3 plus 1 plus h of B, that is 4 plus 3, it's 7. So A to C to B will be 7 and A to C to D will be 8.
So A2 C2 B will be 7 and A2 C2 D will be 8. And now we can take A2 B path. So B is having two nodes, which is D and E. So we have to find out the distance for A2 B2 D and A2 B2 E. Let's take A2 B2 D. For this, J is 7 plus 2, which is 9, and H value for the D is 3, so it's 12, means A2 B2 D is 12. Now let's take A2 B2 E. For this, J will be 13 and its heuristic table value for E will be 0 because it's destination node, right? So distance for A2 B2 E is 13 plus 0, which is 13. Now if we store this 4 path in the priority queue, if you see here, 7 will be the less value than others, right? So this will be stored as the first element in the priority queue. So A2 C2 B 7 and the next element is 8, right? So A2 C2 D 8 and next 12, which is A2 B2 D, and finally this 13 value A2 B2 E. Again we can continue our algorithm execution from where we left. We will resume with A2 C2 B, and from the B we have two options to go. One is D and another one is E. So let's take A2 C2 B2 D. Distance is 3 plus 1 plus 2, which is 6, and heuristic value for D is 3, so 6 plus 3, which is 9. And now let's go for A2 C2 B2 E. Its G value is 10 and H value for E is 0, so 10 plus 0 is 10. So distance for A2 C2 B2 E is 10. Let's take A2 C2 D. From D we have only one option, it's E. So A2 C2 D2 E is 3 plus 2 plus 4, which is 9, plus H value, that is 0. So distance of A2 C2 D2 E is 9. And next is A2 B2 D. Here D is having only one option to go, it's E. So for this, G value will be 7 plus 2 plus 4, which is 13. Now let's take this last element, A2 B2 E. It's already done, right? Because from the source to destination we already completed, which is A to E. So we can ignore this. Now our queue will be like this. If you see here, again it's ordered based on the values 9, 9, next 10, then 13, 13. Alright. If you see here, we can ignore last 4 elements in the queue. Why? Because we are already done from source to destination nodes. Means A to E we have completed. Only remaining thing is first element. So let's take A2 C2 B2 D. D is having only one option to go, which is E. So G value will be 3 plus 1 plus 2 plus 4, which is 10. And H value will be obviously 0, right? So now this one also done from source to destination. So now our priority queue will be looks like this. This 9 will be in first element, next 10, again 10, 13 and 13.
So this queue is ordered based on the shortest path from A to E, right? It clearly says that the shortest path from A to E is A to C, C to D, and D to E. This is how A-star algorithm will work. Hey guys, welcome to the new unit. In this unit, we are going to cover search algorithms. Before we move to the search algorithms, we will just understand what is meant by searching. We are using data structure to store the collection of informations. Only storing is not sufficient, right? Our ultimate aim to store the information is for retrieve it in future. Am I right? Otherwise, there is no use of storing the data. To retrieve the information again from the data structure, you have to search for the information from the data structure, right? Think about your book shelf. There you might have 10 or 20 books. If you need a particular book, you have to search it from the book shelf. We already talked about algorithms. Hope you remember that algorithm is the efficient or best way to do the things. Like here, searching algorithms. Based on the book's arrangement in your bookshelf, it will be easy for you to search for a particular book, right? In this video, we are going to discuss about widely used algorithm for search. That's linear algorithm. It's a searching algorithm which is most of the programmer used. Let's take some array and we will apply the linear search algorithm on top of this array to search for some element in the array. Let's take this array. Five, 10, 3, 8 and 15. This array having 5 elements and index are 0, 1, 2, 3 and 4. Alright. Now we wanted to find the element 8 from this array. If you are going for linear search, we have to travel one by one and check the element is we are looking for. So let's check this first element. Is this 8? No. So move to the next element. Is this 8? No. So again move to the next element. Is this 8? No. And again go for next element. Is this 8? Yes, it's 8. So we got it. This is how we have to search by using linear search. Means we have to look for the element one by one to find the element which is we are looking for. Here we have to start searching the element from the start index to the end until we find the element which is we are looking for in the collection. Let's see the definition given for the linear search in Wikipedia. Linear search sequentially checks each element of the list until it finds the elements that matches the target value. If algorithm reaches the end of the list, the search terminates unsuccessfully. Linear search algorithm is not good for all the cases. In an element we are looking for is in first element of the collection, it's fine. We will get it in the first iteration. But this might not be the case for all the scenarios, right? Let's think. If the element is present in the last position of the array, so we have to travel till end of the collection, right? Since here we have only 5 elements, here it's fine. But what about 1 million elements? Or think about 5 million elements. It's huge performance impact, right? So coming to the complexity, if element is present in first position, complexity will be O of 1. But while considering big O, we have to take worst case scenario, right? So for the linear search, complexity will be O of n. Hey guys, welcome back. In this video, we are going to discuss about implementation approach for linear search algorithm. Let's take this array. If you see this array, we have totally 7 elements inside this array. If I want to search some element from this array, say for example, I want to search number 7 from this array. So how we can do that by using linear search? So first we have to check the first element of this array, whether this is 7 or not. If not, we have to move for the next position of the array. Let's go for second element. Is this 7? No. So again we have to go for third element. Is this 7? No. So again go for next element. Is this 7? Yes. So this is the way we will do the search operation by using linear search, right? So this is what I have implemented for the linear search algorithm. In this main method, I just declared one array which is holding 7 values. After that, I just call search method from this class by creating the object for this class. If you see here, this search method accepts 2 parameters. One is actual array, whatever we have, and next parameter is whatever value we wanted to search from this array. Right? So once we call this method, we are expecting some integer value, which means if you go here, this method will return the index position of the value which is we are looking for. Suppose this method could not find any elements whatever we are passing here. it's simply written -1. If this method returns -1, it means we don't have such an element in this array, right? So if it's returning -1, we are displaying like element not present. If it's not returning -1, means basically we have the data which is we are looking for in this array, right? So we will return the index position of the array. So element found at index this, right? Let's run this program and see what is happening here. If you see here, I'll pass this array and I pass number 1 as the second parameter. Means basically I wanted to search this element from this array. If you see here, 1 is present here, 0, 1, 2, and it's present in index position 2, right? So our program returns element found at index position 2. Okay, let's run this program in debug mode. We'll check what is happening in step by step. I'll just put one debug point here and inside the search method, right? If I run this program in debug mode, see, this is array whatever we have, it's holding totally 7 elements. If you see here, all the 7 elements will be presented here, right? So I'm just creating object for this class to invoke this search method by passing this actual array and the value we wanted to look, right? I'm just calling this method. So program controls going here. So here basically what we are doing, right? We have to iterate this array one by one, and each and every iteration we have to check whether current iteration value means current index having this x value or not. Here x will be 1, right? So for the first iteration this 3 will come, and for the second iteration 6 will come, and for third iteration 1 will come. In the first iteration I value will be 0, so array of 0 will be 3. Is 3 equal to 6? No, right? So it will skip. So again for the second iteration I value will be 1. In the 1 we have 6. So is 6 equal to 1? Again no, right? So again it will skip. And for the third iteration I value will be 2, which is this value. Here we have 1. So 1 equal to 1? Yes. So we found it. So it's written that index value. Now result will be index position 2, right? So result is not equal to -1, so it will be skipped here. It will go for else block, and here we are just printing those values. If you see here, we are printing element found at index position 2, right? This is how linear search algorithm will works. See you guys on the next video. Hello guys, welcome back. In the last video we have discussed about linear search algorithm. There we have discussed about linear search will give huge performance impact while using large dataset. So how we can overcome that situation? There is an alternative option for linear search algorithm, that is binary search algorithm. Okay, imagine that you and me going to play a game. The game is, I'm going to choose one number from 1 to 100, and your job is find out the number which is I have chosen by guessing. But for your each guess, if you are wrong, I will give one clue. That is, I will tell you that whatever number I have chosen is greater than the number you guessed or less than you guessed. Alright, let's imagine that I am choosing number 72. Now it's your turn to guess the number. So let's say your guess is number 50. If so, sorry about it. It's not the number what I have chosen. So as I promised, I will give you a clue. So whatever number I have chosen is greater than your guess. So now you have a clue, right? And the number you are trying to find out is not between 1 to 50, right? Because you know that the number you are looking for is greater than 50 and less than 100. So you can avoid thinking from number 1 to 50. Am I right? Now your next guess is 75. Now your next guess is also not a number which is I have chosen. Okay, again I am giving a clue saying that the number I have chosen is less than 75. So based on my second clue, you can neglect the number from 75 to 100. Am I right? So now you almost identified that the number you are looking for is in between 50 to 75. Am I right? Now your guess is 71. So again your guess is failed. But this time my clue is the number I have chosen is greater than 71. So now your job is almost easy. So based on my clues, you know that the number you are looking for present in between 71 to 75. and already you know that the number is not 71 and 75. So you are sure now the number I have chosen is 72 or 73 or 74. Now your new guess is 73 and I said no, my number is less than 73. Now almost you got. The number I have chosen is 72, right? Whatever search you used here to find my number is binary search. So initially you have to find the number from 1 to 100. At this stage, to find my number having 100 possibilities, but once I told that the number you are looking for is greater than 50, you eliminate half of the element from the possibility, and at this stage you have only 50 possibility, right? And for the next try I said my number is less than 75, so again 25 possibilities are eliminated from 50. So every time we are eliminating half of the possibility, right? This same approach is applied for binary search algorithm. So in this approach, whatever we did, it's divide and conquer. So binary search uses divide and conquer algorithm to solve search problems. Divide and conquer means divide the bigger problem into small problems, and conquer means analyze the problem and finally combine the results. Here also we did the same thing. Out of 100 possibilities, we divided into 50 and we have analyzed those 50 and again divided and again analyzed and again divided and again analyzed till to find the element which is we are looking for. Am I right? Just imagine in this game if you are using linear search, means if you guess the number one by one starts from 0, how many tries you might have take to find the number which is I have chosen? It's about 72 guesses, right? But by using binary search, you find the number in 5th try. Probably you might have predicted that binary search tree is how much efficient compared with linear search, right? Okay, now let's take some example. But before we start the example, we have to know that there is some precondition to work with binary search. Data set should be sorted order. That is the precondition. In our game, we treated the number or ascending order so that we can apply the binary search algorithm and identify the elements in less number of attempts. So to use binary search algorithm, precondition will be data set should be sorted in some order. Let's take this array. Let's take 5, 10, 25, 30, 40, 54 and 62. It should be sorted order. It's the precondition to apply the binary search algorithm, right? And index position will be 0, 1, 2, 3, 4, 5 and 6. And this will be the low element and this will be the high element of this array. Here I mean low and high are based on the index positions. We will just hold on here and we will go Wikipedia page and see definition for the binary search. So according to Wikipedia, binary search works on the sorted array. Binary search begins by comparing the middle element of the array with targeted value. If the target value matches the middle element, its position in the array is returned. If the target value is less than the middle element, search continues in the lower half of the array. If target value is greater than the middle element, the search continues in upper half of the array. By doing this, the algorithm eliminates the half in which the target value cannot lie in each iteration, meaning that we have to start comparing the element from middle of the array with targeted element, and if the target is greater than the middle element, we have to travel to right hand side of the array, else we have to go for left hand side. Again, coming back to our example, let's take our targeted element is 54. So we are going to find the element 54 from this array by using binary search. Since we are using divide and conquer algorithm, we have to divide the problem set to half size. So first we should find the mid element of the array. The formula to find the mid element is mid equal to low index plus high index minus low index divided by 2. So in this array, low is index 0 plus high will be 6. So 6 minus low, so again 0 divided by 2, that is 6 divided by 2. So it's 3. So mid will be index 3. Now we have to check whether the targeted element is mid element or not. If element we are looking for is not the mid element, then we have to check whether the targeted element is greater than the mid element or less than the mid element. If targeted element is greater than the mid element, we have to go for right hand side, else we have to go for left hand side. So here targeted element is 54 and the mid element is 30. So whatever element we are looking for, it's not mid element, and targeted element is greater than 30. So we have to go for right hand side. Now we can eliminate this whole left side of the array because we are sure that the element we are looking for is not available in the left hand side. So now we are going for right hand side. Now our low will be this element. And again we have to find the mid element based on the new low and high values. So how to find the mid element? Mid equal to low plus high minus low divided by 2. That is, currently low element will be index 4. So 4 plus high will be remain same, 6 minus 4 divided by 2. That is 4 plus 2 by 2, which is 4 plus 1. So 5. Now our mid element will be index position 5. Now we have to check whether our targeted value is this mid element or not. If not, we have to decide whether we have to travel to left hand side or right hand side of the array. Here mid element is 54. So we can compare. Is this 54? Yes, this is what we are looking for. That's it. We can terminate the execution of our algorithm and return the result. This is how binary search will work. Let's take for instance, if you are using linear search algorithm to find this element, we have to start from index 0 and needs to check one by one. So for this array, we will find the targeted element in 6th try. But if you are using binary search, we got the targeted value within 2nd try. And for this binary search complexity will be log n, because every time we are dividing the total possibility to off time, right? So binary search complexity better than the linear search. See you guys on the next video.
Hey guys, welcome back. In this video, we are going to discuss about implementation approach for binary search algorithm. Let's take this array. If you see here, we have totally 7 elements in this array, means index position 0 to index position 6, right? So the first thing is we have to calculate low and high, right? So at the initial stage, low will be index position 0, which is 2 here, and high will be index position 6. In this array, we have 30 in this index position 6, right? And the next step is we have to find mid element. So how to calculate mid, which is low plus high minus low divided by 2. Here low will be 0, so 0 plus high minus low, which is 6 minus 0 divided by 2. So mid element is index position 3. Here we have 10 in the index position 3. Now we found the mid value, right? So what's our next step? We have to check whether the value we are looking for is 10 or not. If it is 10, we have to return this index, or else we have to decide whether we have to go for left hand side or right hand side of the mid, right? So the value we are looking for is less than this 10, we have to go for left hand side. If the value is greater than 10, we have to go for right hand side, right? In such a case, we have to recalculate our low and high again, right? If you are going for left hand side, low will be remain same, which is 0. Here high will be changed. So what is the new high value? Mid element minus 1, which is in this case 3 minus 1, 2. So our new high will be 2 and low will be 0. If you are going for right hand side, high value will be remain same, low value will be modified. In this case, low value will be mid plus 1. So 4. Now we have new low and high value, right? So again we have to start the same process. Means we have to find the mid element. We have to check whether this mid element is the element we are looking for, If not, again we have to decide whether we have to go for left hand side or right hand side. Alright. Okay, let's take this program. In this main method, I have declared one array which is holding 7 values: 2, 5, 8, 10, 15, 20 and 30. Right. I am just calling this binary search method by passing this actual array, low index and high index and x value. In this case, I wanted to search element 8 from this array, so I am passing 8 here. At the initial stage, low will be 0, right? So I am passing directly 0 here, and high will be last index, which is in this case array.length will return 7, because here we have totally 7 elements, right? So it will return 7. If you are taking array, right, always index position will start from 0, right? So high will be length minus 1, and in this case I'm just passing 6, right? If we call this method, we are expecting integer value as the result, means basically index position of the element which is we are looking for. If you can't find that element, it will return -1, right? So if I call this method, what is our expectation? This 8 will be presented here in index position 2. So our expectation would be element found at index position 2, right? Let's run this and see what is happening. So this is what we expected, right? Okay, now we will run this same program in debug mode and we'll see what is happening in step by step. I'll just put one debug point here and another debug point in this binary search method. I'll just run this program in debug mode. So this is our array. It's holding 7 values, and here I'm calculating the high value, so it will return 6. Now I'm passing this low value and high value and the value we wanted to looking for, as well as the actual array. This all the values we are passing into binary search method. While calling this method, our first step is we have to find the mid element. So our formula will be low plus high minus low divided by 2, which is in this case 3, right? So mid element will be 3 now. Our next step is we have to check whether this index position 3 holding this x value. If not, we have to decide whether we have to go for left side or right side, right? So in this case, mid will be 3, right? In the index position 3 we have 10, which is not we are looking for, right? So this will be skipped. Here we are checking whether this x is less than mid. If it is less than mid, we have to change our high value, right? Because we have to travel for left hand side. In this case, our x will be 8, our mid element will be 10, so x will be lesser than 10, right? So we have to go for left hand side. So our low value will be same. I'm just passing again 0 only, and the high element will be mid minus 1. So which is current mid is 3, so 3 minus 1 2, so new high will be 2. So by passing the new low and high, I'm again calling the same method. Okay, so array will holding all the values, low will be 0, high will be 2, x will be 8. So in this case, our new mid will be low plus high minus low divided by 2. Here low will be 0 plus high will be 2 minus 0 divided by 2, which is 1. So new mid will be 1, right? Here we are checking whether this mid element is whatever value we are looking for. Here array of 1 will be 5, it's not 8, right? So again it will go for check. Again we have to check whether we have to go for right hand side or left hand side, right? In this case, mid element is the less than 8, right? So we have to go for right hand side. So this will be skipped here, and in this case high will be same whatever we have last time, which is 2, and low will be changed. Initially low will be 0, right? But in this case low will be mid plus 1. Now mid is 1, so mid plus 1 is 2. So in this case low and high will both are 2. So again I'm coming here, I'm finding the mid value again. So in this case 2 plus 2 minus 2 divided by 2, so which is 2. So mid will be 2, and we are checking array of 2 is equal to 8. Yes, right? So in this case it's true. We are returning the mid value, means basically index of the mid value. So it will return 2. Alright, we found the element by using the binary search. So since it's not returning -1, we found the element, right? So this will not print. It will go for else block. Here we are printing index element found at index position 2.
right? This is how binary search algorithm will work. See you guys in the next video. Hey guys, welcome to the new section of this course. Sorting is the process of rearrange data within the collection. Sorting is common task and it's very interesting one to understand data structure world. We can apply sorting algorithm on top of almost all the data structures like array, linked list, like that. There are millions of ways to sort the collection. Similarly, lots of sorting algorithms are available and each one work and give the best result based on the data available in the data structure. For example, some sorting algorithms works well for nearly sorted data set. Means mostly all data are already sorted except 2 or 3 elements. And some sorting algorithms are works well for random data set. And some sorting algorithms are works well for dataset which have some unique values, and it's our responsibility to choose the right algorithm for our dataset to arrange the data. Since sorting is a common problem in software development, mostly all the library or framework gives the inbuilt function for the sorting or rearrange the data. If you are using Java or Python or Ruby, whatever it is, it will provide the feature to sort the dataset. Even though the framework or libraries giving a function to sort the collection, it's our responsibility to know how those algorithms are working. Then only we can able to choose right approach when it need. This sorting algorithm works for number as well as alphabets. In real world, we might get the requirement to arrange the movie list based on the release year, or rearrange the movies based on the movie name, or list down the employees based on the lowest salary to highest salary. This kind of things will be taken care by sorting algorithms. Let's say for example, I have array with data 5, 1, 3, 8 and 2. If we apply sorting algorithm on top of this array, we will get 1, 2, 3, 5, 8. It's basically rearrange the data with ascending order. Okay, let's start with some famous sorting algorithm. Hey guys, welcome back. In this video, we will start with bubble sort algorithm. It's famous algorithm for sorting. As I told earlier, lots of algorithms are available in real world. So based on how it's processed the data is different for each and every algorithm. Some algorithm works well for some set of data and some algorithms works well for another set of data set. So difference between one sorting algorithm with another one is based on how it's processed the data. Let's take this array. Twenty, 6, 8, 2, 9 and 10. In bubble sort, we will start with first element of the array and we will compare with next element. If it's greater than the next element, we have to swap the position of those elements. So here we have to compare this 20 with next element 6. Since 20 is greater than 6, we should swap this element in this array. So we should swap these elements in an array. So 6 will be shifted here and 20 will be shifted here. Again we have to follow the same process for remaining elements. Let's take this 20 and compare with next element. So 20 is greater than 8. So again swap these elements. Now 20 will be third element and 8 will be second element of this array. And next compare this 20 with 2. Again 20 is greater than 2. So again swap. Now 20 is greater than 9. So swap again. Finally 20 is greater than 10. So swap these positions. Now we have completed this last position of this array. While we are done with this, the maximum value will be placed in last element of the array. So after completing this iteration, we have settled bigger value in the last position. That means we are done with last element. And if you noticed, other elements are not yet started, right? Seems like incorrect order. Means our job is not yet done. We have done with only one element as of now. We have to follow the same process for other elements too. But while iterating, we no need to compare the last element because we are already done with that. So we have to stop here while comparing. So now let's start with first element again. It's 6. Is 6 greater than 8? No. So don't swap. It will remain same. moving to the next position. Is 8 greater than 2? Yes, so swap it. So 8 will be moved here and 2 will be moved here. Now check, is 8 greater than 9? No, so don't swap and it will remain same. And is 9 greater than 10? No, so no swap. So we are done with second iteration. So last two position will be arranged. And next iteration we should not consider this 10 and 20 because we are already done with that. Let's start with next iteration. Is 6 greater than 2? Yes, so swap these two positions. So 6 will be moved here and 2 will be moved here. Then next check. Is 6 greater than 8? No. So without changing anything, we will move to next position to compare. Is 8 greater than 9? No. So don't swap. And we are done with this last three position of this array. Now continue with next iteration. Is 2 greater than 6? No. So don't change. And next position is 6. Is 6 greater than 8? No. So don't change again. So we are done with this iteration because we already done with last three positions. So we should not consider this, right? So now we are done with last four position. Means this last positions are sorted. And remaining elements are only first two elements. So we will continue with next iteration. Is 2 greater than 6? No. So don't swap. And that is for this iteration. So finally we are done with the algorithm. Now this array is sorted. That's it. This is how bubble sort will work. So we are done with sorting algorithm, but what about the complexity for bubble sort? In the first iteration, we have moved biggest number to the last position, right? So this is for one element and we have to continue the same process for other elements also, right? Means if array size is 5, we need to do the iteration for 5 times to complete all the elements, right? And for the first iteration, to move the biggest number to last position, we have compared position by position. Am I right? So within first iteration, there is another loop is going on to compare one to another. So it's a loop inside of another loop. Like this. This for loop run for n times and this for loop run for n times. So it's n square. So the complexity of bubble sort will be n square. Okay, now we will visualize how bubble sort works. Let's go for visualgo.net. Let's go with sorting. And it's going to sorting page. If you see here, there is almost all the famous sorting algorithms are available. So here I'm selecting bubble sort. In the bottom of the page, I'm selecting sort and go for visualization. Once I click go button, algorithm starts here. Here you can see the visual representation for how bubble sort is working. If you see here, algorithm and execution line are displayed with description. See you guys on the next video. Hello guys, welcome back. In this video, we are going to implement bubble sort algorithm. Means we are going to take one unsorted array and we are going to apply this bubble sort algorithm on top of this array. Okay, let's take this array. If you see here, this array holding 5 elements within it. 4, 3, 5, 2 and 1. Once we applied any sorting algorithm on top of this array, we will get the result as 1, 2, 3, 4 and 5, right? So the core idea of bubble sort algorithm is, here we have totally 5 elements, right? And each and every iteration, we will move the maximum element into last position of the array. Let's say for example, in this array, we have 5 is the maximum value, right? So at the end of the first iteration, we will move this 5 into last position, means in this index position 4. So how to do that? First, we'll start with index position 0. From here, we will compare this 4 with next index position with 3. If this 4 is greater than this 3, we have to swap these elements, right? So how to swap that? Here index position 0 will have 4 and index 1 will have 3, right? Basically we wanted to move this 4 into index position 1 and this 3 to index position 0. To do that, what I'm going to do, right? First I will take this element and store it in some temporary variable. Let's take this 4 and store it in somewhere like temp, okay? And now next step is move this 3 into index position 0. And finally, whatever value we have stored in the temporary variable, right, that one moved into index position 1. So this is the way we can swap the elements between the positions, right? So at the end of the first iteration, we will move this 5 into index position 4. So basically at the end of the iteration, we will find that this element 5 will be the maximum element. So it will be moved to index position 4. And at the next iteration, we will consider only these first 4 elements. Means basically length minus 1. Here we have totally length 5, right? In the next iteration, length minus 1, which is 4. So in the next iteration, we will consider only these 4 elements. And at the end of the second iteration, we will move this 4 into index position 3. At the end of the third iteration, we will move this 3 into index position 2. And the next iteration, we will move this 2 into index position 1. And finally, we will move this 1 into index position 0. Okay, let's run this program in debug mode and we will see what is happening in step by step. I'll just put some breakpoint here and I'll put some breakpoint in bubble sort method. If you see here, this bubble sort method accepts one parameter, which is our array. I'm just calling this bubble sort method by passing one array. See here, this array is unsorted now. Okay, let's run this program in debug mode. So this array holding 5 elements within it, 4, 3, 5, 2 and 1, right? If you see here, we have 2 for loop. This top level for loop is responsible for moving the maximum element into last index position, and this inside for loop will be responsible for inside the each iteration compare one element with another element to swap the elements between the positions. Then only we can able to move this maximum element into last position, right? So that is why we are using inner loop. That's the reason this complexity will be n square that we have already discussed in the last video, right? Okay, now in the first iteration I will be 0, right? So this for loop will be executed for 5 times because here we have totally 5 elements, right? Starts from 0 to 4. And this inside for loop, it will reduce its iteration value based on the upper for loop. Say for example, for the first iteration I will be 0, right? So n minus I, which is 5 minus I, still 5 minus 1. So again 0 to 4. So for the first iteration, this loop also will be executed for 5 times because here we have totally 5 elements, right? For the next iteration, means once we move this 5 into last position, we have to execute this algorithm only for this first 4 element, right? So for the next time, this loop will execute only for 4 times. Means for the next iteration, I will be 1, right? So n minus 1, which is 5 minus 1, 4, and minus 1, which is 3. So till 0 to index position 3 we will execute, means basically these elements. And for the next iteration I will be 2. So 5 minus 2 is 3 minus 1, 2. So basically 0 to 2 means this 3 position. And for the next iteration only these 2, and for the last iteration only this. Clear? Okay, now we'll execute. So currently I value will be 0 and j value will be 0. Here we are just checking this value with this value. If this index position 0's value is greater than the index position 1's value, we have to swap this. In this case it's true, right? So it will go inside. By help of temporary array, we are swapping these 2 elements. So I'm just moving this 4 into one temporary array. So this temporary will have 3. And next we are moving the j plus 1, which is this 3 into index position 0, array of j. Currently j is 0, right? So array of 0 equal to j plus 1, which is 3. We are simply moving this 3 into index position 0. And finally, from the temp we have the value 4, right? That one we are assigning into j plus 1. Means basically we are swapping these elements by using temporary variable. So in the first iteration we swapped this. Okay, now I'll change this. 3 will be moved here and 4 will be moved here. In the next iteration, index position 1 will have value 4, right? If you see here, this 4 is not greater than 5, right? So this will be false for the next iteration. And for the next iteration, 5 and compared with 2. So this is bigger value, right? So again swapping. After swapping, 2 will be moved here and 5 will be moved index position 3. And again, right, for the next iteration, 3 is greater than 1, right? So again we have to swap. So after swapping this, it will be moved to
here and 1 will be moved to here. Right, we are done with first iteration of this upper for loop, and for the next iteration we have to compare only these 4 elements. Means in the for loop we have to consider only first 4 elements. Okay, let's do that. Now j equal to 0, so array of 0 means this value is greater than next position, no, right? So it will be skipped. And for the next iteration 4 and 2, 4 is greater than 2, yes, so we have to swap that. So after swapping that, 2 will be moved here and 4 will be moved here. Okay, in for the next iteration also, right, 4 is greater than 1, right? So again we have to swap. So after swapping that, 1 will be here and 4 will be here. Yes, now we are done with the second iteration. At the end of the second iteration, 4 and 5 elements are the sorted, means last 2 elements are sorted. Okay, now we are going for third iteration. On the third iteration we have to move this 3 into index position 2, right? Okay, let's do that. In this inner for loop we have to consider only these 3 elements. If you see here, n will be 5 minus current I will be 2, so 5 minus 2 is 3 minus 1, which is 2. Totally we have to iterate 3 times, starts from 0 to 2, right? Okay, now in array of j is 3, array of j plus 1 is 2, so 3 is greater than 2, right? So we have to swap it again. After swapping this, 2 will be moved here and 3 will be moved to index position 1. And for the next iteration, this and this, right? So we have to compare this 3 with 1. Since it's 3 is greater than 1, we have to swap it again, right? After swapping this, 3 will be moved here, 1 will be moved to index position 1. That's it. Now we have completed the third iteration. Like that, in the fourth iteration we have to consider only these 2 elements. Let's do that. Array of j, which is 2, j plus 1, which is 1, 2 is greater than 1, so we have to swap it. After swapping this, 1 will be here and 2 will be in index position 1. That's it, we are done, right? Because we have only one element that will be already in index position 0. Now we are done with our algorithm. After running this method, we are just printing whatever values we have it in this array. That's it. If you see here, 1, 2, 3, 4 and 5. So this is what we have expected, right? So this is how bubble sort algorithm will work. See you guys on the next video.
Hey guys, welcome back. In this video, we are going to discuss about selection sort. This selection sort algorithm sorts an array by repeatedly finding the minimum element from the unsorted part and putting it at the beginning. Means this algorithm finds the minimum element from the array and it will be placed in the first position. And if it's done with first position, it will take and process the rest of the element which is unsorted now in the array. Since first position is already filled with minimum value, we are not consider this first position for the next iteration. Okay, fine. Now in the second iteration, algorithm finds the minimum value from the array and placed it in the second position. This is how all the elements will be processed in the selection sort. At the end of the algorithm execution, we will get the sorted array. Let's see how selection sort works in step by step. Let's take this array. One, 6, 3, 9 and 7. So starting with first position of the array, we will check this 1 with the next element 6. Is 6 less than 1? No. So now our minimum element will be 1. And let's take this minimum element and compare with next element 3. Is 3 less than 1? No. Still 1 is the minimum element. And next element is 9. Is 9 less than 1? No. And next element is 7. Is 7 less than 1? No. So at the end of first iteration, 1 will be the minimum element. So it will be moved to first position of the array. Since 1 is already first position, there is no changes in this array. Now we will go for second iteration. Let's take 6 and compare with next element, that is 3. Is 3 less than 6? Yes. Now 3 is the minimum element now. We will keep this 3 as a minimum element and continue the next iteration. Next element is 9. Is 9 less than 3? No. Still 3 is minimum. And the next element is 7. Is 3 less than 7? No, that's it. Now at the end of second iteration we found that 3 is the minimum value in the array. So swap this 3 with 6. So 3 will be moved here and 6 will be moved here. Now we are done with first two positions. Now we can do the same process for rest of the items in the array. Let's take element 6. Initially this will be the minimum, and compare this 6 with next element. Next element is 9. Is 9 less than 6? No, still 6 is the minimum. So moving to the next item. Is 7 less than 6? No. So at the end of third iteration 6 will be the minimum value. So it will be moved to third position of the array. So in the next iteration we have to start with 9 because we are already done with first three positions. Now minimum value will be 9 and we have to check this with next element, which is 7 here. Is 7 less than 9? Yes. So now 7 is the minimum now. So swap these elements between 9 and 7. And on the final iteration we have only one element, so it will be the last element in the array. So this is how selection sort will work to sort the element in an array. So what is the complexity of the selection sort? This is same like bubble sort, right? One loop for process the number of elements, and inside that loop another loop to find the minimum value. So like bubble sort, selection sort complexity also n square. See you guys on the next video.
Hello guys, welcome back. In this video we are going to discuss about implementation approach for selection sort algorithm. Let's take this array 4 3 5 2 1. So this is unsorted array, right? I'm just calling sort method from this class by passing this array. Once I call this method, in this method we are going to implement selection sort algorithm. So once we applied selection sort algorithm on top of this array, we will get the result as 1 2 3 4 and 5, right? The idea of the selection sort algorithm is, let's take this array. So in the first iteration we have to find the minimum element of this array. So for example, in this case it's 1. Once we find the minimum element, we have to move this minimum element into index position 0. Means basically here we have 4, right? It has to be moved to index position 4 and 1 will be moved to index position 0. So at the end of the first iteration we have completed this sorting algorithm till the index position 0, means till index 0 it's sorted. And for the next iteration we should consider only remaining elements, right? If you see here, this upper for loop help us to process the all element inside this array. Means basically for the first iteration index position 0, for the second iteration index position 1 and 2 and 3 and 4. Means from index position 0 to index position 4, right? And this inner for loop help us to identify the minimum element inside the each and every iteration. So for example, for the first iteration we have to sort the element till 0, right? To find the minimum element from this array we have to process one element with another element, right? So this inner for loop will do that. If you see here, this is the first element. So for the first iteration we have to start the comparing the element from index 0, right? If I start here, I should not consider this 4 again, right? We have to compare the element from next index onwards. So that's the reason in the inner for loop j value will be start from I plus 1. So for example, in the first iteration I will be 0, right? So from the here we have to compare from 1 2 3 4 and all. We should not consider 0. That's the reason j equal to I plus 1. So at the end of the first iteration we will find that this 1 will be the minimum element, so it's moved to index position 0, and the next iteration we will find that this 2 will be the minimum element, because we are not considering the index position 0, right? Because it's already processed. So from the remaining element 2 will be the minimum element, so it will be moved to index position 1. And for the next iteration we should consider only these 3 elements. From these 3, which one is minimum element, we have to move that into index position 2, and for the next iteration index 3, and for the next iteration index 4. That's it. Once we completed all the elements in this array, we are done with this selection sort algorithm, right? Okay, let's run this program in debug mode and we'll see what is happening in step by step. I'll just put some breakpoint here as well as in sort method. If you see here, I'm just calling this sort method by passing this array whatever we have. It's unsorted initially, right? This is upper for loop to process all the elements within this array. So first we have to complete index position 0. So we'll start from index position 0 till index position 4. We have to iterate this for loop. So for the first step is we have to find the minimum element. So initially whatever element we are taking, that is the minimum element, right? So in this case 4 will be the minimum initially, and we have to compare this 4 with all other elements. In somewhere in middle, if you found anything is less than this 4, we have to make that element as the minimum element. So as of now 4 will be the minimum element, and we have to compare this 4 with all other remaining elements from this array. In somewhere if we find anything is less than this 4, we have to make that element as the minimum element. Okay, at the end of this inner for loop we will find that what is the minimum element of this array, right? Then we have to start our swap process. Okay, let's do that. So initially j will be 1, in index position 1 we have 3, current minimum will be 4. So just we are checking array of j means 3 is less than 4, yes, so it will be true. So we are making this 3 as the minimum element. Alright, so currently index 1 will be the minimum, right? And for the next iteration j will be 2, right? In this case 5. So here we are checking whether this 5 is less than 3. No, right? So it will be skipped. And for the next iteration j will be 3. We are comparing this minimum value with 2. So what is the current minimum now? It's 3, right? Is this less than 2? No, right? So we are updating our minimum. So now minimum element will be index position 3, which is 2 here. And for the next iteration index position 4, it's 1 actually, right? So current minimum is 2. Again we are comparing with this 1. So 1 is the minimum, then 2, right? So again we are updating the minimum element. So finally minimum element will be 1, means index position 4, right? So now we have to move this 1 into index position 0. And currently we have 4 in this index position 0, right? This one have to move into this location, means index position 4. For that we are using temporal variable to swap the elements. So in this case array of minimum index will be 4. We are just storing this minimum index value into some temporal variable. So in the temp we have value 1. Now we have to assign first element value into index position 4. So basically 4 into index position 4, right? So that is what here we are doing. So now we move this 4 into index position 4. Now whatever elements we have it in the temporary variable, that has to be moved into index position 0. So temp value we are assigning to index position 0. So at the end of the first iteration 4 will be moved here and 1 will be moved here, right? So now for the second iteration we should not consider this index position 0, because till index position 0 elements are sorted order, right? And for the second iteration I will be 1, right? So minimum element will be 3 as of now, means basically it's index position 1, right? And this inner for loop we have to compare from these elements, compare from index position 2, because currently we are in index position 1. To compare this index position 1 is less value or not, we have to compare with all other elements from this array. So I plus 1, in this case 1 plus 1, which is 2. So j value has to start from index position 2, right? So again we are comparing this 3 with all other elements. If you see here in this current iteration index position 2 will be 5, right? It's not less than 3, right? So we can skip. And for the next iteration 2, so this will be the less value, right? So we have to change our minimum value. Now our minimum value present in the index position 3. And for the next iteration value will be 4, right? 4 is not less than 2, so we keep our minimum index will be 3 only, right? So we are done. So now we found that in the second iteration 2 will be the minimum value. So in our current iteration I will be index position 1, right? So we have to swap this 2 into index position 1, and already we have 3 in this position, right? We have to move this 3 into index position 3. That is what we are doing here. Using the temporary array, first we are keeping this minimum index value, which is 2 to temp variable, and then we are moving this 3 into index position 3 here in this line, and finally we are moving that 2 from the temporary variable to index position 1, right? So at the end of the second iteration 2 will be stored here and 3 will be moved to here, right? Now we are done with first two elements in this array. From the third iteration, we should consider only these three elements. So currently I value will be 2, right? And we have to start our inner loop from index position 3 to 4, right? So from here 5 we have to compare with 3. Yes, 3 is the minimum value, right? So we have to change our minimum value. Now in the current iteration 3 will be minimum value, means index position 3. And for the next iteration 4, it's not less than 3, right? So we will keep the old value in the minimum index. So at the end of this iteration we will find that index position 3 will hold the minimum value of this array. So now again we have to swap with index position 2 because our current iteration is 2, means I value is 2, right? So we have to swap these two elements. So 5 will be here, 3 will be here. That's it. Now we have completed first 3 elements in this array and we have left with these 2 elements. So in this current iteration I index will be 3 and we should consider in the inner loop only these elements. So we have to compare. The minimum will be index position 3. So in this inner loop we will find that 4 will be the less than 5, right? So we have to update the minimum index, which is from 3 to 4. Now minimum index will be 4. We have to swap this. So at the end of this iteration 4 will be moved here and 5 will be moved here, and at the last iteration we have only one element, right? So that's it, we can directly add it here. So now our array is sorted order. So once sorting is completed, I'll just print all the elements within this array. If you see here 1, 2, 3, 4 and 5, which is we expected, right? So this is how selection sort algorithm will work. See you guys on the next video.
Hey guys, welcome back. In this video, we are going to discuss about insertion sorting algorithm. Insertion sort is a simple sorting algorithm that works the way we sort playing cards in our hands. Let's assume you have set of playing cards in your left hand and it's not in sorted order. Let's take cards like 5, 2, 4 and 7. These cards are available in your left hand. And now we are going to move these cards to right hand. While moving these cards to right hand, we will arrange it on sorted order. Okay, let's do that. Let's take first card. It's 5. Move it to right hand. Since we have only one card, there is no need for sorting here. Okay, let's take second card. It's 2. While we insert this card into right hand, make sure it should be inserted in sorted order. So insert this 2 into before this card 5 because it's smaller than 5, right? Okay, now let's take third card and do the same process. So move it to right hand. It's number 4, so it will be inserted between 2 and 5. And the next card is 7. Move this to right hand, so it will be inserted here. That's it. We are done, right? Now whatever the card we have it in our right hand, it's sorted. Insertion sort also work in same way. Let's take this array. Six, 2, 1, 5 and 4, and index positions are 0, 1, 2, 3 and 4. Before we start applying insertion sorting algorithm onto this array, just imagine that this array having two subsets or two sections. One is holding unsorted list and another subset is holding sorted list. So now unsorted subset holding all these data within it and sorted subset holding 0 elements now because we haven't started our sorting algorithm. So whatever elements we have is not yet sorted, so it will be in unsorted subset. While we are executing this algorithm, each and every iteration we will start moving these elements from unsorted to sorted subset. Let's start the algorithm. Let's take first element of this array, which is 6. Let's take this 6 and move this element into sorted subset. Understand that there is only one array. We are just assuming that there is two sections within this array and one section having sorted elements and another sections having unsorted elements. Okay, now take out this 6 from unsorted subset. Imagine that at this stage from index 0 to index 4 are unsorted subset and move this into another subset. But while moving it to the another subset, compare with other elements within the subset and insert before the greater value than this element and after the lesser than this element. Since it's the first element in the sorted subset, we can directly insert this 6 into sorted subset. So moving this 6 into index position 0. Imagine that we started creating sorted subset. While processing each and every element, sorted subset will be increased by 1 and unsorted subset will be decreased by 1 index from this array. Now index 0 is sorted subset and from index 1 to index 4 are unsorted subset of this array. Now let's take next element from the unsorted subset. It's 2 and we have to move this to sorted subset. While moving, we have to start comparing this 2 with last element of sorted subset. As of now, sorted subset having only one element, so it's the last element as well. So compare this 2 with 6. It's lesser than 6, right? So this 6 will be shifted to one position to the right. And 2 will be inserted before that. So now we have extended sorted subset to index 0 to 1 and from the index 2 to 4 will be remain same as unsorted subset of this array. Let's take next element from the unsorted subset. It's 1. So take this out from the unsorted subset and check with last element of the sorted subset. So 1 is lesser than 6. So let's shift this 6 to one position right. Now 6 will be shifted from index 1 to index 2 and check with next available value. It's 2. Again 1 is less than 2. So shift this 2 to one position right. And now there is no element to compare with 1. So insert this 1 before this element 2. Now from index 0 to index 2 are sorted subset and index 3 to index 4 are unsorted subset. Let's take next element from the unsorted subset. It's 5. Let's take out 5 from this unsorted subset, compare with last element of the sorted subset. It's less than 6. So move this 6 from index 2 to index 3. And compare this 5 with next available element, which is 2 here. 5 is not less than 2. So no need to shift 2. We can insert this 5 into this empty position and do the same process for this last element. Let's take this 4 and compare with 6. It's less than 6, right? So move this 6 to one position right. And compare with next element 5. Again 4 is the less than 5. So move this 5 as well as one position right. And compare with next element 2. 4 is not less than 2, right? So we can insert this 4 here. That's it. Now our array is sorted order. This is how insertion sorting algorithm will work. While we think about complexity for this algorithm, like bubble sort and selection sort algorithms, this algorithm complexity also will be n square. One loop for process all the elements and inside that loop another loop to compare with other elements to decide where it should be inserted. So its complexity also will be n square. Let's see the implementation for this algorithm in next video. See you guys. Hello guys, welcome back. In this video, we are going to discuss about implementation approach for insertion sort algorithm. Let's take this array. It's holding 5 elements within it. As of now, imagine that these all 5 elements will be in unsorted subset. And currently we have nothing in our sorted subset. These two subsets are just imaginary things, right? I'm just calling sort method by passing this array. This sort method holding the logic for insertion sort algorithm. By applying this insertion sort algorithm on top of this array, we will get the sorted result. Result will be 1, 2, 3, 4 and 5. Alright, okay, we'll just put some breakpoint here and we will run this code in debug mode. So initially, right, if we start from index position 0, we don't have anything to compare with sorted subset, right? So that's the reason in the upper for loop we will start the index from position 1. So I will be starts from 1, and this inner for loop j value will be starts from index position I, means initially, right, I value and j value will be 1, and we have to execute this for loop if j value is greater than 0. And if you see here, we have to decrement j value for each and every iteration. Say for example, now I am in index position 2, means I have to compare the elements less than index 2. Means if I am in index position 2, in the first iteration I will compare this, in the second iteration I will compare this. So I have to decrement j value. You will understand this whenever we execute this algorithm. Let's go further. I and j value will be 1. So here array of j will be 2 because now current index is 1. And we are comparing that this 2 is less than j minus 1, means 5. Yes, right? So this will be true. We are swapping these two elements by using temporary variable. After executing this first iteration, 2 will be moved into first position and 5 will be moved to second position, right? Now if you see here, j value will be minus minus, means in this case j will be changed to 0, right? So this will be terminated. Again we are going for upper for loop second iteration, means basically index position 2. So currently in our index position 2 we have 3. We are starting this inner for loop by assigning I value into j, right? So j value will be also 2. So array of j, which is 3, is less than j minus 1, 5. Is it true? Yes. So again it will go inside. So again we are swapping these two values. So after executing this iteration, 3 will be moved here and 5 will be moved here, right? Now j value will be decremented by 1. So it's decremented from 2 to 1. Now j value will be 1. Still it's greater than 0. So again it's going inside. Now array of j is 3, right? Because in index position 1 we have 3. Is less than j minus 1, means it's less than 2. No, right? So this will be false. That's it. We are done with this iteration. Again we are going back to upper for loop third iteration. In this third iteration I will be 3, right? In index position 3 we have value 1. So in inner for loop also we'll start from j value 3 and it's greater than 0. So we are going inside of this loop. Array of 3 will have 1. Is this less than j minus 1, means 5? Yes, right? So we have to swap these two positions. So after end of this iteration, 1 will be moved here, 5 will be moved here. Now still j value will be greater than 0, right? Because j value decreased by 1 from 3, right? So j value will be 2. So array of 2, here we have 1 is less than j minus 1. Yes, 1 is less than 3, right? So again we have to swap. So 1 will be moved here, 3 will be moved here. In this iteration again this condition will be true because now j value is 1, right? So again it's going inside. Array of 1 will be 1. Is this less than j minus 1, means 2? Yes. So again we have to swap. So 1 will be moved to position 0 and 2 will be here. Now j will be 0, right? So this will be fail. That's it. Again we are going back to upper for loop. Now in the current iteration I value will be 4. So we'll start this inner loop with j value 4 and it's greater than 0, so it's going inside. In array of j we have value 4. Is this less than 5? Yes. So we have to swap this. So 4 will be moved here, 5 will be moved here. And in the next iteration index position 3 will have 4. Is 4 less than 3? No. So this will be skipped. And still this condition is true. So now j value will be 2. 3 is less than 2? No, right? So again it's failed. And now we are in index position 1. In this case 2 will be less than 1? No, right? So again this will be fail. So that's it, right? We have completed all the elements. So we'll terminate the loop. Finally our array is sorted order by using insertion sort algorithm. I'm just printing all the elements by calling print array method. So it's print all the values here. I'll just clear this. 1, 2, 3, 4 and 5, which is we expected, right? So this is how insertion sort algorithm will work. See you guys on the next video. Hey guys, welcome back. So next algorithm is merge sorting algorithm. Merge sorting technique based on divide and conquer technique. Algorithms which is we have discussed earlier, that is bubble sort, selection sort, insertion sort and all, taking the time complexity will be n square in worst case. But for the merge sort, time complexity will be O of n log n. It's somewhat less complexity than other sorting algorithm. I hope you remember that divide and conquer means divide the bigger problem into smaller problems, and conquer means analyze the problem and finally combine the results. Okay, now let's take this array. Four, 7, 6, 1, 2, 8, 5 and 3, and index positions are 0, 1, 2, 3, 4, 5, 6 and 7. Let's apply merge sort algorithm on this array and sort these elements in ascending order. So after we complete this merge sort algorithm execution, result array would be 1, 2, 3, 4, 5, 6, 7 and 8. Merge sort will divide all array into 2 of, and again it will divide the resulted array into another 2 of, and again it will do the same process until the array element splitted into one element. After that it will combine the elements based on the way it's splitted. Means if you take this array, it's having 8 elements within it, right? So in merge sort it will be divided into 2 of, which is from index 0 to index 3 will be 1 of, and index 4 to index 7 will be in another of. So element 4, 7, 6 and 1 will be stored in the new array. Similarly, 2, 8, 5 and 3 will be stored in another array. In merge sort, we are using temporary array to do this. And again, these 4 elements divided into 2 of, which is 2 elements. So 4 and 7 will be stored in one array. 6 and 1 will be in another array. And like this, 2 and 8 will be in another array. Finally, 5 and 3 will be stored in another array. And again, this 2 element array divided into of. So finally, it will be 8 1 element arrays. So finally, it will be like this. So each and every element will be in different array. In the divide and conquer technique, divide process is done, and the next step is process it and finally combine the result. Here the process means sorting the array, which is compare the elements and place the elements which is less value as first element, and the higher value element will be the next position. Okay, let's do that. So here we have divided 8 into 4 and 4 into 2 and finally 2 into 1 element, right? And now we have to do it reverse. Means same way how we splitted the array. Means 1 element array into 2 element array, and 2 into 4 and finally 4 into 8 element array. While combining this array, we have to compare the elements within the array and sort the elements. Let's take this first 2 arrays, 4 and 7. 4 is less value than 7, so no swapping required here. And next we have to take this. Among these 2 elements, one is smaller than 6. So while combine these 2 elements, 1 will be the first element and 6 will be the next element. And next array is 2 and 8. It will be same order, just combine this array. And finally take this 5 and 3. While combining, this 3 will come first and 5 will be the next element. So now we have reduced 8 arrays into 4 arrays and each array having 2 elements. Again we have to do the same process. Let's take this first 2 array and combine this as single array. And take this next 2 array and combine this into one array. While doing this, we have to sort the array by comparing the value within it. Let's start with this 2 array. While combining, we have to sort the array based on the values present in the array. So result will be 1, 4, 6 and 7. And similarly, if we combine this array, result will be the array with 4 elements, that is 2, 3, 5, 8. Make sure that whenever we combine 2 array, we have to sort it first and combine it. And finally, we have only 2 array and combine this array and make it as one array with 8 elements. And again, while combining this array, we have to sort the elements by comparing them. So result array will be 1 with 8 elements. And elements order will be 1, 2, 3, 4, 5, 6, 7 and 8. This is how merge sort will work. See here, we are dividing the elements as 2 of, and again we are dividing the result will be another 2 of, something like that, right? So for this operation, time complexity will be log n. But we have to do the process based on the number of elements available in the array, right? So n times we have to divide and again conquer it, right? So complexity will be O of n log n. So merge sort time complexity will be O of n log n. And what about the space complexity for merge sort? Every time we divide the array into 2 of, and the resulted array will be stored in another temporary array. So based on the number of elements, we have to use many number of temporary array, right? So space complexity for the merge sort will be O of n. See you guys on the next video. Hello guys, welcome back. In this video, we are going to discuss about implementation approach for merge sort algorithm. As we have discussed in the last video, merge sort algorithm will work based on the divide and conquer technique. It means we have to divide the bigger problem into smaller problem, then we have to conquer that. Conquer means we have to process that. In this case, we have to sort them and then we have to merge, right? Let's take this array. If you see here, in this array we have totally 4 elements within it. If we consider this as a big problem, we have to divide this problem into smaller one. Means basically this 4 values into 2 values, then this 2 values into 1 value. Whenever we merge this 4 and 1, we have to sort this, then we have to merge. We will make this as 2 element array which is holding 1 and 4. And then we have to take this. Whenever we merge these 2 elements, we have to sort it, like it will be 3 and 7. Finally, we have to merge this and this array. So result will be 1, 3, 4, 7. Right? Okay, let's run this and we'll see what is happening. I'll just put some breakpoint here. And I'll put some breakpoint here as well. Before we start the execution of this program, I'll just mention that here I just declare one array in class level. So whatever array we are passing to this method, I'm just assigning to this global variable. In the merge sort, we are going to use some temporary array, right? For that, I'm just creating one temporary array which is having the same size as whatever we already have. Yeah, that's it. Okay, let's run this program. If you see here, I'm just calling this arrangement for sort method by passing this array. If we go here, now our current array object will holding all the elements which is we sent 4173, right? In the temporary array, we don't have anything. Initially, everything will be 0, right? While executing this merge sort algorithm, we are going to move this array elements into temporary array. While doing that, we will sort it out. Okay, fine. Here
From here I am just calling the merge sort method by passing low index and high index. Here low will be 0 and high will be length minus 1, right? So in this case low will be 0, high will be 3. So I'm just pausing that. So based on this high and low value, we have to find the middle value. This formula we have already discussed in the binary search, right? So formula will be low plus high minus low divided by 2. So in this case 0 plus 3 minus 0 divided by 2, which is 1, right? Now we are again recursively calling this merge sort method by passing new low and high value. In this case, whatever mid value we found, that value we are sending that as a high value for the same method. So low will be same 0 and high will be 1, means this section, means we are reducing this array size into half. Now this is our new array. In this array low will be 0 and high will be 1, right? So based on the new low and high value, we are again calculating the middle. So middle will be 0 based on this formula, right? So again we are calling this same method by passing new low and high value. Low will be 0 and high will be 0 again. So this will be skipped, right? So we are done with this. Means basically we are split this array from the original array, right? Now this is the one of our array, and now we have to take this second section. From the original array, low will be 0, high will be 3, right? So second part will have low will be mid plus 1 and high will be remain same, which means basically this part, right? Again we are calling the same method by passing new low and high values. Okay, fine. Now we have splitted our one array into two arrays, which is one array holding 4 and 1 and another array will holding 7 and 3. So now we have divided our 4 elements array into two elements array. So now we are going to call merge part method. In this merge part we are sending low, mid and high value. Let's take this. We are calling this method for this array, right? So low will be 0 and high will be 1 and middle will be again 0 based on this formula, right? So low will be 0, mid will be 0, high will be 1. So basically what we are going to do in this method, right? Let me draw that so that you can understand easily. Just imagine this 4 element array we are passing into merge part method. So this will be low, this will be high, and think about this will be the mid element, right? And in the program we are referring this part as I indexes. From mid plus 1 onwards we are referring as j values. This will be I and this will be j, right? Now think about, so this is the element we have. We have to compare this element with this element. Which one is lesser value? We have to move that into temporary array. So for example, in this case this will be the less value, so we are moving that into this position, and we will keep this j as same, but we have to increase I value to next position, means this position. That is what we are doing here. Now we have to compare this with this element. Say for example, in this case j will be less value than this, so in this case we have to store this value as the second position of the temporary array, and we have to increase j value to next value. That is what we are doing here, right? So at the end of this full process, all the element will be sorted in the temporary array. So coming back to this execution flow, now we are in this array, right? So low will be 0, high will be 1, mid will be 0. So after executing this, I'll just open this array. If you see here, all the elements are zeros, right? From this array we have to take these two elements and we have to sort this and merge. After executing this merge part for this array, our original array first two elements are sorted with ascending order, and again we have to do the same process for this array. In this case low will be mid plus 1 and high will be last element, means index 3.
So low will be mid plus 1, which is 1 plus 1, 2, and mid will be 2, and high will be index position 3. So once we complete this process, this 7 and 3 of this original array will be sorted order and merged. If you see here, this 3 and 7 will be placed in sorted order, right? Now we have done with this array and this array. Our next step is we have to merge these two arrays into single array. So on the next step, our low will be 0, high will be index position 3, and middle will be index position 1, right? If we call this merge part for these positions, we will get the sorted result of this array, means 1, 3, 4 and 7. Right? After completion of this program, we will get 1, 3, 4 and 7. This is how merge sort will work. See you guys on the next video. Hey guys, welcome back. In this video, we are going to discuss about quicksort algorithm. This algorithm applies divide and conquer approach to solve the sorting problem. As we have already discussed, divide and conquer means divide the bigger problem to smaller problems, and conquer means analyze the problem and finally combine the results. The overall idea of quicksort algorithm is choosing one element as a pivot element and partitioning the array around it. Means the element which is smaller than pivot has to be moved to left hand side of the pivot, and the element which is greater than the pivot has to be moved to right hand side of the pivot. Basically, partition is a process of selecting pivot element and rearrange the other elements left or right side of the pivot. So finally, left side of the pivot contains all the elements which is less than the pivot element, and right side contains all the elements greater than the pivot. These moving operations done within the same array, so it reduces the space complexity and removes the use of auxiliary array that is we used in the merge sort. Okay, let's take this array and apply the quicksort algorithm on top of this array. Three, 2, 6, 1, 5 and 4, and these index positions are 0, 1, 2, 3, 4 and 5. Let's choose pivot element. We can choose first element as the pivot or last element as the pivot, or we can choose randomly any element as a pivot. It's up to our choice. I am going to choose last element as the pivot. So here 4 is my pivot element. And the next thing is partition. Means we have to rearrange this array by comparing the element with pivot. So we have to move the smaller element than pivot to the left hand side of the pivot, and larger element has to be moved to right hand side. Right? Let's take pivot 4. So after partitioning, 3, 2, 1 will be left hand side of pivot element 4, and 6, 5 are right hand side of this 4. So just imagine that this array looks like this. Now take this section and do the partition process till the sections are reduced to single element, because after the single element we don't have anything to partition it, right? From this subset array we have 3, 2 and 1. Let's take 1 as pivot. So next step is again partition. Rearrange the element from this array based on the pivot value. So both the values are moved to right hand side because both the values are higher than 1, right? So 1 will be shifted to index 0, and 3 and 2 will be moved to index position 1 and 2. So array will be 1, 3 and 2. Now let's take this subsection, do the partition again till it's reduced to one element. So let's take 3 and 2. Here we will take 2 as the pivot. While rearranging, 3 will be shifted to right side and left side nothing will be there. So now 2 will be the index position 1 and 3 will be the index position 2, and that's it, right? Now we have only one element, So nothing to compare now. And now we have to do the same process for this section. Remember that here we are not using any other array to do this process. We are using the same array whatever we have. Just for better understanding only, I am just showing this as different array. Okay, let's do the same process for this subsection. Here we have 6 and 5 and these index positions are 4 and 5, right? Let's take 5 as pivot element because we are considering rightmost element as the pivot, right? So here 5 is the pivot element, but you can use the random number also. It's up to your choice. Okay, now 5 is the pivot element here. While doing partition for this subset array, 6 will be moved here. So now index position for the element 6 will be 5 and 5 will be shifted to index position 4. That's it, right? Now sorting algorithm completed. So our final result is, before that I'll just write down the indexes 0, 1, 2, 3, 4 and 5. So now element 1 will be in index position 0 and 2 will be in 1 and 3 will be in index position 2 and next is 4, it will be in index 3 and the next element is 5, it will be in index 4 and finally 6, it will be in index position 5. That's it. Our array is now sorted, right? So this is how quicksort algorithms will work. So now what is the complexity of this algorithm? Best case time complexity will be O of n log n, because in the quicksort we are using divide and conquer approach, right? So it will be split the array into two sections based on the pivot. Similarly, we will do the same process for all the subsets of the array. So if you have 8 elements in an array, it will be divided into 2 4 elements. Again, these 4 elements will be divided into 4 2 elements, like that. So time complexity will be O of n log n for the best case. But think about in worst case. If the array is already sorted in some order, like ascending or descending order, so the worst case occur when the partition process always picks the largest or smallest elements as the pivot element, right? So such a case, time complexity will be O of n square and the space complexity will be O of 1, because we are using same array to this all process. So space complexity will be O of 1 for the quick sorting algorithm. But still, quicksort is the faster in practice because its inner loop can be efficiently implemented on most architectures and in most real-world data. Okay guys, see you on the next video. Hello guys, welcome back. In this video, we are going to discuss about implementation approach for quicksort algorithm. So the core logic of quicksort algorithm is, first we have to select pivot element, and then what all elements we have less value than pivot element has to be moved to left hand side of the pivot, and what all the element greater than the pivot, it has to be moved to right hand side. So that is called partition process, right? First we have to partition the array, then we have to take the left side of the pivot, again do the same thing, and take the right hand side of the pivot and do the same process again. So left hand side and right hand side will be sorted. So this is how we are going to implement quicksort algorithm. If you see here, I have declared one array which is holding 4 values within it, 5 2 1 3. Once I apply the quicksort algorithm on top of this array, we will get the result as 1 2 3 and 5, right? Okay, let's go to this method and we will see how we can implement quicksort algorithm. If you see here, this method accepts 3 parameters. One is actual array, it contains all the 4 elements within it, and low index and high index. In this case, low index will be 0, high index will be 3, right? The first step is partition process, right? Once we partition this array, this 3 will be the pivot element. So once we selected pivot, we have to move greater element of this 3 will be right hand side, and less value than this pivot element has to be moved to left hand side, right? So after applying the partition, our result will be like this. See, this is the pivot element. So what are elements we have lesser than this 3, we moved to left hand side, and what are elements we have greater than this 3 has moved to right hand side. Now partition process done, and what next? From the pivot element, what all we have as the left side, for this again we have to do the same process. Means again we have to call the same sort method by passing new low and high index. In this case, low will be 0, this high will be partition index, basically pivot element,
minus 1. So that is what this call, right? And then we have to do the same process for right hand side. So again we have to call the same method by passing new low and high values. Here new low will be partition index plus 1 and high will be the same thing, right? Let's execute this. We'll see what is happening. I'll just put some breakpoint here and as well as in this partition method. If you see here, I'm just calling the partition method by passing the low and high index. Initially low index will be 0 and high index will be 3, right? Now always we will take last element as the pivot element in this program. So in this case I'll just expand this array. This last element will be the pivot element. We are going to compare what all elements we have less value than this has to be moved to one position left. Say for example, in this case first I will check with this 3 with 5. Is this less than 3? No, right? So go for next position. This one. Is 2 is less than 3? Yes. In this case we have to move this 2 into one position left, which means this 2 will be moved to index position 0 and 5 will be moved to index position 1. Basically we are swapping these two elements. Let's do that. In the first case, let's see it in this program. In the first iteration we have to compare this 3 with 5, right? So this is not less value, so it will be skipped here, and for the next iteration value will be 2. It's less than 3, right? So we have to swap this with 5, right? And the next item is 1. Again 1 is less value than 3, right? So again we have to swap this 1 with one position left, which is we have to swap this 5 and 1, right? Okay, now how many shifts we made? 2, right? So we did 2 shifting, right? So our pivot element moved to after the 2 shifts. Means in this case index 0 and 1 we shifted. So in this case we made 2 shifts, right? After this shift we have to place our pivot element. Means we have to swap this 3 with index position 2. That's it. Now our array will be looks like this. So now we have completed our partitioning process. Now our pivot element will be index position 3. Now we have to call the same process for these two elements. Means basically this part. Again we have to do the same process for right hand side part. So first we will execute partition process for this section. Here low will be 0, high will be partition minus 1. That is what we are doing here. If we do that, always we will choose the last element as the pivot, right? So 1 will be the pivot. Here we will check, is there any value less than this pivot? No, right? In this case it will be skipped, so no swapping here. If we don't swap anything, mean what and all value we have before this element, right? Everything is the greater value. Then we have to move this 1 into index position 0. That is what we are doing here. So this 1 will be moved here and 2 will be moved to index position 1, right? And again we have to do the same process for right hand side of this pivot. Since it's a one element, that's it. We are end up with algorithm. If you print that, we will get the sorted array 1, 2, 3 and 5. So this is how quicksort algorithm will work. See you guys on the next video.
Hey guys, welcome back. In this video, we are going to discuss about one of the most interesting algorithm for sorting. It's heap sort. In this unit, we have seen lots of algorithm for sorting the element in the collection. Compared with all other algorithms, heap sort algorithm will be more efficient than other algorithms. Why? Because if you take merge sort, its time complexity will be n log n. But while we think about space, it's taking more space to execute the algorithm, right? I hope you remember that. That is O of n. Let's think about quicksort. Its space complexity will be O of 1. But what about the time complexity? In the worst case, it will be O of n square. But if you use heap sort to sort the element in an array, time complexity will be O of n log n and space complexity will be O of 1. It's a better deal, right? Okay, let's start. First of all, heap sort will work with binary tree. Before we start with heap sort, there is some terminology you have to understand, such as heap, minimum heap and maximum heap. So what is heap? Heap is nothing but it's a simple binary tree, and minimum heap and maximum heap are just type of the heap. Minimum heap means root node will be smaller than all other child node. See, this is example for minimum heap. If you see here, all the parent node will be less than child node. If we take 1, it's less than its child 3 and 6, right? And if we take 3, it's less than its children 5 and 9. And maximum heap means root node or parent node will be greater than all the child nodes. See, this is example for maximum heap. If you see here, all the parent node will be greater than child node. If we take 9, it's greater than its child 8 and 6. And if we take 8, it's greater than its children 5 and 2. Okay, now coming back to heap sort. The first step we need to do is we have to create heap for the collection. And the next step is transform the heap into minimum heap or maximum heap. If we want to order an element in ascending order, we have to transform our heap into minimum heap. If we want to order an element in descending order, we have to transform the heap into maximum heap. If you are not clear on this, don't worry about it. You will get clear idea about it after we finish this video. Okay, fine. And the next step is delete the root node. So after deleting the root node, fourth step will be replace the empty space with last node of the tree. These are the steps we should follow to execute heap sort. Let's take this collection of data 4, 6, 1, 2, 5, 3. We are going to sort this collection of elements in ascending order. Okay, fine. Let's put these elements in array. I will store the elements from index position 1. So 4 will be in index position 1 and 6 will be in index position 2 and 1 will be index position 3, like that. Okay, now the first step is we have to create the heap based on these elements. Here we have 6 elements, so we should have 6 nodes in heap, right? Let's create root node. I will take this first element as the root node and next 2 elements are the child of this root node. So I will have 6 here and 1 will be here. Alright, then 2 and 5 will be child for 6. And 3 will be here. So we are done with first step. We just constructed this heap based on the order we have in the array. There is no special rules for this. Anyway, we are not directly going to use this heap to sort out the elements, right? We have to transform the heap into minimum heap or maximum heap. Based on that, we are going to sort the elements. Okay, fine. Now the next step is we have to transform this heap into minimum heap because we are going to sort the element in ascending order. So minimum heap rules is parent element should be less than its children's. So we have to compare the elements within the heap and swap the elements between the nodes to make the heap as minimum heap. So from where we have to start comparing the nodes? If the total elements of the node is n, we have to start from n by 2. For example, if the total elements is 4, we have to start from index 4 by 2, which is 2. What if the total node is 5? It's 2.5, right? For this, we can round it to nearest value, maybe 2. So here we have totally 6 elements. So we have to start comparing the elements from 3, right? Here index position 3 will be 1. So we have to start from 1 to compare the elements to make this heap as minimum heap. Let's take this 1 from the heap. Is any elements or less than 1 here? No, right? It is having only one child and it's 3. 3 is higher than 1, so no swap needed here. And move to next index position, which is 2. Here we have 6 in index 2. Let's take 6 from the heap and compare with its children's. Here both the nodes are smaller than 6. Among these two, which one is small? It's 2, right? Let's take that and swap with 6. So I will remove this and move the 2 here, and I will move 6 to here. Now let's do the same again. We have completed index 3 and 2. And next is index 1. Let's take index 1. It's 4. So compare this with its children's. 4 is having 2 and 1 as children. So we have to swap 1 with 4. So I will move this 1 to here and 4 to here. Now look at the heap and again start from index 3. We have to do the same process until index 3 to 1 will be less than its children. So check this 4. It's having lesser element in its children. So let's swap this. So I will move this 3 here and move this 4 to this location. Again index 2. Now the element present in the index position 2 is element 2. Let's check this. It does not have smaller elements than this. So let's move to index 1. Currently index 1 will have element 1. It's smaller than its children, right? So no swap needed here too. Now it's minimum heap. We have transformed the heap into minimum heap. So we have completed second step. And the third step is delete the root node from the minimum heap. So let's delete the root node from this minimum heap. Here 1 is the root node. We can delete this. So I will remove this and put this as first element of the array. And the next step is replace the empty space with last node of the heap. Here last node will be 4. So move this to root node. I'm just moving this to here. That's it. Now we have sorted the first element of the collection. We have to do the same process for all other elements. Now it's not minimum heap, right? Because this element is bigger than its children's. So again we have to transform this heap into minimum heap and delete the root node, and finally we have to replace the empty space with last element of the heap. Okay, let's do that. Now we have only 5 nodes in the heap. So now n is 5. So now from where we have to start to compare the elements? 5 by 2, which is 2.5. So we can round it to 2. So let's start with index 2. So here index 2 will be the element 2, right? Is this having any lesser element as child? No, right? So no swap needed here. And go for index 1. It's 4 here. Is there any element lesser than this? Yes, it's 2. This node is less than 4, right? So let's swap this. So move 2 to here and move this 4 to here. Again check index 2. Now it's 4. It's not having less element, right? So no swap needed here. And again check for index 1. Now index 1 is 2. This is also not having any lesser value than this. So no swap needed here. That's it. Now it's minimum heap, right? So what next? Delete the root node from this heap. So remove this 2 from here. And I'm adding this into second element of the array. And the next step is replace the last element of the heap with empty space. Here 5 is the last element of the heap. So move this 5 to root position. So now we are end up with 2 elements sorted. Let's do it for remaining elements. Now we have totally 4 nodes. So 4 by 2 is 2. So we have to start comparing from index position 2, right? Here index 2 will be node 4. Check whether it's having any smaller node as child. No. So no swap needed here. And next position is index 1. Here index 1 is 5. Check whether it's having any smaller node as child. Yes, it's having 3. And 3 is the smaller than 5, right? So swap it. Again we have to check index 2. So here no swap needed. And check index 1. Here also no swap needed. So now it's minimum heap, right? So let's do the next step. Let's delete this root element. It's 3 here. So I'm deleting this. And next step is replace last node of the heap to the root node. So I'm moving this 6 to here. And whatever the element we have deleted from the heap, add that as the next element of the array. Now we have sorted 3 elements. We will do the same things for remaining elements. Now we have totally 3 elements. So 3 by 2, which is 1.5. So we will round off this to 1. So start comparing from index position 1 to transform this heap into minimum heap. Here index 1 will be 6. So check whether it's having any smaller elements than this. Yes, it's 4. So let's swap. So we will move this 4 to here and 6 to here. That's it. Now it's minimum heap, right? So next step is remove this root and move the last element of the heap to root. So let's remove this 4 and add this next element of the array. So now last element is 5. Move this 5 to root. That's it. Now we have only 2 nodes in our heap to process. That's great, right? So 2 by 2, which is 1. So start comparing this heap from index 1. 5 is having only one child and it's not less than this. So no swap needed. It's minimum heap only. So delete this root. I'm removing this 5 and add it to the array as the next element. And we have only one element. Here we can stop our heap sort algorithm. We can add this element to this array as the last element. That's it. We are done with the algorithm. Now our collection elements are sorted in ascending order. Actually, we wanted to sort this collection in ascending order. That's why we have transformed the heap into minimum heap. If we need to sort it on descending order, we could have used maximum heap. But we have to do the same step to sort the elements. Only thing is we have to transform the heap into maximum heap. So if we use maximum heap, larger element will be present in the root node. So when we delete the root node and move that element into array. So if we use the maximum heap, we will delete element 6 as the first element. And it will be the first element added to the array. And next bigger element is 5. So it will be added next to 6 in this array. Similarly, next element will be 4 and next will be 3 and next 2 and finally 1. So finally we will get descending order as the result. That's it, guys. This is how heap sort algorithm will works. Hello guys, welcome back. In this video we are going to discuss about implementation approach for heap sort algorithm. The first thing is we have to create heap and then we have to convert the heap into minimum heap or maximum heap. If we convert the heap into minimum heap, root element will be the minimum value, right? After that we will move this root into last node of the heap and finally we will delete this last node and we will move this into array. Whenever we move this last element into array, we will keep this last element into first position of the array. That's the reason if we use minimum heap, we will form the array in ascending order. If we use maximum heap, maximum element will be the root node. Whenever we delete the last element of the heap, maximum element will be the first element of the array. That's the reason we are getting descending order, right? But here I'm going to create maximum heap, but still I'm going to order the array in ascending order. Whenever I move the heap element into array, I will move it into the last position of the array. Means if I'm using maximum heap, larger element will be deleted first. That has to be moved to last element of the array. And for the next iteration, last node will be moved to last index minus 1. So that we can form ascending order of the array. Right? Okay, let's do that. I just declared one array which is holding 6 elements within it. I'm just passing this array into sort method. In this method we are going to implement heap sort algorithm. So the first thing is we have to create heap. So before we start execution, I'll just put some debug points here. We will run this program in debug mode. So this is our array. It's holding 6 values within it. The first thing is we have to create heap. I'm just calling the heapify method by passing this array. We are just creating the maximum heap by passing array and index position. In the current iteration, index will be n divided by 2 minus 1, which is 6 divided by 2 minus 1, which is 2. Right? In this array, index 2 will be value 4. I'm just passing this index and array. In this maximum heap, it will find the maximum element of the array. It will put it into the root element of the heap. If you see here, this is the index we are passing, right? From here, 2 into I means 2 into 2 is 4. This will be the left child. 2 into I plus 1, which is 5. This element is the right child of this 4. And from these 3 values, we have to find which is the maximum value. If left is greater than this value 4, maximum will be left. If right is greater than this maximum element, maximum will be right element. Or else whatever element we send, that is the maximum element. So at this stage, maximum element will be index position 5. In this case 7, right? So we have to swap this 7 with this 4. If you see here, 7 will be moved to index position 2 and 4 will be moved to last position. Okay, now again we have to call this heap method by passing this maximum value. Maximum means here index 5, right? We have to pass this index 5 to this heap method, and we have to pass this updated array as well. And the next time here left will be 10, right? Because 2 into 5 10, 2 into 5 plus 1, which is 11. This is exceeding our array length, right? So we can skip this. As of now, array will be looks like this. In this second iteration, we are just decrementing our I value, right? So initially it will be 2, now it will be 1. We are just passing 1 here. 1 means value 11 here. So left will be 2 into 1, which is index 2, 4, and right will be 1. 2 into I plus 1, which is index position 3, that is 1. While comparing these 3 elements, 11 will be the maximum value, right? So maximum will be 11, means index position 1, but our I value will be also 1 and maximum also will be 1. So no changes required here. And in the next iteration, I will be 0. If it's 0, 2 into I, left will be 0, right will be 0 plus 1, which is 1, right? So from this, 11 will be the maximum value, index position 1. So we have to swap this 11 with index position 0. If you see here, after this swap, 11 will be moved to index position 0, 6 will be moved to index position 1. So that's it, right? So whenever we call this heapify method, we got the maximum value into the first element of the array. So what next? We have to swap this last element into last position of the array, right? That is what we are doing here. So after moving this 11 will be moved to last position, and whatever we have it in this last element, right, that will be moved to index position 0. Now again we have to do the same process. Now we have completed this last position, right? For the next time we should not consider this last position, means n value we have to reduce by 1. That is what we are doing here. So whenever we call this maximum heap, so same process will happen again. Means whatever element we have from this, which one is the maximum value, that has to be moved to index position 0. I'm just removing these breakpoints. If you see this array, 7 will be moved to index position 0 because this is the next maximum value, right? And then again we have to swap this 7 with last index position. As of now, our last index is index 4. After swapping this, 3 will be moved here, 7 will be moved here. Again we have to reduce our n value by 1, right? Now from this last 4 elements, which one is maximum value? 6. In the next maximum heap call, 6 will be the maximum value. It's swapped, so it's moved to index position 0. Now again we have to swap this with index position 3. In index position 3 we have 1 has to be moved to index position 0 and 6 has to move to index position 3. It's done. Now we have completed last 3 positions. So again we have to reduce our n value by -1. Maximum heap method will be called. So at this call, 4 has to be moved to index position 0. Right? It's moved. Now we have to swap this 4 with last position. So swapped. Again we have to reduce our array length by -1. So this 3 will be moved to top by using maximum heap. Now again we have to swap this. That's it. Now our array is sorted now. If you see here, it will be printed all the elements here. 1, 3, 4, 6, 7 and 1. So this is how heap sort algorithm will work.
Congratulations, you made it in the course. So by now we have gone over tons of materials. We have gone over it. You know how to use right data structures and how to choose a right algorithm for your problem statement. Now what I want to do in this lecture is I want to talk about next step where you go from here. So the next step is practice, and next practice, and next again practice, because now you know complete details about data structures and algorithms. As I told you already, data structures and algorithms are not a technology, it's a skill. So practice is the only way to develop your skill. So do practice a lot. I recommend you to spend your valuable time in geeksforgeeks.org. This is a computer science portal for geeks. It contains well-written, well-thought, and well-explained computer science and programming articles and quizzes. If you see here, you can see almost all the topics in computer science are there. If you see this menu, here you can find articles related to algorithms and data structures. See, inside this algorithms menu, you can find lots of information about it. Say for example, I'm going inside the all algorithms. See, here is analysis of algorithm, search and sorting algorithms, greedy algorithms, and graph algorithms, something like this. Here, related to algorithms, you can find analysis of algorithms. Inside this, there is lots of materials related to analysis of algorithms. Okay, I'm just go back and I'm going inside searching and sorting algorithms. Here, related to searching and sorting algorithms, you can find lots of articles. I'm going inside linear search. Here you can see clear explanation about the topic, and here you can find the implementation approach in almost all the popular languages. And another great resource to increase your problem solving skill is hackerrank.com. Here you just sign up with your email ID. After that, this site will prompt you to go access your dashboard. Here you will get tons of practice activities. If you see here, under the problem solving skill, you can see algorithms and data structures. Not only this, if you want to gain your problem solving skill in any language, you can choose your preferable language here. Same as here you can choose your favorite skills like database, security, like that. We are interested on data structures and algorithms, right? So I will just go inside the algorithms. Here you will get lots of problems to solve related to algorithms. In right hand side, you can choose difficulty level for your problems. First, start with easy level. Once you feel that ready to go for next level, then you can go for the medium difficulty, and finally go for hard difficulty. So I'll just go for this problem to solve. If you see here, it's your problem statement. This is what you have to solve, and for this input, expected output will be this. And here you will get hints to solve this problem statement. And here you will find the coding editor to solve this problem. By choosing this drop down, you can choose your familiar language to work with and start coding here. Once you have done with coding, here you can see run code and submit code. Run means it will just run your code without submit. Once you're done with your code, you can just hit submit button. Here HackerRank will test your code by help of already designed test cases for this problem and give the results to you immediately. I would suggest you to spend more time on these two websites. This will increase your problem solving skill and it will increase your debugging ability.